Chapter 1 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista, Zaleski. The Romance of Modern Astronomy by Hector Macpherson. Chapter 1. Our Place in the Universe. Science is the study of nature. By means of science, we are enabled to understand the everyday things of life, the flowers, the hills, the stars, and the place which they occupy in nature. Thus, botany is the study of flowers and trees. Geology is the study of the hills and rocks, while astronomy raises our thoughts to the star-spangled heavens. Of all the sciences, and they are many and varied, astronomy is the most interesting and the most wonderful. Not only is it full of interest, but it is in many ways the most educative study which the human mind can pursue, for it enables us to understand the position which our world occupies in the universe. By astronomy, men were enabled to answer the question, what is the Earth? In childhood we learn that the Earth is round like an orange or a ball. But when we stand out in the open and look around us, the Earth seems more like a vast, illimitable plain than a round globe. Long ago, in the childhood of the race, men believed that our world would be a vast, illimitable plain, but reflective minds were not satisfied with this theory. They soon perceived that the earth was not a plain. The sun, it was observed, rose in the east every morning and set in the west every evening, and it was obvious that it could not rise and set through the solid ground. The question presented itself to those early Chaldean and Greek students of nature. Where did the sun go every night? Did it pass under the earth? Such an idea was unthinkable to those early scientists. Was not the earth solid and immovable, firmly fixed at the bottom of creation? Accordingly, some very remarkable theories were devised to explain how the sun rose in the east in the morning, after having disappeared in the west the previous evening. Some of the ancients believed that the sun fell into the sea at night and was quenched, and that the gods were busy all night making a new sun to start the next morning in the east. But, as Sir Robert Ball remarks, this was thought to be such a waste of good suns, that a more economic theory was afterwards proposed. This was, that as the sun was falling into the ocean in the west, it was caught by the god Vulcan, who was wading in his boat to prevent it falling into the sea. Having placed the orb of day in his boat, Vulcan rowed round by the north, where a great ocean was supposed to exist. Arriving in the east, he pitched the sun into the sky with tremendous force, to commence another day's journey. Theories such as these had influence for many years over the minds of men. Gradually, however, it became apparent that such ideas were absurd, and that the sun must really go below the earth. And here students of nature asked, what is the earth, and what supports it? Many grotesque theories were put forward. One speculator thought that the earth was held up by great pillars, which allowed the sun to pass between them. Another believed our world to be supported by enormous mythical animals. Some support, in the minds of ancients, was absolutely necessary. The author of the Book of Job, however, had grasped the truth. For writing of the power of the Creator, he says, "He hangeth the earth upon nothing." This is literally true. The earth hangs upon nothing. Gradually, the truth dawned that the earth was a globe, not a vast plain, a view which was held by the great Greek philosopher Aristotle, and became generally accepted. Aristotle thought that the earth, a globe suspended in space, was the center of the universe, round which the sun, moon, and stars revolved. By this time, considerable progress had been made in the study of astronomy. The study of the stars had become a science of measurement, and it was soon apparent that the celestial bodies had not one motion round the earth only, but a number of motions. For instance, it was known that the sun, moon, and stars revolved round the earth every 24 hours. But it soon became apparent, as observation progressed, that the moon had another motion round the earth once in a month, and that the sun seemed to have also another motion, revolving round the earth once in a year. Then, attentive observation of the heavens disclosed the existence of another class of objects. The ordinary stars, fixed stars, as they came to be called, revolved once in 24 hours, but they did not change their positions relative to each other. The star groups or constellations remained unchanged. the early astronomers noted that there were 5 bright star-like objects, which, instead of remaining fixed in the sky, moved in an irregular manner round the heavens, always keeping close to the path traversed by the sun on its annual journey. These the early observers named planets, which is Greek for wanderers. It was soon recognized that there were 5 of these objects, each different from the other. There was Venus, the brightest of the wanderers, shining with a soft, gentle, steady light, named by the ancient Greeks after their goddess of love. They noticed that Venus never moved far from the sun, that it was never to be seen shining on a really dark sky. It was also observed that Venus was sometimes visible as an evening star after sunset, and sometimes as a morning star before sunrise. Indeed, it was long thought that the morning star and the evening star were separate bodies. But very early in astronomical history, it was recognized that they were one and the same. The ancients recognized another bright object, also visible as an evening and morning star, and keeping much closer to the sun than Venus. They called the planet Mercury, the messenger of the gods. But they also called it the sparkling one, from its rapidly twinkling light. Another bright object, much brighter than Mercury, was also recognized, a great golden star, which, instead of keeping close to the sun, swept majestically round the entire heavens. This they named Jupiter, after their chief deity. Then they recognized a planet of reddish hue, which at times waxed almost as bright as Jupiter, and then rapidly waned. From its fiery color, they named this object Mars, after the god of war. Yet another planet, fainter than the rest, slow-moving, of a dull yellowish light creeping round the entire heavens once in about 30 years, was named Saturn after the god of time. Each of these planets had its own peculiarities of motion, and partook also in the revolution of the entire heavens once in 24 hours. The problem before the ancient astronomers was then how to account for the motions of the sun, moon, planets, and stars. Many and varied were the explanations put forward. Eudoxus, a Greek thinker who died about 355 BC, was the author of an ingenious attempt to explain these motions by an elaborate theory known as that of the spheres. The Earth, he believed, was a globe firmly fixed at the center of the universe. Each planet was fixed to a number of different spheres by the manipulation of which the elaborate motions resulted. Then, at the extreme limit of the universe was a sphere to which all the stars proper were fixed. Another theory was that of the astronomer Hipparchus, which was developed to its greatest extent by his successor Ptolemy, of Alexandria in Egypt. Like Eudoxus, Ptolemy believed that the Earth was firmly fixed as the center of creation, but he did not accept the theory of spheres. He believed that the sun, moon, planets, and stars revolved round the Earth in the following order: the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and the stars proper, which, as in the theory of Eudoxus, were supposed to be attached to the inside of a large sphere. But Ptolemy was not ignorant of the irregularities in the motions of the planets, of the fact that the planets did not move with uniform velocities. He was one of the most thoughtful of the ancient astronomers, and he knew that if a planet moved around the Earth in a uniform circular orbit, its velocity and direction would not change. Accordingly, he devised a most complicated and ingenious theory that the planets moved in circles, and that the centers of these circles revolved round the Earth in larger circles. The smaller circles were called epicycles. As new irregularities came to be discovered, new epicycles had to be invented, until at last the theory became so difficult and cumbersome that few could understand it. Indeed, it is recorded of a certain king of Spain that when his tutor was explaining to him the theory then generally accepted, he exclaimed in disgust that if he had been consulted at the creation, he could have given some useful hints for simplifying the system of the universe. In spite of the intricacies and improbabilities of Ptolemy's theory, it was accepted for 1400 years. It is true that some keen minds among the Greeks had come to the conclusion that there was a much simpler conception of the universe, but they had not the courage to declare for a new theory, and it was left for Nicholas Copernicus, a Polish clergyman, to propound the system which bears his name. Copernicus, after giving deep attention to the subject, came to the conclusion that it was much easier to believe that the Earth turned on its own axis, and so caused the apparent motion of the sun, moon, planets, and stars. Then to think that these objects all happened, by some coincidence, to go round our planet in exactly the same time. Copernicus also came to the conclusion that instead of the sun moving round the Earth once a year, and the planets also revolving round our world in complicated orbits, it was more reasonable to believe that the Earth and the other planets revolved round the sun. This was the theory which Copernicus put forward. It had the merit of simplicity, but notwithstanding this fact it was disbelieved, and its supporters were threatened with persecution. Nevertheless, men of science were driven to accept it because they saw how greatly its acceptance simplified the complicated motions of the planets. Tycho Brahe, the famous Danish astronomer, abandoned the idea that the planets revolved round our Earth, choosing to believe that they revolved round the sun, which moved round our planet. The next step was to declare boldly that the theory of the Earth's motion explained more satisfactorily the motions of the celestial bodies. This step was taken by Bruno, Galileo, and Kepler, but it was taken at a great risk and at a great sacrifice. Bruno was burned alive for holding this theory among others which the Roman Catholic Church had pronounced to be impious. Galileo had to suffer much persecution for his championship of the Copernican theory. Its opponents disliked Galileo most of all because he brought forward unanswerable arguments in favor of the new system. Kepler, the least persecuted of the three, was destined still further to improve the theory by his famous 3 laws. He showed that the Earth and the other planets, instead of revolving round the sun in circular paths, moved in ellipses. He was enabled to explain many of the irregularities which Copernicus had to leave unsolved. Thus, the labors of Copernicus, Galileo, and Kepler showed us beyond a doubt our true position in the universe, that the Earth is merely a planet in constant revolution round the sun, a member of the Sun's system, and a companion planet of Mercury and Venus, Mars, Jupiter, and Saturn. It was Sir Isaac Newton who demonstrated beyond doubt the truth of the system of Copernicus. Newton furnished mankind with a key to unlock the mysteries of the solar system. He explained why the Earth and the other planets were constantly moving round the sun, and why they moved in elliptical orbits. It was in the year 1666, when Newton was a young man in his ancestral home near Grantham in England, that his mind first lit on the grand idea of the law of gravitation, that every particle of matter in the universe attracts every other particle. The story goes that one day when Newton was sitting in his garden, he saw an apple fall to the ground. Now he knew why the apple fell, because it was heavy. In other words, because it was drawn to the earth by the power of gravitation. And he was led to ask if the same force did not keep the moon in its monthly orbit round the earth, and prevent it flying off into space, and also keep the earth and the other planets in their paths round the sun. After 20 years' hard mathematical work, he was able to prove that the force which drew the apple to the ground held the moon in its orbit, and that the moon moved round the earth and the other planets round the sun, simply by virtue of the inherent power of gravity in these various bodies. For instance, the earth attracts the moon, and the moon attracts the earth. But the earth is so much larger than the moon that our satellite is compelled to revolve round our world. Similarly, the sun attracts the earth, and the earth attracts the sun. But owing to the immense superiority of the sun in size, the earth, though having a natural tendency to move in a straight line, is compelled to move round the larger body. Thus Copernicus showed us our Earth's position in the solar system, and Newton showed us why we occupy that position. The result of the change in astronomical thought was that the Earth's inhabitants could no longer consider themselves the chief objects of creation. Our world was brought down from the position of ruler and center of the universe to the humble place of a small planet revolving round the sun. As we shall find in the following chapters, this was but the first step in the change of opinion, for the researches of Sir William Herschel and later astronomers have proved that our planet is a mere grain of sand in the ocean of infinity. Astronomy enables us to understand the fact, though we but imperfectly realize it, that our Earth, which seems to us a great flat immovable plane, is in reality a globe about 8,000 miles in diameter, turning on its own axis in 24 hours, and dashing onward in its orbit round the sun at the rate of 18 miles a second. We do not feel the motion of our planet, because we are carried along with it, and the atmosphere is also a component part of our globe. It is difficult to grasp the fact that our planet is moving onwards with so great a velocity that each second of time finds us 18 miles onward in our journey. Thus we see that astronomy, alone of the sciences, answers the question, what is our Earth and what is its position in nature? End of Chapter 1.
Chapter 2 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 2. Effects of the Earth's Motions. The motion of the Earth is the magic key which unlocks the door of the mysteries of the everyday phenomena of nature. Day and night, the seasons, twilight, quote, the midnight sun, end quote, the long polar night, all these phenomena are easily understood when we regard them in the light of the rotation of the Earth on its axis, the inclination of this axis, and the revolution of the Earth round the sun. To the first of these facts, the rotation of the Earth, we are indebted for the phenomenon of day and night. The Earth is constantly whirling round on its axis from west to east, and the result is the apparent motion of the heavenly bodies from east to west. By this motion of rotation, we get the first and most obvious measure of time, the day, which measures in length only a few minutes under 24 hours. A good idea of the rapid rate at which the Earth is turning on its axis may be had by pointing a telescope to a star, and by noticing how swiftly the star passes out of the field of view. At sunrise and sunset, too, we notice plainly the difference made by a few minutes. Owing to the fact that the Earth has an atmosphere, daylight does not disappear whenever the sun sinks below the horizon. The rays of the sun still strike the upper regions of our atmosphere, and thus we have twilight and the gradual darkening of the sky and disappearance of daylight. The chief effect of the Earth's revolution round the sun, an effect which affects the periods of light and darkness, is the change of the seasons, spring, summer, autumn, and winter. This ceaseless cycle, to which the Earth's inhabitants are so accustomed that they scarcely stop to ask themselves the why and wherefore, is due chiefly to one astronomical fact. The axis of the Earth, the imaginary line joining the North and South poles, is inclined to the orbit of our planet by about 67 degrees. This explains the seasons and the differing lengths of day and night on the various parts of the Earth. Most of us have heard of such phenomena as the long polar night, the midnight sun, etc., but few really understand that these phenomena are due to the same causes which give us our long periods of daylight in summer and of darkness in winter. At the spring equinox, day and night are equal all over the world, at the poles and at the equator. At this period, both poles of the Earth are equally exposed to the solar rays. Neither is tilted towards the sun more nor less than the other. But as the Earth moves gradually round, the northern hemisphere becomes more and more inclined towards the solar beams, while the southern hemisphere is more and more inclined away from the orb of day. Spring is giving place to summer. At the summer solstice, the northern hemisphere is tilted towards the sun at its greatest inclination, while it is midwinter in the south. The days and nights were equal at the spring equinox. At the summer solstice, the days are much longer than the nights in the northern hemisphere, the opposite being the case in the south. After the 21st of June, the period of darkness increases in the northern hemisphere and decreases in the southern, until on the 21st of September, daylight and darkness are equal all over the globe. In its cycle of change, the axis of the Earth is again upright relative to the sun. After the autumn equinox is past, the northern hemisphere tilts more and more away from the sun, while the southern comes more and more into sunlight. The result is that by the 21st of December, when the winter solstice is reached, The northern hemisphere has a short period of daylight and a long period of darkness, while the reverse state of affairs takes place in the south. The northern hemisphere is tilted from the sun at its greatest tilt. After the winter solstice, the period of daylight increases in the northern hemisphere and decreases in the southern, until we come again to the 21st of March, when at the spring equinox, day and night are equal all over the world. In the early ages of the world, before astronomy had been developed, men did not understand this revolution of our dwelling place round the sun. They only knew, just as the unlearned know today, that at the winter solstice, in the middle of December, the sun rose in the southeast, moved across the southern sky, rising to a low altitude above the horizon, and set in the southwest in the afternoon. We notice that after the solstice is past, the sun rises a little earlier each morning and sets a little later each evening, that it rises farther east each morning and sets farther west each evening, until on the 21st of March, the orb of day rises exactly in the east and sets exactly in the west. Likewise, we notice that as more and more is seen of the sun, the earth wakens out of its winter sleep. Trees begin to bud, grass to grow. In short, nature revives. As one writer puts it, quote, "The melting of the ice and snow, the gradual reviving of brown soils, the flowing of sap through branches apparently lifeless, the mist of foliage beginning to enshroud every twig until the whole country is enveloped in a soft haze of palest green and red. All these are nature's signs of spring." End quote. Then, as spring gradually passes into summer, the sun rises every morning a little farther north, and sets every evening a little farther north, while every day it rises higher and higher in the sky. Then on the 21st of June, the quote, longest day, end quote, it rises northeast and sets northwest, and is about 18 hours above the horizon. This is the period of longest daylight, because, as explained, the northern hemisphere is turned directly towards the sun, but the period of greatest heat is about a month later in coming. If the earth and the atmosphere could retain none of the heat which is showered down from the sun, the period of greatest heat would exactly coincide with the summer solstice. However, the accumulation of heat retards the time of the greatest heat until about a month after the solstice, the end of July and the beginning of August. Similarly, the period of greatest cold is a month later than that of least sunlight, at the end of January and the beginning of February. Gradually summer passes into autumn. After the summer solstice is past, the sun begins to rise later and later each morning, and sets a little earlier every evening. And in addition, the orb of day does not rise so high in the heavens. This continues until the autumn equinox, when the sun rises due east and sets due west. In fact, day and night are equal all over the world, and the conditions are the same as those at the spring equinox. But there is one difference. The weather at the spring equinox is generally cold and uncertain, while at the corresponding period in autumn it is summer-like and pleasant. This is due to the same cause which was previously mentioned, that after summer solstice the earth continues to store up heat, while after winter the earth is slow to absorb heat. In short, the autumn equinox generally takes place in summer-like weather. As an American astronomer expresses it, quote, "Not until falling leaves begin to flutter about our feet, and grapes and apples ripen in orchard and vineyard, do we realize that autumn is really here, that everything is mellow and finished. Our hemisphere is turning yet farther away from that sun on which all growth and development depend. When trees are a glory of red and yellow and russet brown, when corn stands in full shocks in fields, and day after day of warmth and sunshine follow through royal October, it seems impossible to believe that slowly and surely winter can be approaching. But soon chilly winds whistle through trees from which the bright leaves are almost gone. A thin skin of ice crystals shoots across wayside pools at evening, and speedily shivering winter is upon us. Just before Christmas, this part of our earth is tipped its farthest away from the sun. Then for a few days, the hours of darkness are at their longest. The sap has withdrawn far into the roots of the trees until the cold shall abate. Leaden skies drop snowflakes, and earth sleeps under a mantle of white." End quote. This description applies only to the temperate zones of the earth. As we go northwards, we approach the exaggerated aspects of the same phenomena, the midnight sun and the long polar night. The cause of these phenomena is a source of difficulty to many, but it is quite easily understood with a little thought. At midnight in the end of June, in Scotland, there is very little darkness. The sky never grows actually dark. We seem to see the glow of the sun almost up to midnight after it sinks in the northwest. As we go farther north, we see more and more of the sun. We follow it farther and farther until it goes just below the horizon and no more. Still farther north, it skirts the horizon and is visible all night at the 66th parallel of latitude. Beyond this, the sun does not disappear at all in summer, and there are 6 months of daylight. The phenomenon of the midnight sun draws many to the northern parts of Sweden, Norway, and Russia, where for a few days at the summer solstice, the sun merely skirts the northern horizon. A good description of the midnight sun is given by Paul du Chaillu in his account of his travels in Scandinavia. Quote, "The brilliancy of the splendid orb varies in intensity, like that of sunset and sunrise, according to the state of moisture of the atmosphere. One day it will be of a deep red color, tinging everything with a roseate hue and producing a drowsy effect. There are times when the changes in the color between the sunset and the sunrise might be compared to the variations of a charcoal fire, now burning with a fierce red glow, then fading away and rekindling with greater brightness. There are days when the sun has a pale, whitish appearance, and when even it can be looked at for 6 or 7 hours before midnight. As this hour approaches, the sun becomes less glowing, gradually changing into more brilliant shades as it dips towards the lowest point of its course. Its motion is very slow, and for quite a while it apparently follows the line of the horizon, during which there seems to be a pause, as when the sun reaches noon. This is midnight. For a few minutes the glow of sunset mingles with that of sunrise, and one cannot tell which prevails. But soon the light becomes slowly and gradually more brilliant, announcing the birth of another day. How beautiful was the midnight! How red and gorgeous was the sun! How drowsy was the landscape! Nature seemed to sleep in the mist of sunshine. Crystal dewdrops glittered like precious stones as they hung from the blades of grass, the petals of wild flowers, and the leaves of the birch trees." End quote. Farther north, the sun is constantly visible, and the North Pole has 6 months continuous light. But there is another side to the picture. For 6 months there is continuous night, and even in the north of Sweden, Norway, and Russia, there are days in midwinter when the sun does not rise, just as in summer there are days when it does not set. Du Chaillu, after describing the midnight sun, has the following remarks on the winter in the same region, which is worth quoting. Quote, "The grass turns yellow, the leaves change their color, and wither and fall. The swallows and other migrating birds fly towards the south. Twilight comes once more. The stars, one by one, make their appearance, shining brightly in the pale blue sky. The moon shows itself again as the queen of night, and lights and cheers the long and dark days of the Scandinavian winter. The time comes at last when the sun disappears entirely from sight. The heavens appear in a blaze of light and glory, and the stars and the moon pale before the aurora borealis." End quote. Such are the various phenomena resulting from the fact that the axis of the Earth is inclined to the plane, or level, of its orbit. Were the axis upright, there would be no seasons, no springtime, no summer, no autumn, no winter season. There would be no midnight sun and no long polar night. In fact, the continuous state of affairs would be an everlasting springtime without the charm of our earthly spring. This seems to be the state of affairs on Jupiter, where the axis is nearly perpendicular to the planet's orbit. Another fact has also something to do with the seasons, though only in a modified degree. As the orbit of the Earth is not a perfect circle, but an ellipse, the Earth is at one point of its orbit nearer to the Sun than at its other. The Earth is nearer to the Sun by 3 million miles in our winter than in our summer. At first, this seems a paradox, that the time of closest approach to the orb of day is the time of greatest cold. A little consideration, however, soon disposes of the difficulty. In the northern hemisphere, the decreased distance of the Sun modifies the severities of winter, while its increased distance mitigates the heat of summer. In the southern hemisphere, on the other hand, the time of greatest heat takes place when the Sun is nearest, and the time of greatest cold when the Sun is at its greatest distance. Thus, the climate in the northern hemisphere is rendered more equable than that in the south. Thus, we understand that it is owing to the inclination of the axis of the Earth that the Sun's apparent path in the heavens, the ecliptic, is tilted, and that the Sun rises so much higher in the sky in summer than in winter. A similar line of reasoning applies to our satellite, the Moon. There is much less moonlight in the summer than in the winter. At a first consideration, it seems as if this was owing to increased daylight, the moonlight not being required, and consequently not noticed. But such is not the case. There is really less moonlight in summer than in winter. This arises from the fact that before the moon can be full and shining with complete radiance, it must be, quote, in opposition, end quote, to the Sun, that is, situated in the diametrically opposite portion of the sky. In winter, the Sun is traversing the lower zodiacal constellations, and as a result the moon, at the full phase, passes through the higher. The full moon at midwinter has the same situation as the Sun in midsummer. Thus, in winter, we get more moonlight than sunlight. In summer, the conditions are reversed. The Sun is in the higher constellations. Consequently, the full moon at midsummer occupies the place of the Sun at midwinter, and thus there is more sunlight than moonlight. Instead of shining from on high with silvery radiance, the moon, in summer, creeps through the lower constellations, gleaming with a golden hue which harmonizes with the period of summertime. As Mr. Maunder puts it, quote, "The evasive moon recognizes that the season belongs by right to her more powerful brother, and timidly skirts the south as if anxious to escape notice." End quote. The apparent yearly motion of the Sun is due to two causes, the motion of the Earth and the inclination of the Earth's axis. The apparent motion of the Sun is not itself visible, but we can trace it in an apparent drift of the stars into the sunlight. The stars, as a result of the Sun's apparent motion amongst them, set 4 minutes earlier each night. In a fortnight, or a month, this makes an appreciable difference in the aspect of the sky. For instance, at 10 p.m. in the beginning of January, Orion and the winter constellations occupy prominent positions in the southern heavens. At the same hour a month later, they have moved considerably to the west, while in March they are beginning to pass over towards the western horizon. By watching these changes with care and attention, the ancient astronomers were enabled, with tolerable accuracy, to trace the apparent pathway of the Sun among the stars. A word may be said here as to the difference of the day measured by the Sun, quote, the solar day, end quote, and that measured by the stars, quote, the sidereal day, end quote. Sidereal time is the exact time required for one star to move from the meridian round to the meridian again. In fact, it is the exact time required by the Earth to rotate on its axis. But the sidereal day is not the ordinary day. Were the Earth standing still, it would be so. But our planet not only whirls round on its axis, it is also moving round the Sun. As a consequence of the motion of the Earth, which gives rise to an apparent motion of the Sun appears to come to the meridian 4 minutes later each day if we reckon time by the sidereal clock. In other words, the day measured by the Sun is 4 minutes longer than the day measured by the stars, and the difference amounts to exactly 1 day in each year. Now, sidereal time is in reality the only true measurement of the day, because it is the exact time of the rotation of the Earth's axis. But it is impossible to measure our ordinary time by this method. Professor Todd puts it very clearly in the following words. Quote, "Sidereal noon comes at all hours of the day and night during the progress of the year. Plainly, then, sidereal time is not a fit standard for regulating the affairs of ordinary life, for while it would answer for a fortnight or so, the displacement of 4 minutes daily would in 6 months have all the world breakfasting after sunset, staying awake all through the night, and going to bed in the middle of the forenoon." End quote. The difficulty cannot be exactly solved by taking the solar day instead of the sidereal, for, as Professor Todd says, quote, "Begin on any day of the year and observe the sun's transit of the meridian as you did that of a star. The instant when the sun's center is on the meridian is known as apparent noon. If you repeat the observation every day for a year and compare the intervals between successive transits, you will find them varying in length by many seconds, because they are all apparent solar days. They will not all be equal, as in the case of the star. By taking the average of all the intervals between the sun's transit, that is, the mean of all the apparent solar days in the course of the year, an invariable standard is obtained, like that from the stars themselves." End quote. Thus, we have the mean solar day by which all the clocks and watches in everyday life are regulated. End of Chapter 2.
Chapter 3 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 3 The Orb of Night. In early times, as was seen in the previous chapter, men believed that the earth was the center of the universe, and round it all the orbs of heaven revolved. Today we know that only one celestial body owns allegiance to the earth. That orb is our satellite, the moon, which goes around our world once in about 27 days. The moon's revolution round the earth from east to west in a little over a day is only apparent, the result of our planet's rotation on its axis, but its motion from west to east is real. We owe much to the moon. To it we owe the glorious silvery light which our satellite sheds on us. As Flammarion has said, quote, "It is the delightful hour when all nature pauses in the tranquil calm of the silent night. The sun has cast his farewell beams upon the weary earth. All sound is hushed, and soon the stars will shine out one by one on the bosom of the sombre firmament. Opposite to the sunset in the east, the full moon rises, slowly, as it were, calling our thoughts towards the mysteries of eternity, while her lamplight spreads over space like a dew from heaven." End quote. Not only is the moonlight useful, it is exquisitely beautiful. The most casual observer of the heavens cannot fail to notice that as the moon moves eastwards in the heavens its form changes. When we first see the new moon in the western sky above the sunset, it is a slender crescent of silvery light. Night after night it grows in size until about 5 days after we first see it, it is half full. It has reached its first quarter. It continues to grow for about another week until one evening it rises just as the sun sets and reaches the meridian, the point due south, about midnight. While it is fully illuminated and its round disk sheds over our world that inimitable light known as moonlight, then slowly its size decreases. it rises later and later, and grows smaller and smaller, until when it reaches its last quarter, it is only to be seen in the morning hours. And then it draws closer to the sun until its thin little crescent is lost in the sunrise, to emerge some days before the sunset as new moon. Those who do not give the matter sufficient consideration believe that the moon actually changes its shape as it moves round the earth. Indeed, it is recorded of a novelist that he wrote of a star shining between the horns of the crescent moon. The poet Coleridge makes the same mistake in The Ancient Mariner. A little consideration, however, will show that there is no real change of shape. Like our own world, the moon is a dark globe, and it only shines by the reflected light of the sun. Therefore, only one half of the globe is illuminated at once, just before the crescent of the new moon appears. When the moon is between the earth and the sun, the dark side of the moon is turned to the earth, and we do not see it. At first quarter, we only see one half of our satellite illuminated. As the moon moves eastward, we see more and more of the illuminated surface, until at full moon, the orb is at the other side of the earth from the sun, and we see it fully illuminated. Then, as it draws closer to the sun, we see less and less of the illuminated surface, until it becomes once again invisible. What is the distance of the moon? That is the first question which presents itself to the beginner in astronomy. The distance varies slightly from time to time, as its orbit round our earth is not circular, but slightly elliptical or oval, but the average distance is 238,000 miles. It is near to us when compared to the other celestial bodies, but the question at once occurs, how is it possible to measure the distance? We do not require to reach the moon in order to measure its distance, any more than we require to ascend a mountain to measure its height. In these measurements, we proceed on the principles of land surveying. The principles of land surveying depend on the measurement of angles. As Professor Comstock puts it, quote, "The instruments used by astronomers for the measurement of angles are usually provided with a telescope, which may be pointed at different objects, and with a scale to measure the angle between lines drawn from the instrument to two different objects, such as two church steeples, or the sun and moon, and this is usually called the angle between the object. By measuring angles in this way, it is possible to determine the distance to an inaccessible point." End quote. An observer wishes to measure the distance of a flagstaff at the other side of a river which he is unable to cross. Accordingly, he chooses 2 points on his own side of the river from which to make observations. The line joining these points he calls the base line, the length of which he ascertains. From either point he measures the angle subtended by the opposite sides at these points. Having measured the angles, he now determines the elements of the triangle, and by means of trigonometry he knows the distance across the river to the flagstaff without having ever crossed it. Similarly, in regard to the distance of the moon, one astronomer located, say, at Greenwich or Edinburgh, measures the moon's position amid the neighboring stars. Another, at Cape Town or Sydney, measures its position seen from that place. The difference of position of the moon at the two stations, the parallax, as it is called, is then measured, and the distance of the moon is found to be 238,000 miles, a great distance indeed when compared with our terrestrial standards, but very small in the eyes of the astronomer. A railway train traveling night and day at the rate of 60 miles an hour would reach the moon in 6 months. The moon, as it were, is our own particular possession. It illuminates our nights. It raises the tides in our oceans. It revolves around our world. It is the nearest of the celestial bodies, the only one whose distance is to be measured in thousands of miles. As has been remarked, it is a detached continent, and as we shall see later, this is probably true in more senses than one. As a result of its proximity, we know more of the moon than of any other celestial body. Indeed, we know its geography, or rather, selenography better than we know that of the Earth. We are close enough to the moon to see its surface spread out before us in a bird's-eye view. By trigonometrical measurements, we can measure the heights of the lunar mountains. We have seen the poles of the moon. This, however, only applies to one hemisphere of the moon. The other side has never been seen by human eye. The explanation is that the moon, instead of turning on its axis in 24 hours like the Earth, requires for its rotation on its axis the exact period of its revolution. Thus, the moon always turns the same face to the Earth, owing, however, to the fact that the moon's velocity in its orbit varies, the orbit being slightly elliptical, while the rate of rotation remains the same. We sometimes catch a glimpse of the other hemisphere. This is known as the libration of the moon. So far, the moon has been viewed as an object and as a satellite of the Earth. It must now be considered as a world. When we look at the moon, even casually, we cannot but notice that the bright disk is diversified. Most people see in the full moon a likeness to a human face, and this is called the man in the moon. Even in the crescent moon and half moon, it is obvious that there are dark markings. In early times, no one knew what these markings signified. Some of the ancients thought that the moon was a great mirror in which we saw the Earth's markings reflected, while others held the correct view, namely, that the diverse markings represented the actual configuration of the moon's surface. Soon after the invention of the telescope, Galileo turned his little instrument on the moon. He was thus enabled to show that our satellite was diversified by mountains and valleys, and great grey stretches which he believed to be seas. Later astronomers, following in this belief, gave these grey stretches names. Thus we have on the moon the Mare Serenitatis, Sea of Serenity, the Mare Tranquillitatis, the Sea of Tranquility, etc. It was obvious as astronomical research progressed that these stretches were not seas, but great plains. It is now known that there are no seas on the moon, but the old names are retained for convenience. It is quite possible that these plains are ocean beds from which the water has long since disappeared. Like the Earth, the moon is diversified by all kinds of formations. There are mountain ridges, isolated mountains, and volcanic craters. The mountain ranges have been called after the mountains on the Earth. Thus there are on the moon the Alps, the Apennines, and the Carpathians. The highest mountains on its surface, so far as known, are the Dörfel and Leibnitz mountains, about 25,264 feet high. As Flammarion remarks, quote, "Relatively to its proportions, the satellite is much more mountainous than the planet, and the mountainous giants are much more numerous than here. If we have peaks like the highest of the Himalayas and of the whole Earth, whose elevation of 29,000 feet is equivalent to 1,140th the diameter of our globe, there are peaks on the moon of 25,264 feet, those of Dörfel and Leibnitz, the height of which is equivalent to 1/470th of the lunar diameter. It will thus be seen that the peaks of the moon are much higher in proportion to its size than those of our own world. The surface, too, is much more rugged and mountainous than that of the Earth. There has been much volcanic activity on the Earth, but there has been much more on the moon. Indeed, on it the volcanic crater is the commonest type of formation. The smallest telescope will reveal the largest of these wonderful formations. The craters are named after eminent astronomers, men of science, and philosophers, and among the more prominent are Tycho, Copernicus, Plato, and Archimedes. Some of these craters are enormous. A large type of formations somewhat similar to the craters are the walled plains. Some of these are actually 150 miles across, and they are, as their name implies, encircled by ramparts of considerable breadth, which in some cases rise to a height of about 12,000 feet above the enclosed plains. In some cases, too, the floors of these walled plains are diversified by the presence of minute craters and mountains. Another curious formation peculiar to the moon is that known as the rills. Of these rills, the late Mr. Elgar, a well-known English observer of the moon, writes, quote, "They often extend for hundreds of miles in approximately straight lines over portions of the moon's surface, frequently traversing in their course ridges, craters, and even more formidable obstacles, without any apparent check or interruption. Their length ranges from 10 or 12 to 300 miles or more, their breadth from less than half a mile to more than 2, and their depth from 100 to 400 yards." End quote. On the Earth we have nothing like them, great yawning chasms running for miles over craters, mountains, and plains. The study of the moon's surface is now a distinct branch of astronomy. To it many distinguished astronomers, such as Mädler and Schmidt, have given the best part of their lives. Schmidt, a notable German astronomer, commenced his observations of the moon with a view to constructing a chart at the age of 14. He just lived to finish his great work about 40 years later. In recent years, photography has been largely used in the study of the moon, and in the able hands of Professor W. H. Pickering of Harvard, USA, much has been learned in this way concerning the lunar surface. To the casual observer, the first quarter is the most satisfactory phase. The full moon is a disappointing object in the telescope. The sun is shining directly on its surface. It is noon on the part of our satellite which we are observing, and the mountains and crater walls cast no shadows, just as on our own world the shadows are shortest at noon. At the first quarter, on the other hand, it is positively fascinating to watch the dividing line between light and darkness, the terminator, as it is called in astronomical language, and to note the sunrise on the various mountain peaks. It is about the time of the first quarter that we see the surface of the moon at its best. It is at this time that the moon is most useful to the astronomer, just as the full phase is the most useful to the ordinary inhabitant of the earth. We have briefly described the surface of the moon, its great plains, its mountains, its craters and rills. What do we learn from a study of these features? Is our satellite a world like the earth? It is not a world like the earth. The first great difference is obvious to the most casual observer. The moon's surface is always to be seen clearly defined without a trace of haziness. There is no atmosphere. Practically, it is an airless globe. Could we see the earth from some point in space, we should sometimes see it clearly defined when the atmosphere was clear, but at times we should see it enshrouded in cloud. But we never see clouds on the moon. It is airless. Not only is there no air, there is no water. The moon's surface is to all intents and purposes changeless, airless, and lifeless. Without air there can be no water, without water, no life. There is no vegetation on the grey plains, no heathery moors, no pine-covered mountains, merely a succession of arid, it may be crumbling, rocks. As Professor W. H. Pickering has pointed out, there is probably a certain amount of change, almost imperceptible. At the bottoms of the craters there seem to be some last relics of the moon's atmosphere, and perhaps the remnants of a lunar vegetation, perhaps a feeble little eruption almost unnoticeable, but that is all. The moon is a dead world, and it is exceedingly unlikely, indeed we may say it is impossible, that any but the very lowest forms of fungus life could live on it for 1 hour. The want of air, as already said, means want of water. It also means violent change of temperature. The moon's day is equal to 29.5 of our days in length. For half of the period the sun beats down on the surface of the moon. There's nothing to temper the broiling heat. The surface is scorched and baked. Then the sun sets and the long night comes on. There is no air to retain the heat. It escapes into space, and the lunar surface is frozen by an intense cold, a cold more terrible than we can conceive. Could we visit the moon, what an extraordinary world we should find it to be. There's no atmosphere, and as a consequence of this the stars are visible in all their glory when the sun is shining. On Earth, the stars are invisible in the daytime, because the sunbeams are dispersed in our atmosphere, and this veil of sunbeams hides the stars from view. But on the moon there is no veil of sunbeams. The sun is seen with all his appendages, which on earth are invisible except during total eclipses, his red flames and his corona. Slowly, very slowly, the sun creeps across the black sky until in 14 earthly days he sinks below the horizon to illuminate the opposite hemisphere. From the side of the moon facing earthwards, there is seen hanging, fixed and motionless in the sky, an enormous orb, a gigantic moon shedding its rays continually on the surface of our satellite. Sun and stars may pass behind it, but this orb hangs fixed in its place in the heavens. This body, which appears from 13 to 14 times as large as the moon seems to us, is our dwelling place, the earth. The magnificence of the earthlight, which our world sheds on the surface of the moon, is difficult to imagine. From the moon's surface, our world is to be seen in all its aspects: blue skies, clouded skies, haze and mist. Sometimes it is full earth, sometimes new earth, sometimes the quarters continually spinning on its axis and exhibiting every part of its surface in turn. Of the power of this reflected light we may get an idea from a consideration of a common phenomenon seen from the earth. Most people have seen the old moon in the new moon's arms. The crescent moon, completed by a darker portion which shines with a dull light. This is the portion of our satellite illuminated by earthshine and reflecting back to us the light of our own planet. Thus we see the light of our own world reflected back to us from the heavens. The chief features of the silver orb of night have been described. It has been seen to be a globe, similar in some respects to the earth, but vastly different in its physical condition, a globe uninhabited and uninhabitable, a succession of rugged, jagged rocks, great grey barren plains and volcanic regions. We have now completed our survey of the earth's vicinity and have passed the first signpost on a journey through the depths of space. End of section 3, read by Czandra, Muskoka 2022.
Chapter 4 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista, Zaleski. The Romance of Modern Astronomy by Hector Macpherson. Chapter 4. The Fountain of Light. Schiaparelli has called the sun the most magnificent work of the Almighty, and so far as our world is concerned, the orb of day certainly merits the title. Without the sun, life on the earth would be impossible. Without the sun, indeed, there would be no earth. Yet so accustomed are earth's inhabitants to the day star, that day after day we experience light and heat. Year after year we enjoy the summer season and do not stop to consider the source of these marvels. It is well to remember, occasionally at least, that the sun is all in all to our planet. There are many marvels in connection with the sun, but perhaps nothing is more astounding than its vast distance and enormous size. The distance of the sun from the earth, as ascertained by methods similar to those used to measure the distance of the moon, mentioned in the previous chapter, is, roughly speaking, 93 millions of miles. The Earth's orbit is not exactly circular, it is slightly elliptical, and as a result, the Sun's distance varies from 91 to 94 millions of miles. It is easy to write out the figures representing 93 millions of miles, 93 followed by 6 zeros. But it is not so easy to realize the enormous distance which these figures represent. Sir Robert Ball has given an excellent illustration as follows. How long will the clock have to tick before it has made as many ticks as there are miles between the Earth and the Sun? Every minute the clock, of course, makes 60 ticks, and in 24 hours the total number will reach 86,400. By dividing this into 93 million, you will find that more than 1,076 days, or nearly 3 years, will be required for the clock to perform the task. There is another vivid way of illustrating the Sun's distance. A tour around the world, involving a journey of 24,000 miles, can be accomplished in 60 days. Before a traveler could cover 93 million miles, he would require to accomplish about 4,000 of these journeys. He would be 600 years old when he arrived, even supposing him to start on his journey as an infant. Take another illustration. If it were possible to travel to the sun in a railway train, night and day without stopping, at the uniform rate of 40 miles an hour, it would require no less than 265 years to reach its destination. If the train had started in the time of Cromwell, it would not yet have reached its destination. No less astounding than the sun's distance is its size. The diameter of the solar globe is 866,000 miles. No fewer than 109 globes of the size of the Earth would be necessary to stretch from the one side of the sun to the other. Properly to estimate its size in comparison with that of the Earth, we must consider its volume. The volume of the sun is 1¼ millions of times greater than the volume of Earth. If all the planets, satellites, and cometary and meteoric bodies in the solar system were rolled into one globe, it would take no fewer than 750 of such globes to equal the volume of the sun. Professor Gregory gives the following unique illustration of the sun's size. If we had a contract to build up this stupendous bulk, and were to deliver a load of the same size as the Earth every hour, the order could be completed working day and night for 150 years. We have seen by how much the sun exceeds the Earth in volume. In weight, however, the sun exceeds our world only 330,000 times. This proves that the density of our world is about 4 times that of the sun. The reason of this is that while our world is a solid globe, the sun, as we all know, is a great ball of gas, incandescent, glowing with an inconceivable heat. We all feel that the sun is very hot. Even on our planet, it sometimes shines so brightly as to make us uncomfortable. What, then, must be its actual heat, if it can be oppressive at a distance of 93 million miles? Perhaps the best illustration on this point was given by Professor Young, the well-known American astronomer. If we could build up a solid column of ice from the Earth to the sun, 2 miles and a quarter in diameter, spanning the inconceivable abyss of 93 million miles, and if the sun should concentrate his power upon it, it would dissolve and melt, not in an hour, not in a minute, but in a single second. 1 swing of the pendulum and it would be water. 7 more and it would be dissipated in vapor. The estimated temperature of the solar surface is no less than 18,000 degrees Fahrenheit. The heat emitted by the sun in each second, according to one of the most distinguished of modern astronomers, is equal to that which would result from the combustion of 11 quadrillions, 600,000 millions of tons of coal burning at the same time. This does not help us to realize the heat of the sun. It helps us rather to realize how far the whole subject transcends our comprehension. How is this enormous heat maintained? It has been calculated that if the sun were composed of coal, it would burn out in 6,000 years. But the orb of day has lasted much longer, and seems to be in its prime. The most probable explanation of the source of the sun's heat is that the solar globe is contracting. This contraction generates heat, which, it has been calculated, will keep the sun at a high temperature for 10 million years. It is also possible that the element radium may have something to do with the maintenance of solar heat. But here we are in the region of speculation. Equally astounding is the brightness of the sun. The intensity of sunlight, as it is called, at the surface has been estimated at 190,000 times that of a candle flame, 146 times that of a calcium light, and 3 2/5 that of an electric arc. Then, in regard to the brightness of the sun, it is estimated that the total light is equal to 1,575 quintillion millions of wax candles. This unthinkable row of figures can assist us in realizing, as it were, the incomprehensibleness of the brilliance of the day star. In reference to the light and heat of the sun, it is well to bear in mind that the Earth and its inhabitants receive only a very small portion. It has been calculated that if the sun were expending, instead of energy, money at a rate of 18 billion pounds a year, the Earth's annuity would be only 9 pounds. Owing to the dazzling brightness of the sun, it is impossible to observe it in a telescope without the aid of a dark glass. When we first observe the sun through a telescope, we behold a disk of yellow light. If we scan the disk carefully, we shall, in all probability, notice 1 or 2 minute markings. These are the sunspots. These spots are not permanent features of the sun, like the mountains and craters of the moon. They are merely temporary markings. Sometimes, indeed, they disappear in a day. An astronomer looks at a sunspot carefully one day and makes a drawing of it. Next day he looks for it again and finds that it has vanished or completely changed its form. Now, what are these sunspots? They were a mystery to the early astronomers who first discovered them, Galileo and Stiner. Indeed, the discovery of these spots came on the men of science of the day with a shock of surprise. It was thought that the sun was too pure to have defects on its surface, and accordingly the astronomers who first announced that they had seen spots on the sun were openly disbelieved. However, the spots were soon proved beyond all doubt to be really features of the disk of the sun. Observation with moderate-sized telescopes, and even with small instruments, reveals a very remarkable fact concerning these spots. They are rents in the glowing atmosphere of the sun. Another remarkable fact concerning sunspots is that they are not uniformly dark. The black central portion, the umbra as it is called, is surrounded by a gray portion, the penumbra. These are supposed to be not really black and gray, but merely dark in comparison with the brilliant envelope of the sun, the photosphere or light sphere as it is called. Spots are supposed to be vast cavities in the glowing envelope. They vary greatly as to size. Sometimes a spot is so large as to be visible to the unaided eye. One famous spot was seen in February 1892. Its length was no less than 92,000 miles, and its breadth was 62,000 miles. A number of small spots were connected with the large one, and the length of the group was 162,000 miles, the breadth being 75,000 miles. The spot group had an area of 3,500 million square miles. 70 bodies equal in size to the Earth would have been required to cover up this gap in the photosphere. Most spots, however, are by no means so gigantic as was this particular example. Sunspots reveal to astronomers many important facts. They show that the sun, like the Earth, rotates on its axis. By observations of the displacements of many spots, astronomers have found that the rotation of the sun is performed in 25 days at the equator and 27.5 days at 45 degrees north and south of the equator. That is to say, the sun does not rotate as a whole. Different parts have different periods. The day of the sun, therefore, is over 25 times longer than that of our planet. Another remarkable fact which sunspots reveal concerns their own distribution. At some seasons, spots are much more numerous than at others, and it has been ascertained that they increase and decrease in about every 11 years. Thus, 1889 and 1901 were years of few sunspots, while 1893 and 1905 were years of many spots. The history of the discovery of the solar cycle, as this increase and decrease is called, is one of the most interesting in the annals of astronomy. In 1826, a German apothecary named Schwab, who was interested in the study of astronomy, commenced to count the number of spots on the sun from day to day. His only instrument was a small hand telescope. After about 20 years, he found traces of the increase and decrease, and by 1851 had fully proved the existence of the sunspot period. Here was a discovery which had escaped all the great astronomers and fell to be made by an amateur. Besides the spots, the telescope reveals the existence of bright ridges which are known as faculae. These are usually observed close to the spots. Like them, they are far from being permanent features. Even in a few hours they utterly change their shape, and in some cases it is impossible to sketch their form, so quickly do they alter and disappear. Although they are closely connected with the spots, there is one remarkable difference. Spots are usually confined to two zones above and below the solar equator, while faculae are found in every latitude except in the polar regions. It is important to remember that the greater part of our knowledge of the sun has been derived from observations not with the telescope alone, but with the telescope aided by an instrument even more remarkable. This instrument is called the spectroscope, and in order to understand properly many of the latest and most wonderful discoveries in astronomy, it is necessary to have some idea of the principle of this instrument. Put briefly, it may be said that while the telescope reveals the celestial bodies, the spectroscope tells us the materials of which they are composed. Just as water can be broken up into its elements, oxygen and hydrogen, sunlight can be broken up into its primary colors, red, orange, yellow, green, blue, indigo, and violet. This can be done by passing sunlight through a prism of glass, and the strip of rainbow-colored light which results is called the solar spectrum. In fact, the rainbow is merely the solar spectrum produced naturally by what is known as refraction, the bending or deflection of the rays of the sun. The solar spectrum was first investigated by Sir Isaac Newton, but it was not until the year 1814 that Fraunhofer, a German astronomer, noticed in the spectrum a number of dark lines. He detected about 300 or 400 of these, and named the more prominent by the letters of the alphabet, from A in the red to H in the violet. He was greatly perplexed at first over the meaning of the lines. He found that they were conspicuous in the spectra shown by the moon and planets, but not in the spectra of all the stars. In other words, the lines were found to be characteristic of sunlight, whether direct or reflected, and sunlight only. It is possible, however, to analyze other kinds of light besides sunlight. In a physical laboratory, the lights of heated elements may be observed with the spectroscope, an elaborated form of the ordinary prism, and when each element is thus analyzed, it is found to be characterized by one or more bright lines. In 1859, Kirchhoff, a German scientist, showed that while a gaseous substance gives a spectrum of bright lines, a luminous solid or liquid gives a continuous spectrum. In the words of a lucid astronomical writer, substances of every kind are opaque to the precise rays which they emit. That is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. This was the solution of the problem. All the astronomers had to do was to examine the spectra of heated elements and fix the position of the bright lines in these spectra, and afterwards compare the position of these lines with the position of the dark lines in the spectrum of the Sun. As the positions were in many cases identical, it became possible to ascertain of what substances the Sun was composed, and Kirchhoff was enabled to detect the presence in the orb of day of such well-known elements as sodium, iron, copper, zinc, and magnesium. One of the uses of the spectroscope is to determine the elements of the Sun, but it has other uses. It has disclosed to astronomers the existence of another atmosphere. In the chapter on eclipses of the Sun, mention will be made of two solar features which are then seen to full advantage. These are the red flames, or prominences, and the corona, a halo of silvery light. We do not see these features of the Sun every day, because they are obscured by its dazzling luminosity. When, however, the dark globe of the Moon interposes and cuts off the light of the photosphere, they are visible. By means of the spectroscope, it is possible, however, to observe the prominences daily, and consequently our knowledge of these marvelous objects has greatly increased since the application to them of this instrument. They have been ascertained to be tongues of glowing hydrogen shot forth with tremendous power from the chromosphere, a thin layer surrounding the photosphere. Some of these prominences are enormous in height. An extraordinary outburst was witnessed on September 7, 1871, by the late Professor Young, one of the foremost solar observers. At noon, he was examining a prominence by the spectroscope method. It had remained unchanged since noon of the day previously. A long, low, quiet-looking cloud, not very dense or brilliant, or in any way remarkable except for its size. At 12:30 a.m., the professor left the spectroscope for a short time, and on returning half an hour later to his observations, he was astonished to find the gigantic sun flame shattered to pieces. The solar atmosphere was filled with flying debris, and some of these portions reached a height of 100,000 miles above the solar surface. Moving with a velocity which, even at the distance of 93 million miles, was almost perceptible to the eye, these fragments doubled their height in 10 minutes. On January 30, 1885, another distinguished solar observer, the late Professor Ticini of Rome, observed one of the greatest prominences ever seen by man. Its height was no less than 142,000 miles, 18 times the diameter of the Earth. Another mighty flame was so vast that supposing the 8 large planets of the solar system ranged one on top of the other, the prominence would still tower above them. Like the spots, the prominences increase and decrease every 11 years. The law, which governs the number and distribution of the spots, also governs the prominences. This 11-year period governs more than prominences and spots. It also governs the shape of the corona, a silvery radiance which envelops the Sun outside of the chromosphere. The entire Sun is governed by this period, which as a result influences the other bodies of the solar system. Take the magnetic variations on the Earth. These magnetic variations indicate a period of almost 11 years. Not only the periods agree, but a great outburst of spots and prominences on the Sun is usually answered by a magnetic outbreak on the Earth. In February 1892, a large group of sunspots appeared, and the result was great disturbances of the delicate magnetic needles kept at Greenwich and elsewhere. In February 1907, another great group appeared. It was followed by a magnificent display of the aurora borealis, or northern lights, an electrical phenomena which is caused by electrical discharges in the upper regions of the Earth's atmosphere. As Professor Gregory remarks, magnetic storms are generally accompanied by auroral displays, and vice versa. What is more, the frequency of auroras keeps time with the frequency of sunspots, and therefore with the intensity and magnitude of magnetic variations. In a word, the Sun is the pulse of the solar system, from which all influences run outward. We may now briefly review what is known of the constitution of the Sun. The central portion of the mighty orb below the photosphere has never been seen. In the words of an able writer, "Of the heat in the Sun's interior we can form no conception. The pressure within the Sun is equally inconceivable. A cannonball weighing 100 pounds on Earth would weigh 2,700 on the Sun. Thus a mighty conflict goes on unceasingly between imprisoned and expanding gases and vapors struggling to burst out, and massive pressures holding them down. The first solar envelope is the photosphere, that bright, calm-looking solar surface on which the spots appear, and from which we derive our light. Above this are envelopes technically known as the reversing layer and the chromosphere. This latter envelope, from which the prominences emanate, may be described as a sea of fire, in a state of everlasting turmoil and unthinkable heat. Like the sea, it is restless and agitated, but its waves are waves of glowing hydrogen, and its spray fragments of shattered sun flames. Beyond the chromosphere is the corona, a soft silvery radiance, which can only be seen when the Sun is totally eclipsed. The corona has long proved a problem to astronomers. Its shape varies in sympathy with the 11-year period, and it seems closely connected with electricity and magnetism. It streams out from the Sun for millions of miles, becoming more and more rarefied, until it gradually fades into the ether of space. It is the final solar envelope, calm and peaceful, a fitting crown for the orb of day. This then is the Sun, ruler and center of the solar system, to which we on Earth owe our light, heat, life. We cannot hope to realize fully the marvels of this mighty orb, or properly to appreciate the delicate mechanism, the marvelous contrivances which keep the grand central orb in touch with the little planets which circle round it. Without the Sun, not only would life on this planet be impossible, but our planet itself would not be in existence. In view of all this, we can fully appreciate the remark of Proctor: "If there is any object which men can properly take as an emblem of the power and goodness of Almighty God, it is the Sun." End of Chapter 4.
Chapter 5 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 5. The Sun's Family of Worlds. A study of the globe of the Sun itself gives us an inadequate idea of the solar power. We cannot realize the extent of the Sun's influence until we comprehend the marvelous system of planets and satellites, asteroids, comets, and meteors which revolve round it. The Sun, as has been well said, maintains in his rays the whole of his system. If the comparison were not offensive to the sun god, we might say that he is like a spider at the center of his web. In the net of his attraction, the worlds are sustained. Relatively to his magnitude and might, the planets are but toys spinning round him. The planets are divided into 3 well-defined groups. Comparatively close to the orb of day, at mean distances ranging from 36 to 141 millions of miles, revolve the inner planets, consisting of 4 worlds: Mercury, Venus, the Earth, and Mars. Beyond the orbit of Mars, we have another group, or rather ring, of 700 small worlds, the asteroids, planetoids, or minor planets. The largest of these is only 500 miles in diameter. Beyond this, at mean distances ranging from 482 to 2,789 millions of miles, we have the group known as the outer planets: Jupiter, Saturn, Uranus, and Neptune. Mere figures convey little or no idea of the relative distances of the planets. We may, however, represent the sizes and distances of the planets in imagination on a much smaller scale. If we take a 9-foot globe to represent the Sun, we may represent Mercury by a large P at a distance of 127 yards, Venus by a 1-inch ball at 235 yards, the Earth by a 1-inch ball at 325 yards, Mars by a 1/2-inch marble at 495 yards, the asteroids by 700 small seeds at distances of from 676 to 1,385 yards. Jupiter will be represented by an 11-inch globe a mile away, Saturn by a 9-inch globe 1 3/4 miles away, Uranus by a 4-inch globe 5.5 miles away. On this same scale, we can represent the Moon as a pea moving in a circle at a distance of 30 inches from the ball, 1 inch in diameter, which represents the Earth. The actual diameters of the planets may be tabulated as follows. Inner planets: Mercury, 3,030 miles, Venus, 7,700 miles, the Earth, 7,918 miles, Mars, 4,230 miles. The asteroids, from 500 to 10 miles. Outer planets: Jupiter, 92,164 miles, Saturn, 74,000 miles, Uranus, 31,000 miles, Neptune, 34,000 miles. From this table, we see that the outer planets greatly exceed in size the inner planets, which in their turn dwarf to complete insignificance the asteroids or minor planets. The three groups, in fact, are completely different in distance, size, and physical condition. Besides the planets, another class of bodies fall to be mentioned. The planets themselves, which revolve directly round the Sun, are called primary planets. But most of the planets are themselves centers of little families of moons or satellites which revolve round them and are carried along with them round the Sun. These are called secondary planets, or more usually, satellites. Mercury and Venus have no satellites, and only 2 of the inner planets are attended by moons. We all know the Moon, the Earth's sole satellite world. Mars has 2 satellites, but they are very much smaller than the Moon. The asteroids, of course, have no satellites because they are much smaller than satellites themselves. But the outer planets have imposing retinues of attendants. Jupiter boasts of no fewer than 8, 4 large and 4 small. Saturn is attended by 10 worlds, and in addition has a ring of meteoric particles somewhat analogous to the zone of asteroids moving round the Sun. Uranus has 4 satellites, and Neptune, so far as we know at present, 1. These satellites vary greatly in size, from Titan, one of the satellites of Saturn, which exceeds the planet Mercury in size, to the little satellites of Mars, which are certainly under 30 miles in diameter. The orbits or pathways of the various planets round the Sun lie almost in the same plane or level, with the exception of the orbits of some of the asteroids. Along these orbits, the planets travel with different velocities. Mercury, 29 miles per second, Venus, 21 miles per second, the Earth, 18 miles per second, Mars, 15 miles per second, Jupiter, 8 miles per second, Saturn, 6 miles per second, Uranus, 4 miles per second, Neptune, 3 miles per second. Mercury, the nearest planet to the Sun, is subjected most to the Sun's attraction and consequently travels fastest. Its velocity is 29 miles per second, or 2,505,000 miles per day. Venus travels at over 21 miles per second, or 1,873,000 miles per day. The velocity of our own planet is 18 miles per second, or 1,555,000 miles per day. Mars travels at almost 15 miles per second, which is equivalent to 1,287,000 miles a day. The outer planets are more leisurely. Jupiter glides along at 8 miles a second, or 771,000 miles a day. Saturn's velocity is over 6 miles per second, which is equivalent to 536,000 miles a day. Uranus travels at a little over 4 miles a second, and in one day covers 372,000 miles, while Neptune, the most distant known world, moves at the comparatively slow pace of 3 miles a second, or 268,000 miles a day. Comparatively slow in comparison with the other planets, but absolutely very fast, Neptune rushes along in its orbit with an almost inconceivable velocity. And if Neptune's speed is so great that it cannot be realized, it is almost impossible to conceive that our world, which seems to us so still and immovable, carries us along with it in its journey through space at the rate of 18 miles per second, and Mercury at 29 miles per second. The following words of Flammarion bring out this clearly. A ball fired from a cannon leaves the mouth with a velocity of 1,312 feet per second. The terrestrial globe flies 75 times quicker, Mercury 117 times faster. This is a rapidity so stupendous that if two planets were to meet in their course, the shock would be frightful. Not only would they be shattered in pieces, both reduced to powder, but further, their motion being transformed into heat, they would be suddenly raised to such a degree of temperature that they would disappear in vapor. Everything, earth, stones, water, plants, inhabitants, and they would form an immense nebula. Fortunately, we need have no apprehension of such a disaster. The planets are all moving in the same direction, and they are at enormous distances from one another. When Mars and the Earth are at their nearest approach, over 30 millions of miles separate them, while Venus, the nearest of all the large planets, is distant from us at its times of closest approach over 20 millions of miles. As a result of these different speeds and different distances from the central orb of the various planets, the various bodies of the solar system require different times to perform their revolution round the Sun. Not only is Mercury closer to the Sun than is our own planet, and has therefore a smaller ellipse to traverse, it goes much more rapidly round its orbit, and therefore requires a much shorter period to perform a complete revolution. The times of revolution of the various planets round the Sun may be tabulated thus. Mercury, 88 days, Venus, 225 days, the Earth, 365 days, Mars, 687 days, Jupiter, 4,332 days, almost 12 years, Saturn, 10,759 days, almost 30 years, Uranus, 30,687 days, about 84 years, Neptune, 60,127 days, about 165 years. Just as the Earth's year is its period of revolution round the Sun, the year of Mercury is only 88 days, while that of Neptune is 60,127 of our terrestrial days, or almost 165 of our own terrestrial years. Thus, a being who had lived only 24 terrestrial years would be a centenarian on Mercury, while a man of 84 on our planet would be an infant of 1 year according to the length of years on the planet Uranus. In the solar system, therefore, measurement of time is relative and depends on the distances of the various planets from the Sun. As the different planets vary in distance, velocity, and size, they also differ in weight. Professor Gregory gives the weight of the Earth as 6,000 millions of tons. If we represent this by 1 pound, the weight of the Sun would be 150 tons. The weight of Jupiter would be 310 pounds, of Saturn 93 pounds, of Neptune 17 pounds, and of Uranus 14 pounds. The smaller planets, however, would be on the same scale, lighter than the Earth. Venus would weigh 13 ounces, Mars 1.5 ounces, Mercury 1 ounce, and the Moon about 3 drams. Although the outer planets are much heavier than the Earth, they are not so much heavier as they are larger, which shows that their density is less than that of the Earth. On the Earth, a falling body during the first second of its descent falls through 16 feet. The following are the distances through which a similar body would fall on the other bodies of the solar system in the same time. Earth, 16 feet, Moon, 2.6 feet, Mercury, 6.9 feet, Venus, 13.1 feet, Mars, 6.1 feet, Jupiter, 42.4 feet, Saturn, 18.9 feet, Uranus, 10.8 feet, Neptune, 14.2 feet. On the same scale, the distance fallen on the Sun is too large to be shown, 442.4 feet. The weight of the body at the Earth's surface is the force with which the Earth attracts that body and depends on the mass of the Earth. Therefore, as the planets have different masses, a body of weight on the different planets would have different weights. Take the case of a man who weighs 12 stones on the Earth. On the Sun, he would weigh 2 tons. As Sir Robert Ball puts it, if a man were to be transferred to a globe as massive as the Sun, everything would weigh 27 times as much as it does on the Earth. To pull out your watch would be to hoist a weight of about 5 or 6 pounds out of your pocket. Indeed, I do not see how you could draw out your watch, for even to raise your arm would be impossible. It would feel heavier by far than if it were made of solid lead. It is, perhaps, conceivable that you might stand upright for a moment, particularly if you had a wall to lean up against. But of this I feel certain that if you once got down to the ground, it would be utterly out of your power to rise again. Thus, a man living on such a globe would be unable to rise out of his bed in the morning. A man weighing 12 stone on our world would weigh 28 stone on Jupiter, 14 stone on Saturn, 10 stone on Neptune, Uranus, and Venus. On Mars and Mercury, the weight would be reduced to 5 stone, on the Moon to 2, while on the asteroids it would come down to a few ounces. Let us suppose a man of 12 stone placed on the Moon. He would be amazed to find everything 1/6 as heavy as on the Earth. His own weight would be so diminished that he could jump over a house with as little effort as he could on Earth leap across a wayside ditch. Pulling out his watch, he would feel practically no weight at all. A horseman who on Earth would consider a 5-barred gate a good jump would on the Moon leap over a hayrick with the same amount of exertion. Suppose a man were playing cricket on the Moon. On Earth, 100 yards is a very good throw. On the Moon, one of 600 yards would be accomplished with the same amount of exertion. One able astronomer puts this lessened gravity very clearly. Football would show a striking development in lunar play. A good kick would not only send the ball over the crossbar, but it would go soaring over the houses and perhaps drop in the next parish. If our imaginary man of 12 stones weight were transferred to one of the asteroids which circulate between Mars and Jupiter, his weight would be reduced to a few ounces. Suppose he kicked a ball into the air as an ordinary player would do on Earth. It would not, as in the Moon, go soaring over the houses. It would go soaring into space and leave the planet forever. The force of gravity on the little asteroid would not be sufficient to counteract the upward motion of the ball, which would rush into space on a career of its own and become a little asteroid on its own account. These illustrations bring home clearly the different masses of the various planets composing the solar system. For reasons which will be explained later, the planets have different densities. Thus, Mercury is in proportion to its size a very heavy planet. Its density is equal to that of zinc, which means that it weighs the same as a globe of zinc the same size. The weight of our Earth is equal to that of a globe of arsenic the same size. The densities of the other bodies of the solar system vary considerably. That of Venus is equal to iron pyrites, that of Mars to ruby, and that of the Moon to flint glass. The Sun and the 4 large planets, although so much superior to the inner planets in size, have smaller densities. The Sun and Jupiter weigh the same as globes of dry sand the same size, while the densities of Uranus, Neptune, and Saturn are equal to those of amber, boxwood, and walnut wood. The key to the different velocities, densities, and masses of the planets is the marvelous power of gravitation, which was referred to in the opening chapter, and the complete investigation of which we owe to the genius of Newton. Not only the planets and their satellites, but the various comets and the systems of meteoric rings conform to this mighty law, which extends throughout the entire length and breadth of the universe. Gravitation is the marvelous invisible bond everywhere present, operating throughout all space, which keeps the planets in subjection to the Sun, and which maintains order instead of chaos, harmony instead of discordance. Much as astronomers know of the operation of gravitation, of its nature they are entirely ignorant. In contemplating this marvelous force which so far has baffled science, the mind is lifted right into the region of things divine and eternal. In this chapter, we have briefly referred to the system of planets surrounding the Sun. The solar system is not only a system, but a system of systems. For, as we have seen, the various planets with their satellites form subordinate systems within the larger one. To explain the outstanding features of these planets and satellites will be the task of the next few chapters. End of Chapter 5, read by Andrea Kotzer.
Chapter 6 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Read by Krista, Zaleski. The Romance of Modern Astronomy by Hector Macpherson. Chapter 6. Mercury, the Sparkling One. So far as we know, Mercury is the nearest planet to the Sun. The existence of a world at a less distance than Mercury was suspected, and indeed generally believed in, half a century ago. There were certain irregularities in the motion of Mercury which astronomers attributed to the action of an unseen planet. One observer boldly announced that he had seen the planet crossing in front of the Sun, and so the name of Vulcan was bestowed on the supposed world. But Vulcan was never seen again, and accordingly the great majority of astronomers believe that it was never seen. In fact, that no such planet exists. Mercury, therefore, is the nearest known planet to the Sun. Seen from the Earth, the little orb is never far from the day star. Mercury revolves round the Sun in an orbit within that of the Earth, and consequently it is never to be seen on a dark sky in the opposite part of the heavens to the Sun. In Britain, Mercury is rarely visible, so close does it keep to the orb of day. In fact, it is recorded of Copernicus, to whom we owe the true theory of the planetary motions, that although he often looked for the planet, he was never successful in seeing it. The reason of his failure is not far to seek. He lived the greater part of his life near the valley of the Vistula in Poland, where the horizon is rarely free from mists, and Mercury is never very far above the horizon. Notwithstanding the difficulty of seeing it, Mercury has been known from the earliest times. The ancient Greeks were well acquainted with it, and it was sometimes known to them as the Sparkling One. This name was given to it because it does not, like the other planets which rise high in the heavens, shine with a steady light. As we always see it through the more or less misty air about the horizon, it twinkles and sparkles in a beautiful manner, hence the name which the ancient Greeks so poetically conferred on the little planet. As Mercury, owing to its proximity to the Sun, is difficult to observe with the unaided eye, it is also difficult to observe with the telescope. The opportunities of favorable observation are few, so closely does it follow the Sun. The first thing which impresses the telescopic observer of Mercury is that the planet exhibits phases similar to those of the Moon. As the Earth's path encloses the orbits of both Mercury and Venus, we never see these planets fully illuminated. To be fully illuminated, a body must be in the opposite quarter of the heavens from the Sun, like the Moon at the full phase. Sometimes, however, Mercury is at the opposite side of the Sun from our planet. That is to say, we have Mercury, the Sun, and the Earth all in a straight line, with the Sun between the Earth and Mercury. The planet is then at its farthest from the Earth, but could we observe it, we should see it with a fully illuminated disk. In fact, we should have a full Mercury. We do not see the planet at these superior conjunctions, as such occurrences are called, for Mercury is then lost in the glare of the Sun and quite invisible to the terrestrial observer. After a time, however, the planet, in its journey round the orb of day, reappears from the solar glare as an evening star. As it comes nearer and nearer to the Earth, and as its disk becomes apparently larger, the illuminated portion decreases until we have only half Mercury, then a crescent Mercury, until, when the planet is at its nearest, the thin crescent disappears altogether and we soon have new Mercury. Like our satellite at new moon, Mercury becomes invisible. Technically, it is said to be at inferior conjunction, because the Earth, Mercury, and the Sun are in a straight line, with Mercury in the center, the result being that the bright side of the planet is turned towards the Sun and away from the Earth. Then, on its journey round the Sun, Mercury again appears as morning star. Only a little crescent is at first visible in the telescope, but gradually the illuminated portion becomes greater as the planet recedes from the Earth and the apparent diameter decreases. Again we have half Mercury, and again the planet disappears in the rays of the Sun to reappear as an evening star. Thus we are placed at a disadvantage in regard to the observation of Mercury, because the planet revolves round the central orb within the orbit of the Earth. When Mercury is nearest to us, it is invisible. When it is fully illuminated, it is also invisible. We only see it bit by bit, as it were, at its various phases. Above all, it is so near the Sun that astronomers are never able to observe it on a dark background, and it is so low in the heavens that it is always seen through a stratum of thick air. For many years, nothing was known of the surface of Mercury. At the beginning of the 19th century, however, a series of observations were made by Schroeder, an able German astronomer of the day. Schroeder was anxious to ascertain the period of Mercury's rotation on its axis, the length of the planet's day. Schroeder detected certain markings, and from the motions of those, he concluded that the rotation of Mercury was performed in about 24 hours, similar to our own terrestrial day. For many years this estimate was generally accepted, although owing to the great difficulty of observing the planet, it was not implicitly relied on. Some distinguished astronomers, however, were not content with a mere unconfirmed estimate of the length of Mercury's day. Among these was Schiaparelli of Milan, who in 1882 commenced a prolonged series of observations of the planet for the purpose of determining the rotation period. Previous observers had been handicapped by the fact that Mercury, when visible as an evening or morning star, is to be seen for only a short period. Therefore, prolonged observations of the planet are impossible under such conditions. Schiaparelli struck out a new line. Instead of observing Mercury at the usual time, he followed it by day, considering that the disadvantage of observing the planet in the daytime was more than compensated by the advantage of prolonged observation. He followed the planet for hours at a time, and at last, after 7 years' observations, he announced his discoveries. They were as startling as they were unexpected. He found that so far from the planet rotating on its axis in 24 hours, the markings visible remained fixed in position, and that the planet performs only one rotation on its axis during its revolution round the Sun. Instead of rotating in 24 hours, as the Earth does, it rotates in 88 of our terrestrial days. Controversy raged for some years among astronomers as to the accuracy of this result, but now the truth of Schiaparelli's discovery is generally accepted. Let us try to imagine what sort of a world Mercury must be. Rotating on its axis only once during its journey round the orb of day, it turns the same face to the Sun, just as the Moon does to Earth. One face of the planet is bathed in perpetual sunshine, the other is shrouded in everlasting night. One side is baked with heat, the other is frozen with cold. No wonder that the surface, as the observations of Professor Lowell indicate, is cracked in all directions. The surface of Mercury, he says, is colorless, a geography in black and white. However, there is a small zone on the planet's surface on which the Sun does not rise and set. Owing to the irregular motion of the planet in its path, its varying velocity due to the eccentricity of its orbit, and its uniform motion on its axis. This is clearly explained by Mr. Gore in the following words. This difference in the regularity of the two motions will of course give rise to a libration, which will have the effect of bringing a portion of the dark side of Mercury periodically into the sunlight, and will thus diminish the area of the planet's surface which is shrouded in perpetual night. About 3/8 of the total surface will forever remain in darkness, 3/8 in perpetual sunshine, while the remaining 1/4 will have alternately day and night. In fact, an inhabitant living near the mean bounding line and on the planet's equator would have 44 days of sunshine and 44 days of night and twilight. A little farther in on the dark side there would be perpetual twilight, and farther still eternal night would reign. Owing to the low altitude attained by the Sun near the bounding line, its intense heat and light would of course be much mitigated, so that probably this region of the planet's surface may be comparable with the temperate zones of Earth. Little is known of the markings of Mercury. The few observations which astronomers possess seem to indicate that the surface is rugged and mountainous, somewhat similar to that of the Moon. As to whether there is an appreciable atmospheric envelope surrounding Mercury, opinion is divided, some holding that the globe of Mercury is, like that of our satellite, airless, others believing that there is an atmosphere surrounding the little planet. The general opinion of astronomers is that under such conditions as exist on Mercury, life as we know it is impossible. If there are inhabitants of Mercury, they must, from the dark side of their world, obtain magnificent views of the outer universe. Venus and the Earth will shine with a glorious radiance fully illuminated. The Earth and Moon seen from Mercury form a fine double star. The Earth will appear a magnificent object, attended by a little star of the third magnitude. The brightest object in the evening skies of Mercury will be Venus, as the little planet has no satellite circling round it, illuminating its dark hemisphere. End of Chapter 6.
Chapter 7 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Rolga Smith. The Romance of Modern Astronomy by Hector Macpherson. Chapter 7. The Evening Star. From the earliest ages, the planet Venus has been known to and admired by mankind. No record exists of the recognition of this beautiful planet as distinct from the ordinary stars, for of all the wanderers, Venus, as the brightest, would probably be the first to be detected. Homer refers to the star as the, quote, star of Lucifer, end quote, and one distinguished astronomer holds that under the title of Mazzaroth. It is referred to in the book of Job. Venus is both the evening star and the morning star. That is to say, the phenomena known as evening star and morning star are different appearances of the same orb. The earliest astronomers amongst the Greeks did not know this. The morning star they called Phosphorus, and the evening star Hesperus, and for many years the two were believed to be separate bodies. It was noticed, however, that when the evening star was to be seen in the evening, there was no trace of the morning star on the following morning, and that conversely, when the morning star was visible, it was hopeless to expect to see it at the night at the same period. Pythagoras, the famous Greek thinker, is believed to have been first in identifying the two stars as one, the evening and morning star. Venus, like Mercury, exhibits phases when observed with the telescope. As Venus is so much nearer than Mercury and is a much larger planet, these phases are much more easily observed. To the unaided eye, Venus is but a luminous point, bright enough on rare occasions to cast shadows, but with no definite shape. When, however, we turn even a small telescope on the evening star, a remarkable change is wrought. The beautiful, soft, luminous point is transformed into an exquisite little disk of varying phases. For Venus, in Galileo's phrase, quote, imitates the phases of the moon, end quote. The existence of these phases was affirmed by Copernicus when he propounded the theory of the planetary system. The existence of these phases was a necessary proof of his contention that the planets went round the sun and not round the earth. It was pointed out to Copernicus that no phases of Venus could be seen, and in those days there were no telescopes. God, replied Copernicus to his critics, will cause instruments to be invented to improve the sight, and then you will see them, end quote. Soon after the invention of the telescope, in 1611, Galileo turned his instrument on the evening star, and there, in the field of the telescope, shone an exquisitely beautiful miniature of the moon, going through each of our satellite's phases. As a telescopic object, Venus is indeed beautiful. The observation of the planet is a source of never-ending delight. No one can avoid feeling a thrill of pleasure as he beholds the beautiful evening star, shining out softly in the twilight, with its calm and rich radiance, transformed by the telescope into an ever-changing golden disk, sharply defined in the evening light. The phases of Venus are similar to those of Mercury. At superior conjunction, the disk of the planet is fully illuminated, but it is lost in the rays of the sun. Then the planet emerges from the sunlight as evening star. When it reaches its greatest elongation east, the disk is half illuminated, like the moon at the quarters. As the planet approaches the Earth, the disk increases in size, but the illuminated portion decreases until the planet, a dwindling crescent, is again lost in the rays of the sun at inferior conjunction, and we have new Venus. The planet is at its nearest only some 26 millions of miles from the Earth, but it is invisible. Shortly after this, it reappears as morning star, a thin crescent increasing in size and its apparent diameter decreasing. When it reaches its greatest elongation west, Venus is in its best position for observation as morning star. The disk becomes smaller, more and more of it becoming visible, until it draws close to the sun, once again passes superior conjunction, and emerges from the sunset as evening star. Our knowledge of the configuration of the surface of the planet is very limited for two reasons. In the first place, Venus is, like Mercury, unfortunately placed for observation. It is, of course, easier to observe than Mercury, being much further from the Sun and much larger, but like that orb, it is never seen on a dark day and never observed for a protracted period. In the second place, the planet is so dazzlingly bright that it is very difficult to observe markings on its surface. Venus reflects a greater proportion of light which it receives from the Sun than any other planet. As Mr. G.F. Chambers remarks in his book, The Story of the Solar System, quote, "The reflective power of Venus was probably never more effectively brought under the notice of the human eye than on September 6, 1878, when Nasmyth enjoyed an opportunity of seeing Venus and Mercury side by side for several hours in the same field of view." He speaks of Venus as resembling clear silver and Mercury as nothing better than lead or zinc. Seeing that, owing to its greater proximity to the Sun, the light incident on Mercury must be 3.5 times as strong as the light incident on Venus, it follows that the reflective power of Venus must be very great. End quote. This reflective power has been estimated as equal to that of newly fallen snow. The evening star reflects 70% of the light which falls on it. What is the reason of this remarkable reflective power? The generally accepted explanation is that the planet is surrounded by a very dense and cloud-laden atmosphere, and that the sunlight falls on these clouds. In other words, we rarely catch a glimpse of the surface of Venus. This is fully confirmed by observation of the planet. It is only with the greatest difficulty that the markings can be detected. As in the case of Mercury, the length of the planet's day has been for many years a matter of controversy. Observations made in the 17th century by the famous astronomer Cassini indicated that Venus turned on its axis in a period of about 23 hours. At the same time, however, another astronomer, Bianchini, made observations which suggested a period of 24 days, 8 hours. The German astronomer Streuter tackled the question at the end of the 18th century and confirmed the short period of 23 hours. In 1839, an Italian astronomer, Di Vico, confirmed these observations, and for 50 years the 23-hour period was generally accepted. It was the same distinguished astronomer who showed the probability of the long rotation period of Mercury who made the same discovery in regard to Venus. A series of observations extending over 13 years convinced Schiaparelli that the markings noted by the early observers were not really permanent. As in the case of Mercury, he observed the planet by day and was enabled to follow it for hours at a time. He concentrated his attention on round white spots which remained fixed in position. The obvious conclusion to be drawn from this is that Venus performs only one rotation on its axis in its period of revolution around the Sun, 225 days. One face of the planet is constantly turned to the Sun and in continuous sunlight. The other face is always turned from the Sun and is in everlasting darkness. In the case of Venus, there is not the same amount of liberation as in that of Mercury. The pathway of Venus is much more clearly circular. The variation of velocity is much less than in the case of the smaller planet, so that only a very small part of the surface will enjoy the alternation of night and day, as does a considerable portion of Mercury. Since Schiaparelli announced his results, a number of different observers have made observations to determine the rotation period. The period of 225 days has been abundantly confirmed by observers favored by good climates and clear skies, while astronomers in less favorable climates supported the short period. It may be now taken as very probable, therefore, that Venus rotates on its axis in the same period as it requires to revolve round the Sun. Little is known of the physical condition of the planet owing to the dense atmosphere which surrounds it. Polar caps, supposed by some to be somewhat similar to those on our planet and on Mars, have been observed, or at least suspected, from time to time. Some astronomers, however, do not regard them as snow. The drawings of Schiaparelli represent them as separated by a dark shadow, which suggests that they represent two mighty mountain systems. Evidence of the mountainous condition of Venus was obtained by Streuter as long ago as the beginning of the last century. He noted the southern horn of the planet when in the crescent form to be blunted, and he attributed this to the existence of a great mountain, 5 or 6 times higher than the loftiest peaks on the Earth. Along the terminator, or the dividing line between the light and darkness, he noted irregularities which he considered to be more strongly marked than those on the Moon. These observations have since been only partly confirmed. Still, there seems fairly strong evidence that the surface is rocky and mountainous, although not so mountainous as was believed by Streuter. Trouvelot, a French astronomer, found in 1878 the polar spots distinctly visible. Quote, "Their surface," he wrote, "is irregular and seems like a confused mass of luminous points, separated by comparatively somber intervening spaces. This surface is undoubtedly very broken and resembles that of a mountainous district studded with numerous peaks, or our polar regions with numerous ice needles brilliantly reflecting the sunshine." End quote. These features, then, are either striking enough to be seen through the dense cloud canopy which surrounds Venus, or else they are high enough to project above the dense portions of the atmosphere. Of the existence of the atmosphere, there is no doubt. It has been actually observed when the planet is in transit across the face of the Sun. Spectroscopic observations show that water vapor exists in the atmosphere, which is very dense. Seen from the Earth, this atmosphere seems the very picture of calm and quiescence. But if the long period of rotation indicated by Schiaparelli's observations be correct, it can scarcely be a calm region. As a recent writer puts it, quote, "The atmosphere circulation of Venus must be conducted by a permanent hurricane system. A violent uprush of heated air on the side perpetually exposed to the glare twice as fierce as that of our hottest sun should be compensated for by a furious inrush on both sides of the illuminated hemisphere, like the drought caused by a fire in a cold room." End quote. Venus has no satellite, in this respect resembling Mercury. For many years, nevertheless, a search for a satellite was persecuted with great energy, and it was believed by several astronomers that they have detected a companion world. It was afterwards shown, however, that what they had taken for satellites must have been either optical illusions caused by the glare of the planet in the field of the telescope, or small stars which happened to lie in the same field of view as the planet. Thus, although in size resembling the Earth more than any other world, it differs from our planet in several important respects. Its days, are utterly different from ours, and it has no moon to circle round it and perform the useful offices of satellite world. The question of the habitability of Venus has attracted little attention. Certainly the planet, with its remarkable rotation period and its dense atmosphere, does not seem an inviting abode. On this point, however, astronomers know too little to speak with confidence. Sir Robert Ball inclines to the view that even though Venus does rotate in the way that the majority of astronomers believe, quote, we might expect to find in that planet a luxuriant tropical life of a kind perhaps analogous to life on the Earth, end quote. If there are inhabitants of Venus, and if they ever catch a glimpse of the outer universe, their eyes will be gladdened by a beautiful celestial spectacle, such as we on this planet are not privileged to see. The Earth and Moon combined probably appear more brilliant to Venus than Venus does to us, and the two orbs, the smaller moving round the larger, form a beautiful and imposing double star. End of chapter 7.
Chapter 8 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by raiynn. The Romance of Modern Astronomy by Hector Macpherson. Chapter 8, Mars, the Red Planet. As was shown in the previous chapters, Venus revolves round the Sun in an orbit wholly within that of the Earth, and consequently is not seen by us to full advantage. When nearest, the planet is invisible. It is in a straight line between the Earth and the Sun, and turns its dark hemisphere to our planet. With Mars, the case is entirely different. Mars revolves in an orbit exterior to ours, and when nearest to the Earth is on the other side of our planet from the Sun. The Sun, the Earth, and Mars are in a straight line with the Earth in the middle. If the near approaches of Venus correspond to new moon, those of Mars correspond to full moon. We then see Mars with a full round disk. The planet is said to be in opposition to the Sun, because it is in the opposite quarter of the heavens. It rises at sunset, culminates at midnight, and sets at sunrise. Mars as a celestial spectacle is usually inferior to Venus, but at times its brilliancy becomes extraordinary, and that planet shines with a bright, ruddy light which makes it one of the most striking objects in the heavens. In the words of a famous modern astronomer, once in every 15 years a startling visitant makes his appearance upon our midnight skies. A great red star that rises at sunset through the haze above the eastern horizon, and then, mounting higher with the deepening night, blazes forth against the dark background of space with a splendor that outshines Sirius and rivals the giant Jupiter himself. Startling for its size, the stranger looks the more fateful for being a fiery red. Small wonder that by many folk it is taken for a portent. It is recorded that in 1719, Mars was so brilliant that a panic ensued among the ignorant. Owing to the comparative nearness of Mars to our world, at times about 35 millions of miles, along with its favorable presentation when closest to the Earth, we know more of the surface of Mars than of any other body in the entire universe, with the single exception of the Moon. For over 250 years, Mars has been attentively studied by astronomers. It was observed by Galileo, who, however, discovered nothing important. In 1656, the Dutch astronomer Huygens made the first determination of the length of the Martian day, the period of the planet's rotation on its axis. Unlike Mercury, Mars has a day somewhat similar to our own, the length of which has been known for over 2 centuries. The exact length, to within a fraction of a second, is 24 hours, 37 minutes, 22.65 seconds, only about half an hour longer than the day of our own world. Its year, therefore, which consists of 687 of our days, contains 669 of its own. In another particular, Mars closely resembles the Earth. The inclination of its axis to the plane of its orbit is about 66 degrees. Its seasons, therefore, closely resemble those on the Earth. Another remarkable point of resemblance was noted about 2 centuries ago. In 1719, the French astronomer Mercury discovered 2 white spots on the disk of Mars, one at the North Pole, the other at the South. These spots correspond to the polar regions of our own planet. Like the Earth, Mars has an atmosphere, but it is much thinner than our own. Thinner at least by half, says Professor Lowell, than the air on the summit of the Himalayas. It is very clear and transparent, and it is believed not to differ much from our own in constitution. The following description of this Mars atmosphere is from the pen of the late Miss Agnes Clerke. This slender envelope is exceedingly extensive. In the pure sky, scarcely veiled by it, the sun, diminished to less than half its size at our horizons, probably exhibits its coronal streamers as a regular part of his noontide glory. Atmospheric circulation proceeds so tranquilly as not to trouble the repose of a land, in which it seemeth always afternoon. Huygens and other early astronomers detected various prominent markings, chief among them the well-known features known variously as the Kaiser Sea, the Hourglass Sea, and, in the now prevalent system of nomenclature, the Syrtis Major. It was not, however, until Herschel took up the study of Mars that much was known of its surface. He found that the spots at the poles waxed and waned in accordance with the Martian seasons. That is to say, the north polar cap increased in size during the winter of the northern hemisphere and decreased in summer, while the reverse process took place in the southern hemisphere. He concluded, therefore, that the polar spots were masses of snow and ice, similar to the polar regions of the Earth. After the planet had been attentively studied by Beer and Madler, Dawes, Secchi, and other astronomers, the late Mr. Proctor constructed a map of Mars in 1869 from drawings by Dawes. He gave names to the various features, the red portion of the planet's disk being known as continents, and the green as seas, in accordance with the prevailing views of contemporary astronomers. Along with this, he put forward in other worlds than ours some very fascinating and plausible ideas of the habitability of Mars, which he named a miniature of the Earth, having continents, oceans, snow, rain, clouds, rivers, and probably inhabitants. The researchers of the last 28 years, however, have revolutionized our knowledge of Mars. The close analogy which Proctor perceived has vanished, and Mars is now considered as an emblem of what our world will be in the future rather than as a miniature at present. The most recent observations have changed but not destroyed the analogy. It was in 1877 that the revolution in our views concerning Mars began. In the words of Mr. Percival Lowell, "Our knowledge of the planets, and especially of Mars, has advanced greatly within the last quarter of a century. The first steps of this advance we owe not to instruments, but to the genius of one man, the Italian astronomer Schiaparelli. When in September 1877 the planet reached its opposition, this famous astronomer commenced a trigonometrical survey of the planet's disk. While so employed, he discovered a number of fine dark lines crossing the red areas of the planet. He called them canali, an Italian word meaning canals or channels. In 1879, Professor Schiaparelli again observed the canals, which revealed the same appearance as they had done 2 years previously. Towards the end of the year, he was amazed to find that one of the canals had become double, a new canal running parallel with the original one. Suspecting optical illusions, he changed his telescope and eyepieces, but was soon convinced of the reality of his observations. In 1881, he again saw the canals double and single, and during the unfavorable oppositions of 1884, 1886, and 1888, he went from discovery to discovery. Indeed, he declared in 1888 that the canals had all the distinctness of an engraving on steel with the magical beauty of a colored painting. Considerable skepticism prevailed in scientific circles for a number of years, as other astronomers could not see the canals, either double or single. At length, in 1886, 9 years after the Italian astronomer made his discovery, the news flashed over the scientific world that his discovery was confirmed. In that year, the astronomers at the Nice Observatory detected the canals. They were soon followed by a number of the most distinguished observers, both of Europe and America, who testified that the canals were there, however much astronomers might differ in their interpretation of them. In 1892, Professor Pickering, observing in the fine climate of Arequipa on the slope of the Andes in Peru, discovered at the junctions of the canals dark spots, which he termed lakes, in keeping with the view that the darker regions of the planet's surface are really aqueous. But his observations at the same opposition threw considerable doubt on his view. For the purpose of observing the planet thoroughly during the favorable opposition of 1894, Mr. Percival Lowell erected a special observatory at Flagstaff, Arizona. Observations were then commenced on May 29, 1894 by Mr. Lowell and his assistant Mr. Douglas, and were continued until April 3, 1895, when the favorable season for observations came to an end. Altogether, Mr. Lowell mapped out 350 canals and obtained confirmatory evidence of the existence of lakes discovered by Professor Pickering. Indeed, of lakes, Mr. Lowell prefers to call them oases. At the same time, Professor Lowell made what he calls a Martian polar expedition. On 3 June 1894, he measured the South Polar Cap when it stretched, almost one unbroken waste of white, over about 55 degrees of latitude, its diameter across measuring 2,035 miles. As it melted, there was observed surrounding it a broad blue belt, and as the cap contracted, the belt, which evidently represented the water let loose by the melting of the cap, also decreased in size. In August 1894, it was, in Professor Lowell's words, a barely discernible thread drawn round the tiny white patch, which was all that remained of the enormous snowfields of some months before. On 12th October, Mr. Lowell noted in his diary, "Polar cap has been very faint for some time, barely visible." On the following day, his assistant, on turning the telescope on Mars, was amazed to find that the cap had vanished. This was the first occasion on which the snow cap was seen to disappear, and this shrinkage or disappearance of the cap apparently holds the key to the various problems of the Martian disk. By this time, several theories had been put forward to account for the phenomena of the planet's surface. Proctor had thrown out the hint that the canals were rivers, but this idea was soon thrown aside. Various other astronomers regarded the canals as cracks in the planet's surface, as swarms of meteors plowing tracks above the planet, and as chains of mountains running over land and sea. But each of these hypotheses was in turn abandoned as untenable. In the end of 1895, Mr. Lowell's views on the planet, the result of his own observations, were given to the world in his book, Mars. Mr. Lowell concludes that the reddish ochre portions of the planet, the continents of Proctor, are desert land, that the dark regions are not seas but marshy tracts of vegetation, and that the polar caps are composed of snow and ice. He adopts Professor Schiaparelli's view that the canals are waterways, lined on either side by banks of vegetation, as well as Professor W. H. Pickering's idea that the lines which we see are not the canals themselves, which are much too small to be seen, but the strip of fertilized ground surrounding them. The canals are distinctly connected with the melting of the polar cap, and grow darker as the cap melts, just as if water was being conveyed along them. All this is very easily explained by one assumption, namely that the canals have been constructed by a race of intelligent beings for the specific purpose of bringing water from the melting polar cap to the equator. Mars is scarce of water, and if there are inhabitants, they must be compelled to utilize every drop which they can secure. The oases are supposed by Mr. Lowell to represent centers of population where the inhabitants, driven from the desert land by scarcity of water, cluster about the ground artificially fertilized. Mr. Lowell also concludes that as Mars is an older planet than the Earth, the inhabitants are probably in a higher state of civilization. Thus, all the complicated Martian phenomena are explained on the assumption that Mars is inhabited by a race of intelligent beings. This theory was not cordially received, and astronomers began to consider if some other explanation would not be more probable. Most scientists inclined to what is known as the optical illusion theory, put forward originally by the eminent Italian astronomer Signor Vincenzo Cirilli of Teramo, and independently by Mr. E. W. Maunder of Greenwich Observatory, the well-known English astronomer. It was supported by Professor Simon Newcomb, who thus explains the canaliform appearance. This phenomenon is not to be regarded as a pure illusion on the one hand, or an exact representation of objects on the other. It grows out of the spontaneous action of the eye in shaping slight and irregular combinations of light and shade too minute to be separately made out into regular forms. A series of experiments made by Mr. Maunder in 1902 and 1903 were described by him in Knowledge for November 1903. In conjunction with Mr. Evans, headmaster of the Royal Hospital School of Greenwich, Mr. Maunder arranged for classes of 200 boys to copy at different distances 3 views of Mars on which the canal system was not represented. As almost all of the boys drew canals on the copies, Mr. Maunder considers that the optical illusion theory is finally proved, but Mr. Lowell answers him by the following criticism of the theory. It asserts that because of the tendency of the human eye to connect well-seen points by imaginary lines, therefore those on Mars are of this class, which is like saying that because a man might see stars without looking at the heavens, therefore those in the sky do not exist. The parallel is not simply for illustration, it is exact for the nervous action of the optic lobes, which similarly cause anyone to see faint points of light in a darkened field of vision, and the whole act of the observer consists in distinguishing which of these phenomena are objective and which not. So with these lines. A little more experience than the boys possessed would have permitted of parting the true lines from the false. Mr. Lowell's observations on Mars at the opposition of 1903 were distinctly confirmatory of this theory. He made use of his various drawings to determine the degree of visibility of a given canal at different seasons of the Martian year. After eliminating all sources of error, Mr. Lowell was able to construct graphs or curves of the visibility of the canals and thus formed a series of curves which he named cartouches. From a discussion of these cartouches, Mr. Lowell finds that the development of the canals does not commence until the polar cap begins to melt. But after the cap melts, the canals develop down the latitudes past the equator into the opposite hemisphere. He finds that it takes the water 50 days to travel from latitude 72 degrees north to the equator, a distance of 2,650 miles. This means a speed of 51 miles a day, or 2.1 miles an hour, and here we confront the surprising part of the performance, for the transference takes place in the face of gravity. A particle of water or other liquid would know no inclination to move from where it found itself. Gravity would not solicit it to stir. Of its own accord, it would not move from the pole to the equator. Now, as it does flow towards the equator, and with a remarkably steady progression too, the inference seems inevitable, that it has been carried thither by artificial means. In 1905 and 1907, Mr. Lowell succeeded in photographing the canals. His first photographs secured a number of converts, if not to his opinion, at least to belief in these remarkable objects. Mr. Lowell hailed his success in 1905 as the refutation of the opposing theory. As the photographic plate cannot be the victim of illusion, the canals should, on the illusion theory, be represented by irregular dots instead of straight dark lines. As Mr. Lowell remarked in a communication to the present writer, the camera does not agree with the armchair critics of the canals, but will have it that these markings are lines. Nevertheless, the supporters of the illusion theory still hold to a modified form of it. In their latest work, published in the end of 1908, Mr. and Mrs. Maunder have the following remarks. Are these markings on Mars actually as we see them, or do we only see them like that? we have no right to conclude that the straight, sharp, even canals we see on the surface of Mars are actually as artificial as they seem to us. Some remarkable observations of the canals were made by Professor Lowell at the opposition of the planet in 1909. On September 30th of that year, when the region known as the Syrtis Major was presented to view, two very prominent canals became evident. Not only, says Professor Lowell, was their appearance unprecedented, but the canals themselves were the most conspicuous ones on this part of the disk. Many drawings were made, and in the course of the next few days, the new canals were photographed, appearing on the plates as the most salient canals in their part of the planet. The record books were then examined, when it appeared that not a trace of them was to be found in the drawings of August, July, June, or May, when this part of the planet was depicted. That they had not been observed in previous years was then conclusively ascertained by examination of the records of those years. Professor Lowell shows that these canals were never seen before, either by himself or by Schiaparelli, or by any other observer. It might seem, he says, that the absence on the charts were proof that a canal was itself new in the second sense, because it was so in the first, but study of Mars has shown that this cannot be taken offhand for granted. Several points must each be carefully considered. In the first place, one must be sure that the phenomenon could have been seen before, yet was not. It must be a size which could not have escaped detection previously. In the present case, however, this possibility of error was excluded by the size of the canals in question. Mr. Lowell, in his announcement of the discovery, merely says that the proofs are clear that two new canals have developed. The inference in harmony with the theory which he maintains, that the canals are artificial, is that two new waterways have been constructed by intelligent beings. A good deal of skepticism has been aroused by a theory so startling, and few astronomers seem inclined to follow the American astronomer in the latest development of his theory. Still, if the theory in its general outline be correct, there is nothing either impossible or fantastic in Professor Lowell's explanation of the remarkable change which he has observed on the surface of Mars. Considerable space has been given here to the various theories of the canals, because these remarkable objects have not only attracted widespread attention, but have for years constituted a different astronomical problem. As was pointed out at the beginning of this chapter, more is known of the surface of Mars than of any other body except the Moon. Our knowledge of the planet's geography, or rather aerography, is well nigh complete. As Professor Lowell says, aerography is a true geography as real as our own. Quite unlike the markings on Jupiter and Saturn, where all we see is cloud, in the marking of Mars we gaze upon the actual surface features of the Martian globe. They change in appearance indeed, according to times and seasons, but they alter as true surface features would, not like cloud belts that gather today and vanish tomorrow. For these markings, a number of different systems of names have been in vogue. Proctor was the first to draw up a real geography of the planet. He named the features after well-known astronomers, such as Herschel Continent, Madler Continent, Dawes Ocean, Kaiser Sea. Flammarion drew up another chart with a different set of names. For instance, the Kaiser Sea became in Flammarion's system Mer du Sablier. Green, another English astronomer, invented another system. Finally, Schiaparelli renamed all the features on the disk, and in this nomenclature he is followed by Lowell and most modern students of Mars. His names are drawn from classical mythology and, being Latin, have the full advantage of commending themselves to astronomers of all nations. In this system, the Kaiser Sea, the best known object on the red planet, becomes the Syrtis Major. The canals are named after mythological and real terrestrial rivers. Thus we find on Mars the Euphrates and the Ganges. This system devised by Schiaparelli is now in general use. The canals vary greatly in length and in width. Many of them are about 2,000 miles long. One, known as the Eumenides Orcus, is 3,540 miles, altogether an enormous length on a globe as small as Mars. The larger canals are estimated as from 15 to 20 miles in width, and the smaller from 2 to 3 miles. As to their number, several hundreds have been catalogued by Schiaparelli and Lowell, and as the last named astronomer says, their name collectively is legion, while to name them individually is fast getting, for the number detected, to be impossible. The geography of Mars is truly a marvelous one, so much does it resemble, and at the same time so much does it differ from our own. Whatever be our opinion Professor Lowell's theory of their development, there is no doubt that Mars is relatively a much older world than the Earth, and that we see in it a world nearer to the end of life than our own, although relatively much younger than the Moon. For, as has been well remarked, in space there are both cradles and tombs. Mars has 2 satellites, which were discovered in the memorable year 1877. For 40 or 50 years, astronomers searched for satellites to the red planet. It was felt that as the Earth had 1 satellite and Jupiter 4, Mars should have at least 1 if not 2, but up to 1877, the search has been in vain. In that year, however, the late Professor Asaph Hall, aided with the large telescope of the Washington Observatory, detected 2 minute little satellites which circle round the red planet. In several respects, these little satellites differ considerably from our satellite, the Moon. In the first place, the Moon is comparatively a large body. These satellites of Mars, on the other hand, are very small. The diameter of Phobos, the nearer of the 2 to Mars, is estimated at 36 miles. That of Diomedes, the more distant, at 10 miles. In the second place, our satellite is at a considerable distance from the Earth, about 238,000 miles. The moons of Mars are comparatively close to their primary. Diomedes revolves at a distance of 14,600 miles, Phobos at a distance of 5,800 miles. Thirdly, our moon is a leisurely body. It requires about 27 days to complete its circuit of the Earth. The Martian satellites are remarkable for the extraordinary rapidity of their motions. Diomedes, the more distant of the 2, revolves round Mars in 30 hours 18 minutes, while Phobos completes a revolution in 7 hours 39 minutes. Now Mars requires over 24 hours to rotate on its axis. Phobos therefore revolves round Mars more than 3 times in 1 Martian day, an extraordinary state of affairs. As it revolves more swiftly than the planet rotates, it will not, like our moon, seem to rise in the east and be carried westward, the result of the Earth's rotation in the opposite direction. This Martian satellite rises in the west and crosses the heavens 3 times in 1 day. It overtakes Diomedes and eclipses it, and runs through all its phases in 11 hours. Each phase lasts only 3 hours. Imagine a world with a moon which could be seen in early evening at first quarter and 3 hours later at the full. The satellites are so small, however, that they can be of little use to Mars in illuminating the evening skies. If there are inhabitants of Mars, their skies will appear the same as our own. The stars and constellations are identical, but of course the different bodies of the solar system are definitely seen. An able astronomical writer explains the appearance of the planets from Mars in the following words. Jupiter is magnificent from Mars. It appears to the Martians half as large again as it seems to us, and his satellites should be easily viewable to the naked eye. Saturn is likewise very brilliant. Uranus is easily visible, and they might have discovered Neptune before we did. They must have distinguished with the naked eye a large number of the small planets which revolve between their orbits and that of Jupiter. Mercury, drawn closer to the Sun and lost in his rays, is almost impossible to distinguish. Venus appears to them as Mercury does to us. As for the Earth, how do they see it? We are for that planet, Mars, a brilliant star presenting an aspect similar to that which Venus presents to us, preceding the dawn and following the twilight. In a word, we are to the inhabitants of Mars the shepherd star. Our natural vanity, then, might delude us with the idea that the inhabitants of Mars contemplate us in their evening skies purpled with the last solar rays, that they admire us from afar, that they have discovered our phases and those of the moon as we have discovered those of Venus and Mercury, and that they suppose our world to be an abode of peace and happiness. Perhaps even they raise altars to us. What a disillusion if they could observe us a little nearer. End of Chapter 8. Read by raiynn, Toronto, March 2022.
Chapter 9 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 9. The Asteroids. The orbit of Mars marks the limit of the inner group of planets. These are separated from the outer group by what is variously known as the zone of asteroids, planetoids, or minor planets. They are, indeed, the most minute of bodies. Unlike their mighty neighbor, Jupiter, and their comparatively large neighbor, Mars, they are not to be seen without the aid of a telescope. The discovery of this zone belongs, therefore, to comparatively recent times, although the existence of one or more planets between the orbits of Mars and Jupiter was suspected fully 300 years ago. In fact, Kepler, who gave the world the 3 laws of planetary motion, predicted that a planet would be found revolving between the 2 bodies. Belief in the existence of such a planet was strengthened when, in 1772, a German astronomer named Bode investigated a curious relationship since known as Bode's law, connecting the distances of the planets. If we write down the following numbers, of which each after the second is double that preceding it, 0, 3, 6, 12, 24, 48, and 96, and add 4 to each, we have another series: 4, 7, 10, 16, 28, 62, and 100. Now, it is a remarkable fact that these numbers represent approximately the proportions of the distances of the various planets from the Sun. Bode pointed out that 4 corresponded to the distance of Mercury, 7 to that of Venus, 10 to that of the Earth, 16 to that of Mars, 52 to that of Jupiter, and 100 to that of Saturn. In 1781, another planet, Uranus, was discovered, and it was found that it filled the number 196. But there was not a planet at a distance corresponding to 28 between the orbits of Mars and Jupiter. Bode noted this fact and stated his belief in the existence of a planet to fill the vacant space. In 1800, von Zach, another German investigator, summoned a congress of astronomers to make a search for this remarkable body, whose existence was believed in before it was glimpsed by human eye. The zodiacal region of the heavens was divided for the purposes of the search into 24 zones, each of which was assigned to a particular astronomer. Some astronomers were unaware of the fact that a zone of the heavens had been laid aside for their own particular attention. Among those who did not, at the end of 1800, know of his own position among the band of searchers was Piazzi, the director of the observatory at Palermo, in Sicily. On the first night of the 19th century, January 1, 1801, Piazzi was making observations for the purpose of forming a star catalogue when he noted particularly an 8th magnitude star. On the following night, he ascertained that this was not one of the stars proper, but a body possessed of an appreciable independent motion. At first, Piazzi believed that he had discovered merely a faint comet, but he soon came to the conclusion that he had found the missing planet. Accordingly, he wrote to Bode at Berlin, informing him of his discovery. Piazzi continued to observe the strange object for 6 weeks, when he became unwell. By the time he was able to observe again, the planet was invisible in the rays of the sun, and astronomers were afraid that it had been found only to be lost. However, an orbit was calculated from the few observations made by Piazzi, and on the last day of 1801, the planet was again observed. It received the name of Ceres at the suggestion of the discoverer. The gap had now been filled. The planet, it was true, was not comparable in size with any of the known planets of the solar system. It was so faint as to be invisible to the unaided eye. Still, astronomers believed that the missing planet had been found, filling the vacant space 28 of Bode's numerical progression. The solar system was now regarded as complete. Only 3 months after Ceres was rediscovered, this opinion was rudely overturned. Olbers, a famous German astronomer, followed closely the new planet Ceres in the months following its rediscovery, and on March 28, 1802, he was astonished to find quite close to the position of Ceres another strange star of the 8th magnitude. A few hours showed him that this object was in motion. Here was a remarkable discovery. Not one, but 2 planets revolved in the vacant space, and the new body, which received the name of Pallas, was found to revolve round the sun at nearly the same distance as Ceres. The 2 bodies were without doubt akin to each other. The symmetry of the solar system was supposed to be broken, and no one was more astounded at the existence of 2 planets where one alone was expected than Olbers, the discoverer of Pallas. At length he put forward his explanation of the presence of 2 small bodies. He supposed that there had existed between the orbits of Mars and Jupiter a large planet, of a kind similar to the other worlds of the solar system, and that through some terrific catastrophe, this planet had, in the remotest past, been shattered to fragments. He predicted that many more such fragments as Ceres and Pallas were likely to be found, and recommended that a search be made for other portions. In 1804, Harding, another German astronomer, discovered a 3rd fragment, which was named Juno, and in 1807, Olbers, who had been maintaining a close watch, detected a 4th. The new planet was named Vesta, and is the brightest, though not the largest, of the asteroids. These 4 bodies were named the asteroids or planetoids, and for about 40 years the system was again regarded as complete. It may be stated here that the theory of Olbers, although it led to the discovery of other 2 fragments, is not now accepted by astronomers. As no further asteroids seemed to be forthcoming, the search was abandoned in 1816. 14 years later, however, it was resumed. A German amateur astronomer, Henke, ex-postmaster of Dresden in Prussia, began to search for further members of the asteroid system. For 15 years he watched without success, but at last, in December 1845, he discovered a 5th asteroid, which received the name of Astrasa. A year and a half later, he detected yet another, known as Hebe. In the same year, an English astronomer, Hind, detected Iris and Flora, other two members of the system. Since 1847, not a single year has passed without the discovery of one or more asteroids. Some astronomers devoted almost all their time to the search for and discovery of minor planets. Peters, an American astronomer, discovered 48. Palisa, an astronomer of Vienna, found over 80, while Goldschmidt, Luther, Schakornak, and other observers each discovered many of these small planets. The method of discovery adopted by these astronomers was to construct charts of the regions round about the ecliptic in which such planets were likely to be found, and to compare those charts with the actual appearance of these regions of the heavens through the telescope. By this method, it was easy to pick out unfamiliar stars and identify them as new asteroids. This method, however, has now been discarded. A new method was devised in 1891 by Professor Max Wolf of Heidelberg, who has discovered over 100 asteroids. It occurred to Dr. Wolf to apply photography to the detection of these objects. It is obvious that an asteroid, owing to its appreciable motion, will be represented on a photographic plate not as a point of light, like the stars in the background, but as a streak of appreciable length. As Professor Brashear explains, when the picture is developed, the stellar images show themselves as small circular dots. But if a planet were in the photographic field during the exposure, its image would be that of a very short line or trail about 1/20th of an inch long, because it has an average movement through space of a little less than half the diameter of the moon in 24 hours, while the stars remain practically stationary. This tiny trail is the clue to a new planet, or perhaps one already discovered. Since 1891, this method has been used extensively. In less than 2 years, Dr. Wolf discovered 17 asteroids. During the past 18 years, many minor planets have been detected in this way by Wolf and his assistants, and by Charlois, Metcalfe, and other observers. The number of known asteroids now stands at about 700. By the time Dr. Wolf applied his photographic method, popular interest in the ever-increasing family of little planets was on the wane. Mr. G.F. Chambers in 1895 described the asteroids as of very little interest to anybody. It was hinted that there was no use continuing a search for bodies which so closely resembled each other and the discovery of which served no useful purpose to the discoverer. Certainly it must have been a singularly uninteresting search for the astronomers who prosecuted it, because with so many asteroids already discovered, there was always the possibility that the newly found object might not be a new asteroid at all, but merely a known one which had been lost to astronomers. Great care had to be taken to ensure that the same planet was not discovered twice and regarded as two different objects. As Professor Turner of Oxford remarks, there was a system of numbering in existence as well as of naming, but it was inadvisable to attach even a number to a planet until it was quite certain that the discovery was new, for otherwise there might be gaps created in what should be a continuous series by spurious discoveries being struck out. Accordingly, it was decided to attach at first to the object merely a letter of the alphabet, with the year of discovery as a provisional name. The alphabet, however, was run through so quickly, and confusion was so likely to ensue if it was merely repeated, that on recommencing it, the letter A was prefixed, and the symbols adopted were, therefore, AA, AB, AC, etc. After completing the alphabet again, the letter B was prefixed, and so on. This was getting tiresome to the astronomical world until, at length, in 1898, an insignificant little object was discovered on a photographic plate by Witt in Berlin, and designated as DQ. It was seen that this was a real discovery, and to the little body was assigned the number 433 and the name of Eros. It soon appeared that this asteroid was of more interest and use to the astronomer than all the other asteroids put together. The vast majority of the asteroids have their orbits between the paths of Mars and Jupiter, but this little planet revolves in an orbit so elliptical that at its nearest position to the Earth, it comes within the orbit of Mars, and is only 13.5 millions of miles from the Earth. It is at times our nearest planetary neighbor, but is so faint that it is never to be seen without the aid of a telescope. It can, however, be photographed, and in this way is of the greatest use to the astronomer. By means of observations on a body so near, its distance, and thus the scale of the whole solar system, is very easily calculated. The little planetoid, therefore, has supplied astronomers with perhaps the most reliable measurements of the actual scale of the solar system. Since 1898, the discovery of asteroids has gone on at the same rate, but no further objects of interest have been found. Although the asteroids are, generally speaking, akin to one another and form a distinct zone in the solar system, they have their own individual differences. Their periods of revolution vary considerably from about 3 to 9 years. Some of the orbits are very elliptical in shape, and unlike the large planets, many of them do not move almost exactly in the plane of the ecliptic. Pallas, for instance, moves in a path which is inclined to the ecliptic at an angle of 34 degrees. In size also, there are great differences. The 4 earlier discovered asteroids, Ceres, Pallas, Vesta, and Juno, are the largest. These are the only asteroids which actually show measurable disks and can thus be actually measured, and it is only by the aid of the largest telescopes in the world that such measurement can be made. Ceres is 477 miles in diameter, Pallas 304 miles, Vesta 239 miles, and Juno 120 miles. Vesta is the brightest of the 4, so its surface must be highly reflective. The sizes of the smaller planets have not been measured, but can be estimated, and it is believed that few of them have a greater diameter than 25 miles. Practically nothing is known of the physical nature of these minute planets. Professor Barnard observed the 4 larger ones carefully some years ago with the large telescope of the Lick Observatory, and saw no traces of atmosphere round them. Nothing is known either of their rotation or of the actual condition of their surfaces. Some of them are variable in light, and it is supposed that such variation is caused by the different reflective powers of the different hemispheres, combined with the rotation of the planetoids on their axes. These variable asteroids probably have rugged surfaces on which the amount of light reflected varies considerably. The asteroid group is one of the most remarkable features in the solar system. It is obvious that one large planet is replaced by many little ones. It is also obvious that the zone divides the 2 groups of inner planets and outer planets, and thus separates the solar system into two portions. The existence in the solar system of this group of minute bodies, all but innumerable, each pursuing its own appointed path round the orb of day, is another example of the variety and harmony of nature. End of Chapter 9. Read by Carrie Adams, your book voice, at Mesa, Arizona, on the 25th of March, 2022.
Chapter 10 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 10. Jupiter, the Giant Planet. Once in about every 13 months, there reaches the meridian at midnight one of the most brilliant objects in the sky. Rising about sunset in the east, it gradually ascends until it is due south at midnight and in opposition to the sun. For some time after opposition, it is the most brilliant object in the night skies, and as such commands the attention of even the most casual of stargazers. For Jupiter so far outshines all the stars in its vicinity that there can be no doubt in identifying the great planet. It reigns supreme, shining with a steady light, not so soft as that of Venus, but sharper and more sparkling. As Flammarion remarks, quote, "When Jupiter shines among the stars of the silent night, and when our gaze is fixed on him, who would suppose, while admiring this simple luminous point, that it is an enormous and massive globe, weighing over 300 times more than the planet which we inhabit, and of which the colossal volume exceeds by nearly 1,300 times that of the earth. We have our eyes fixed on him, his light is so vivid that it casts a shadow like that of Venus, but we do not guess the marvelous grandeur of this distant body." Unquote. Of all the planets, Jupiter is the easiest to observe telescopically. The smallest instrument will show that it is a planet with a round disk, and will give us a glimpse of the 4 satellites of the planet discovered by Galileo in 1610, over 300 years ago. Great must have been the delight and wonder of the great Italian astronomer when, pointing his newly constructed telescope to Jupiter for the first time, he beheld the luminous point of light transformed into a flat disk, with 4 little points of light circling around it. A 2-inch telescope gives a very striking view of the planet. On a clear night, such an instrument enables us to see on the disk 2 or 3 parallel strokes, as it were. This is our first glimpse of the famous belts of Jupiter, which were first discovered after the time of Galileo. It requires a much larger instrument to bring out the principal features of the belts. With a good telescope, we may view what an American astronomer thus vividly describes, quote, "Belts of reddish clouds, many thousands of miles across, are stretched along on either side of the equator of the great planet. The equatorial belt itself, brilliantly lemon-hued or sometimes ruddy, is diversified with white globular and balloon-shaped masses, which almost recall the appearance of summer cloud domes hovering over a terrestrial landscape, while towards the poles shadowy expanses of gradually deepening blue or blue-gray suggest the comparative coolness of those regions which lie always under a low sun." Unquote. The belts are not permanent markings. They are belts of cloud, and as such are continually changing. Still, they are not so fleeting as the clouds in our own atmosphere. Some of the Jovian features, indeed, are more or less permanent. Chief among these must be mentioned an object known as the Great Red Spot. It was first noticed by a number of observers in the summer of 1878, and described by them as a pale pinkish oval spot. In 1879, it became much more prominent. The pinkish hue gave place to brick red, while the entire object extended 30,000 miles from east to west and 7,000 from north to south. The area of the spot was no less than 200 million square miles, greater than the area of the entire terrestrial globe. For 3 years, the spot was a brilliant object, the most prominent feature on the globe of Jupiter, lying immediately south of the great equatorial belt of the planet. Then it began to fade, and an observation by Rico at Palermo in 1883 was thought to be the last. But in a short time it revived and again became the most prominent object on the planet's disk. Again, it faded considerably, but it is still visible, a permanent feature of Jupiter's disk. This marvelous spot has for many years attracted the attention of astronomers all over the world. Many speculations have been made as to its nature, and it is difficult to ascertain the exact cause of the appearance in a cloudy atmosphere of a permanent feature lasting so many years. Mr. W. F. Denning, one of the most devoted observers of the planet, gives as his opinion, quote, that it represents an opening in the atmosphere of Jupiter through which in 1878 through 82 we saw the dense red vapors of his lower strata, if not his actual surface itself. Its lighter tint in recent years is probably due to the filling in of the cavity by the encroachment of durable clouds in the vicinity." Unquote. Another remarkable fact in connection with the spot was ascertained by the American astronomer Professor Barnard. One of the most interesting features of the great spot, he said, quote, was the repulsion it seemed to exert upon adjacent markings on the planet. For a time it was surrounded by a sea of light that completely circled it for a distance of 3,000 or 4,000 miles, and which appeared as a visible barrier against the approach of any spot or marking." Unquote. Observations on various spots and belts many years ago revealed the fact that Jupiter rotated on its axis in a little under 10 hours. The most exact determination fixes the rotation period at 9 hours 55 minutes 36.56 seconds. Thus, Jupiter's day is very much shorter than that of the Earth, notwithstanding the size of the mighty planet. The curious point, however, about the rotation of Jupiter, as ascertained from observations on the red spot and other markings, is that, like the Sun, its rotation is not uniform. According to one astronomer, no fewer than 9 different rotation periods are found. There is not much difference, it is true, between the various periods, but this difference gives rise to curious results. Some bright spots round about the equator actually overtake the red spot at the rate of 260 miles an hour. All these facts go to prove that in Jupiter we have a world of a different type from the 4 inner planets. In the case of Mars, for instance, we see the actual surface of the planet. The markings may change in accordance with the seasons, but they are always to be seen, and the rotation period derived from them is constant and unchanging. In the case of Jupiter, we never see the actual surface. A remarkable thick atmosphere enshrouds the planet, an atmosphere quite unlike our own. We cannot compare the Jovian markings to our terrestrial clouds. A cloud on the Earth is a fleeting thing. It does not last for days, still less for 32 years. The red spot in Jupiter's atmosphere has been seen since 1878. It is quite obvious, therefore, that Jupiter is a body of quite a different order from our own world. In many ways it resembles the Sun more than the smaller planets. Indeed, in 1879, Bredikhin of Moscow observed on the Jovian disk a group of faculae similar to those of the Sun. Some astronomers believe that the markings on Jupiter, like those on the Sun, are regulated by an 11-year period, but this is not absolutely certain. At all events, observations of Jupiter during the last 50 years have abundantly shown that it resembles the Sun more than the Earth. It used to be believed that the atmosphere was something similar to our own, but much more dense, and that the cloud belts were analogous to the trade winds on our planet. But the impossibility of this view was long since demonstrated. The clouds on the Earth are raised by sun heat. Jupiter is at a much greater distance from the Sun than the Earth is, and yet it possesses an atmosphere much more dense and cloudy than ours. The explanation is obvious. Jupiter is very much larger than the Earth. It is a world in a state of chaos, quote, without form and void, unquote. It is in a condition of great heat, so that the vapors, instead of settling on the surface in the form of oceans, are boiled off the fiery surface, as it were, and kept suspended in the atmosphere in the form of dense cloud masses. Jupiter seems to be in a very primitive condition, somewhat similar to Saturn and probably Uranus and Neptune, and it throws an interesting sidelight on the previous condition of our own world. For some time, astronomers believed Jupiter to be slightly self-luminous, but this view has not been confirmed. The planet probably gives out an appreciable quantity of heat, but it is likely that its days of shining by its own light are ended. Very probably the surface is only now becoming solidified and enormous volcanic disturbances are of daily occurrence in the semi-liquid planet. Of course, this is but speculation, for the atmosphere is so dense that it is quite impossible to see it. From the surface of the planet, whether it is a solid or a semi-liquid surface, no glimpse of the outer universe is visible. Supposing, however, that an observer on Jupiter could see through the cloud belts, the Earth would be hardly visible, being only seen with difficulty in the vicinity of the Sun. At night, says a famous astronomer, quote, "The spectacle of the sky seen from Jupiter is, with reference to the constellations, the same as that which we see from the Earth. There, as here, shine Orion, the Great Bear, Pegasus, Andromeda, Gemini, and all the other constellations, as well as the diamonds of our sky. The 390 millions of miles which separate us from Jupiter in no way alter the celestial perspectives. The most curious spectacle of this sky is unquestionably the spectacle of the 4 moons." Unquote. To these moons, Jupiter acts as a miniature sun, giving out an appreciable amount of heat, as well as reflecting the heat of the Sun. Jupiter is attended by no fewer than 8 satellites, 4 large and 4 small. The discovery of the 4 large satellites was one of the greatest in the history of astronomy. In 1610, Galileo at Padua turned the newly invented telescope on Jupiter and discovered that the giant planet was surrounded by 4 satellites. The discovery was hailed with great joy by the supporters of the Copernican system. Here was a miniature of the solar system disclosed by Galileo's telescope, which ought to convince even the most skeptical. But the opponents of the new system would not be convinced and regarded the discoverer with very unfriendly feelings. One Italian student refused to look through the telescope lest he should see the satellites. Another consented to observe Jupiter and was immediately convinced that the satellites existed, while a third declared that even though he saw the satellites through the telescope, he would not believe in them, declaring that they were in the telescope and not in the sky. The 4 satellites are sometimes known by the name of Io, Europa, Ganymede, and Callisto, though they are more frequently designated by the numerals 1, 2, 3, and 4. The nearest satellite, Io, revolves round Jupiter in one day 18 hours, 27 minutes, at a mean distance of 261,000 miles. Its diameter measures about 2,500 miles. The second satellite, Europa, the smallest of the 4, with a diameter of 2,100 miles, revolves round the primary in 3 days, 13 hours, 13 minutes, at a mean distance of 415,000 miles. The third moon, Ganymede, is the largest of the 4, its diameter measuring 3,550 miles. It is therefore larger than the planet Mercury. It moves round Jupiter in 7 days, 3 hours, 42 minutes, at a mean distance of 664,000 miles. Callisto, the 4th satellite, with a diameter of 2,960 miles, revolves round the primary at a mean distance of 1,167,000 miles in 16 days, 16 hours, 32 minutes. These satellites are among the easiest objects of observation to the amateur astronomer. The smallest telescopes will show them, and they are a source of never-ending pleasure. They may be seen sometimes in transit across the disk of Jupiter, while sometimes we are able to witness their immersion into the shadow of the giant planet and consequent eclipses, while at times we see Jupiter's disk pass over one or more of the satellites and obscure them from view. This phenomenon is known technically as occultation. A small telescope will not show surface markings on the disks of the satellites. Even with the largest and best instruments, astronomers have learned little of the constitution of these moons. As to size, the 2 largest are of planetary bulk and dimensions. The 4 satellites combined form 1/6,000th part of the mass of Jupiter, and their volumes form 1/7,600th part of the volume of the giant planet. Hence we see that while 3 of the satellites are absolutely larger than our moon, all 4 are, in comparison to Jupiter's bulk, relatively much smaller bodies. The satellites seen from Jupiter's surface cover an area of the sky larger than the area filled by our moon, but they are much less brilliantly illuminated, owing to the much greater distance of the Jovian system from the Sun. The total amount of light reflected from all 4 satellites at once is only 1/16 of that reflected by the full moon as seen from the surface of the Earth. For over 280 years, the system of Jupiter was regarded as complete. The 4 satellites had been known for a long period. Their motions had been carefully calculated. In fact, astronomers were thoroughly acquainted with all the details of the Jovian system. Great was the surprise among astronomers when in September 1892 it was announced that an American astronomer had discovered a 5th satellite. On the 9th of that month, Professor Barnard, while observing Jupiter with the great telescope of the Lick Observatory in California, detected a minute speck of light near the planet. A series of observations proved that this was indeed a new satellite of Jupiter, closer to the planet than any of the other moons. It revolves round Jupiter in 11 hours 57 minutes at a mean distance of 112,000 miles. It is very much smaller than the other satellites, for its diameter is little over 100 miles. In 1905, 2 other satellites of Jupiter were discovered by Professor Perrine at the same observatory. Both of these minute objects were discovered by the aid of the photographic plate. The 6th satellite revolves round Jupiter in 242 days at a mean distance of 6,968,000 miles. The 7th satellite is slightly closer to the planet, round which it moves in 200 days at a mean distance of 6,136,000 miles. Early in 1908 came the announcement of the discovery of another satellite. The 8th moon, also very small and faint, was discovered by Mr. Mellote, assistant at the Royal Observatory, Greenwich, with the aid of photography. It is at a much greater distance from the planet than the other satellites and revolves round Jupiter in the opposite direction. In astronomical language, its motion, instead of being direct, is retrograde. In this respect, the most distant satellite of Jupiter resembles the most distant satellite of Saturn, as will be explained in the next chapter. It is quite possible that there may be other satellites still undiscovered. The system of Jupiter is as interesting as it is beautiful. So far as is known at present, the planet has 8 satellites, 4 of almost planetary dimensions, 4 of what may be called asteroidal size. The system is more beautiful and complex than Galileo and the early astronomers imagined. As to the possibility of life in the Jovian system, the reader will have to be able to judge from the physical condition of the planet that no life akin to life as we know it can possibly exist at the present moment. That it may be inhabited at some future time when the cloud belts roll away and the vapors settle on the surface as oceans is quite possible. Some astronomers believe that the satellites are likely to be inhabited, and certainly the 4 larger moons seem the more likely bodies in the Jovian system on whose surfaces life may exist. To these moons, Jupiter will be a semi-sun radiating, if little or no inherent light, at least a vast amount of inherent heat. But of the actual surfaces of the satellites, we know practically nothing. Marvelous and complex as is the system of Jupiter, it is simple compared to that of Saturn, to the consideration of which the next chapter is devoted. End of chapter 10.
Chapter 11 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Jack Hill. The Romance of Modern Astronomy by Hector Macpherson. Chapter 11. Saturn, the Ringed World. In ancient days, when astrology had sway over mankind, the planets were believed to influence the destinies of mortals. To be born under the planet Jupiter was to be sure of a career marked by good fortune and distinguished by glory. Mars was the god of war, and those born under the sign of that planet were characterized by martial deeds and military renown. The favorites of Mercury had the arts as their special sphere, while Venus held sway in the realms of love. Saturn was known as the unlucky planet. Its slow motion and dull, laden light betokened gravity and gloom, and those born under its sign were called Saturnine, and were thought to be dull and morose in their natures, and to be destined to grief and calamity. To the unaided eye, Saturn appears as a star of the first magnitude, with none of the brilliancy of the other planets. It has nothing of the steady brilliance of Jupiter, the soft luminosity of Venus, or the fiery red light of Mars. Consequently, the ancients thought Saturn by far the least interesting of the planets, and indeed, when it is examined with the unaided eye, we are inclined to accept their opinion. But with a powerful telescope, we gain quite a different idea of Saturn. So far from being the least interesting of the planets, it is the most interesting. Indeed, it is absolutely unique in the solar system, and as far as is known, in the universe. When we turn the telescope on it, we behold a glorious orb. Its disk is striped with belts similar to those of Jupiter, only fainter owing to its greater distance. A wonderful system of 3 rings surrounds the planet, 2 bright and 1 a dusky hue. These are perfect in symmetry and exquisite in beauty. Our sense of the marvelous is deepened when it is borne in mind that these rings are not less than 176,000 miles in diameter and 30,000 miles in width, and not more than 50 to 100 miles in thickness. Telescopic contemplation of this magnificent planet, with its imposing system of rings, fills the mind with feelings of wonder and awe. As Flammarion puts it, when we think that there is here a celestial deck on which the entire globe of the earth might roll like a ball on a road, and that the world, poised in the center, is several hundred times larger than our planet, we transport ourselves easily in thought to those sublime regions. The system of rings which encircle Saturn has been known to astronomers for 2.5 centuries. To Galileo they were a source of much perplexity. His telescope was not powerful enough to disclose their true nature. When he first observed Saturn, it seemed to him to be oval-shaped, and this appearance he believed to be due to the fact that the planet was in reality triple, consisting of a large celestial body with a smaller orb on each side, like 2 servants who help old Saturn on his way. Accordingly, he announced that the planet was triple. Some time later, he concluded that the appearance pointed to the existence not of a triple planet, but of an orb oval in shape. Great was his surprise when 2 years afterwards he found that the planet had become round again. We now know that these appearances are due to the periodical vanishings of the rings, owing to the fact that as Saturn moves onward in its orbit, we sometimes behold the ring system, which is very thin, directly in the line of vision, and thus see it edgewise. Galileo knew nothing of this, and he was astonished at the planet's change of shape. He was utterly cast down. Writing to his friend, the ambassador of the Grand Duke of Tuscany, in the end of 1612, he said, "Were the appearances indeed illusion or fraud, with which the glasses have so long deceived me, as well as many others to whom I have shown them? I do not know what to say in a case so surprising, so unlooked for, and so novel. The shortness of the time, the unexpected nature of the event, the weakness of my understanding, and the fear of being mistaken have greatly confounded me." So much was Galileo disappointed at his failure to solve the problem, that he gave up observing Saturn altogether. It was left to a later astronomer, the Dutchman Huygens, to demonstrate the true nature of the appearances. With the aid of telescopes much more powerful than those used by Galileo, he came to the conclusion that the planet was surrounded by a ring, but he was not absolutely certain, and he wished to test his theory so that there would be no possibility of mistake. In those days it was the custom of men of science to publish their discoveries to the world in the form of anagrams. That is to say, they wished to secure for themselves the right of discovery, and at the same time have the opportunity of confirming their theories. Accordingly, he jotted down a number of letters in chaotic form and published them in an apparently senseless jumble. Huygens was afraid that while testing his theory of the existence of a ring system, some other astronomers might make the discovery independently, and thus rob him of the honor. Therefore he published the following anagram in 1656. A.A. 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 A. C.C.C. C.C. D. E.E. E.E.E. G. H. I. I. L. 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 M, M, N, 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 O, 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 P, P, Q, R, R, S, T, 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 U, 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 U. 3 years later, he arranged the letters in their natural order, having satisfied himself that his theory was correct. This made up the following Latin sentence: Annullo cegitur tenui pleno nusquam cohaerante ad ellipticum inclinato. Translated into English, this reads, the planet is surrounded by a slender, flat ring inclined to the elliptic and nowhere touching the body of the planet. Many years afterwards, it was found that the ring was really composed of 2 rings. We now know of the existence of 3. Within the 2 bright rings, there is a third known as the dusky ring. It was the last of the 3 to be discovered, and was first detected in 1850. For many years it was supposed that the ring system was a solid whole, that the rings were flat planes, but it has been now proved that they are not solid, being made of innumerable small satellites, or rather meteorites, and so close together are these minute bodies that they appear from this vast distance as a complete solid. They are in constant revolution around the planet. From Saturn, it is probable that they appear as a continuous whole. Indeed, from the surface of the planet, the ring system must seem both magnificent and stupendous. Let us imagine ourselves on the globe of Saturn, on a journey from the pole to the equator, keeping a close watch on the Saturnian heavens. From the poles, the rings are invisible. As we move equatorwards, the system gradually comes into view. As we advance, the rings rise higher and higher above the horizon. At the same time, they diminish in breadth as we see them more and more foreshortened. At the equator, they are exactly overhead, and we only see the interior edge of the system as a narrow arch extending right around the heavens. From a latitude of 28 degrees on Saturn, says the French writer Guillemin, the ring system is seen as an immense arch, interrupted by a large space at the summit. The sky is visible through the division which separates the 2 principal rings, and it again appears below the arch. The interruption at the summit is produced by the shadow cast by Saturn, and is only distinguished from the sky by the absence of stars. It is possible, however, that this eclipsed portion of the rings may be sometimes rendered visible by the refraction of the solar rays by the atmosphere of the planet. When we add to the strange beauty of the spectacle the presence of the satellites presenting different phases, some full, others new, others gibbous or crescent, and an idea will be formed of the variety of aspect of the Saturnian nights. This description applies only to the summer time of the particular hemisphere of the planet for which it is intended. In winter, the ring system reflects no light whatever to the planet. Not only do the rings give no light during the Saturnian winter, but they cut off the light of the sun from the planet. They totally eclipse the sun for long periods at a time. For 15 years, half the period of Saturn's revolution, the sun is to the south of the rings, and for 15 years to the north. But the shadow of the ring system is so broad that the regions midway between pole and equator on Saturn have to suffer eclipses which last for more than 5 of our years at a time. Saturn is at a much greater distance from the sun than the Earth, and receives much less sunlight. Consequently, it can ill afford to be deprived for long periods at a time of the little sunshine which it is due. Saturn, therefore, does not seem a very inviting dwelling place for human beings. In all probability, however, there are no inhabitants on the planet. We learn this from a study of the globe itself. Saturn is the second largest planet in the solar system and has a diameter of 74,000 miles. Suppose we represent the Earth by a pea. In proportion, we may take an orange to represent Saturn. Its distance from the Sun is nearly 900 millions of miles, and it requires almost 30 years to revolve once around the central luminary. Like the Earth, Saturn rotates on its axis. This rotation is performed in Saturn's case in 10 hours, 16 minutes, a much more rapid rate of rotation than that of our world, notwithstanding the greater size of the ringed planet. The globe of Saturn, apart from the rings, is a striking spectacle, although not so striking as Jupiter, seen through a good telescope. The cloud belts do not show the same rapidity of change as do those of Jupiter. Still, changes are apparent to the careful observer. The only surface of Saturn which we can see is its atmosphere, which is so dense and cloud-laden that beyond it nothing is visible. On the Earth, and also on Mars and Venus, the atmospheric clouds are raised by the heat of the sun. Venus, for instance, has a denser atmosphere than our world, probably because it is closer to the sun. Mars, on the other hand, has a thinner atmosphere, but Saturn is at a much greater distance, and at that distance the heat of the sun is so diminished in power that it cannot be responsible for the existence of an atmosphere so much more cloud-laden than ours. The heat which raises the clouds comes not from the sun, but from the planet itself. Like Jupiter, Saturn appears to be in a much earlier stage of development than the Earth. The oceans which will at some future date settle down on the planet's surface exist at present only in the form of masses of cloud floating in the atmosphere. It is more than doubtful whether Saturn has any solid surface beneath the dense canopy of clouds. It may have a crust partly solidified, but subject to violent eruptions, such as seem to have been prevalent during the early stages of the life of our own world. Let us picture to ourselves what goes on beneath those cloud belts. A world in a state of chaos exists there. Violent eruptions take place. Boiling, seething masses of fire shoot through the partially solidified crust. It is a world of relentless turmoil and sweltering heat. This view of the condition of Saturn is confirmed by the fact that while it is about 700 times larger than the Earth, it is only about 90 times as heavy. Indeed, in proportion to its size, Saturn is the lightest of all the planets. It is only equal in weight to a globe of walnut wood of the same size. In fact, if we could imagine a great ocean large enough to hold the various planets, and if we could imagine the planets thrown one by one into that ocean, Saturn would actually float, while all the others would sink. The extraordinary lightness of Saturn is explained by its condition of intense heat. Thus we see that in two particulars, Saturn is unique in the solar system. It is the lightest of all the planets, and it possesses a marvelous system of rings. But in another respect, it is also unique. So far as we know, it possesses more satellites than any other planet. There are no fewer than 10 of these little bodies owing it allegiance and circling around it in ceaseless revolution. In order of distance from the planet, the names of these little worlds are Mimas, Enceladus, Tethys, Dione, Rhea, Titan, Hyperion, Thymus, Iapetus, and Phoebe. Of these, Titan is by far the largest. It was the earliest discovered, and was first seen by Huygens during his study of the planet. It is about 3,000 miles in diameter, and equal in size to the planet Mercury. Indeed, Titan is quite a little world in itself. The faintest and probably the smallest is Thymus, which was discovered in 1905 by Professor W. H. Pickering of Harvard by means of photography. So faint is the little moon that it is quite invisible by ordinary telescopic methods, and it is only known by its image on the photographic plate. The most remarkable member of the system of Saturn, however, is the little moon known as Phoebe, the most distant of the satellites. All the other 9 moons revolve from west to east. The rings also revolve in that direction. The planet likewise rotates in that direction. But Phoebe revolves in the opposite direction, from east to west. Just imagine, if we had a number of moons and one of them revolved in the opposite direction from the others, how complicated and bewildering our evening skies would become. The satellites have great diversity in their periods of revolution. Little Mimas, the closest to Saturn of the 10, is at a distance of 115,000 miles and revolves in 22 hours, 37 minutes. Phoebe requires 16 months for its slow revolution around its primary. In the heavens, Saturn, with its magnificent system of rings, and its gorgeous retinue of moons, is a spectacle as majestic as it is unique. If any of its satellites be inhabited, these inhabitants will probably regard the planet as we regard the sun, as light-giver and heat-giver, and with good reason will they look to Saturn as their sun, as probably it gives out a certain amount of intense heat. Supposing either Saturn or its satellites were inhabited, the inhabitants would be hardly able to catch a glimpse of our Earth. Seen from Saturn, the Earth is a small, insignificant point, lost in the light of the far-away luminary, the sun. End of chapter 11.
Chapter 12 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sharon Vock. The Romance of Modern Astronomy by Hector Macpherson. Chapter 12. The Boundaries of the Solar System. Saturn was the most distant world known to the ancients. They regarded its orbit as the boundary of the planetary system, and it was not until the year 1781 that astronomers learned that the solar system extended to a much greater distance than the orbit of Saturn. Of the two distant planets Uranus and Neptune, little is known, but the story of their discovery is one of the most interesting chapters in the history of astronomy. To the genius and skill of William Herschel, we owe the discovery of the planet Uranus. The record of this discovery is so bound up with the life story of the discoverer that it is impossible to separate them. That life story is a record of endless perseverance, boundless energy, and undying enthusiasm. The most striking of all discoveries, however, was nothing less than that of a new planet revolving beyond the orbit of Saturn, the first new member of the solar system discovered within the memory of man. On March 13, 1781, while observing the stars in the constellation Gemini, he, in his own words, quote, perceived one that appeared visibly larger than the rest, end quote. Comparing it with other stars in the vicinity and, quote, finding it to be so much larger than either of them, he suspected it to be a comet, end quote. For some time it was believed to be one of these objects, but when its orbit had been calculated by mathematical astronomers, it soon became apparent that, instead of revolving in a very long ellipse as most comets do, it moved in an orbit, almost circular. There was no doubt, therefore, that the German musician had discovered not a comet, but a new planet, and had doubled by this discovery the diameter of the solar system. The scientific world was amazed at the discovery. It had never even suspected that an unknown orb revolved beyond the orbit of Saturn. It was, however, even more surprising to find that Uranus had often been seen and catalogued as an ordinary star, no fewer, indeed, than 17 times. Flamsteed, the first Astronomer Royal of England, observed Uranus 4 times in different positions and did not notice the difference of place. A French astronomer, Lemonnier, narrowly escaped discovering the planet in 1769 and would certainly have done so but for the careless and slovenly way in which he jotted down his observations. Herschel proposed to name the new planet Georgium Sidus, the star of George, after his patron George III. This title naturally found no favour on the continent. A French astronomer suggested the name Herschel after the discoverer himself, while Bode of Berlin suggested Uranus, in keeping with the custom of naming the planets after the Greek and Roman divinities. All these names were in use for a considerable time, but at length the name Uranus prevailed and is now universally adopted. The discovery of Uranus was a remarkable achievement, but it led to one still more remarkable, the detection of a planet still farther removed from the Sun. After Uranus had been duly recognized as a member of the Sun's family of planets, its orbit was calculated. In making these calculations, astronomers utilized the early observations of Uranus made by the observers who had failed to notice its difference from an ordinary star. The observations were far from useless, for although the observers had failed to make the discovery which was within their grasp, they had measured carefully the positions of their supposed star. This was all that mathematicians needed to enable them to calculate the planet's orbit with a further approach to accuracy. Bouvard, a French astronomer, published tables giving the planet's positions in the future. But as Uranus did not conform to the orbit which had been laid down for it, Bouvard concluded that there must be some mistake in the earlier observations. Accordingly, in 1821, he rejected these altogether and published a new series of tables, utilizing only the observations made since Herschel's time. Again, however, the planet was not in the predicted place. The error was very minute, it is true. As the late Miss Clerk points out, quote, "If the theoretical and the real Uranus had been placed side by side in the sky, they would have seemed to the sharpest eye to form a single body." End quote. In an exact science like astronomy, however, an error like this is intolerable, and is evidence of some flaw in the theory. Some astronomers began to doubt the universality of the law of gravitation on which all these calculations were founded, and to ask if the law did not break down at the boundaries of the solar system. Gradually, the idea dawned on astronomers that perhaps another planet, at a greater distance from the Sun, was attracting Uranus from the predicted path. The problem was, how could this be tested? It was no easy matter to search through thousands of stars along the zodiacal constellations to find a planet. Such a task would be impossible. The only hope of detecting the planet lay in calculating its position from its influence on Uranus. Here was a mighty problem involving great mathematical powers. One of the greatest calculators of the day resolved to grapple with the question, but he died before the discovery was made. Another astronomer intended to investigate the matter, but found it beyond his powers. At length, two investigators in England and France respectively took up the question independently and quite unknown to each other. Adams, a student at the University of Cambridge, noted in his diary in 1841 his resolve to investigate, quote, "the irregularities in the motions of Uranus, which are as yet unaccounted for, in order to find whether they may be attributed to the action of an undiscovered planet beyond it, and, if possible, thence to determine the elements of its orbit approximately, which would lead probably to its discovery." End quote. In 1843, after taking his degree at Cambridge, he commenced his investigation, which occupied him for 2 years. On October the 21st, 1845, he called at Greenwich Observatory and left a paper containing the elements, position, orbit, etc. of the supposed planet, and approximately fixing its position in the heavens, expecting that the Astronomer Royal of England, Sir George Airy, would institute a search for the body. Airy, however, was not particularly interested in this question. He was, above all, what may be called a practical astronomer, and he paid little attention to the paper which the young Cambridge graduate left for his consideration. Adams, too, did not seem particularly anxious to have a search instituted, and the result was that his paper remained in obscurity until it was too late. In 1845, Leverrier, one of the rising astronomers of France, also undertook to solve the problem, and he also assigned the position in the heavens of the disturbing planet in the constellation Aquarius. Sir George Airy happened to see one of the papers in which Leverrier had published his conclusions. He was impressed by the fact that the two independent investigators had reached the same result, and accordingly, he wrote to the director of the observatory at Cambridge, requesting him to search the region of the heavens to which Adams' calculations pointed. The Cambridge astronomer commenced a search, but he had no star maps and had to chart the region of the heavens before he could search for the planet. At length, Leverrier, having completed his investigations, wrote to Encke, director of the Berlin Observatory, requesting him to search for the planet. Encke at once set two of his assistants, d'Arrest and Gall, on the search, with the result that in a few hours, by the aid of some recently published star maps, Gall perceived, almost exactly in the position indicated by Leverrier, a strange star, which was soon identified as the disturber of the motions of Uranus. Thus was the great discovery accomplished, and another planet added to the solar system. The name of the newly found celestial object was more easily settled than that of Herschel's planet. The following extract from the reminiscences of Sir Henry Holland, the well-known physician, tells us of the naming of this distant world. After referring to his visits to foreign observatories, undertaken owing to his great interest in astronomy, he says, quote, "That which most strongly clings to my memory is an evening I passed with Encke and Gall in the observatory of Berlin, some 10 or 12 days after the discovery of the planet on this very spot, and when every night's observations of its motions had still an especial value in denoting the elements of its orbit. I had casually heard of the discovery at Bremen, and lost no time in hurrying on to Berlin. The night in question was one of floating clouds, gradually growing into cumuli, and hour after hour passed away without sight of the planet, which had just come to our knowledge by so wonderful a method of predictive research." Frustrated in this main point, it was some consolation to stay and converse with Encke in his own observatory, one signalized by so many discoveries, the stillness and the darkness of the place broken only by the ticking of the astronomical clock, which, as the unfailing interpreter of the celestial times and motions, has a sort of living existence to the astronomer. Among other things discussed while thus sitting together in a sort of tremulous impatience was the name to be given to the new planet. Encke told me that he had thought of Vulcan, but deemed it right to remit the choice to Leverrier, then supposed the sole indicator of the planet and its place in the heavens, adding that he expected Leverrier's answer by the first post. Not an hour had elapsed before a knock at the door of the observatory announced the letter expected. Encke read it aloud, and, coming to the passage where Leverrier proposed the name of Neptune, exclaimed, "So lass den Namen Neptun sein." It was a midnight scene not easily to be forgotten. A royal baptism, with its long array of titles, would ill compare with this simple naming of the remote and solitary planet thus wonderfully discovered. End quote. Thus closes the record of a remarkable discovery, perhaps the most remarkable ever made in astronomy. The discovery of Neptune was not only a magnificent attack on the secrets of nature, but a glorious triumph of the human intellect. The honor of the discovery is now given equally to Adams and Leverrier, although for some time controversy raged as to which of the two deserved most glory. If Leverrier's results were slightly more accurate than those of Adams, the latter investigator was earlier with his calculations. In this chapter, much space has been given to the history of these two discoveries. In the case of the well-known planets, we know nothing of their discovery, but we have considerable knowledge of their physical condition. In the case of the distant worlds, we know practically nothing of their physical condition, while the story of the two discoveries, the second, the outcome of the first, forms one of the most fascinating chapters in the history of science. Dusky bands resembling those of Jupiter were noticed on the disk of Uranus in 1883 by the late Professor Young. Some astronomers consider that the planet rotates its axis in about 10 hours, but this has not been confirmed by other observers. However, various facts tend to show that its period of rotation must be short. Uranus, so far as is known, is in a condition of great heat. The spectroscope has shown that free hydrogen exists in the Uranian atmosphere, and this indicates the existence of a temperature high enough to separate water into its constituent elements. Observations at the Lowell Observatory a few years ago indicated the existence in the planet's atmosphere of the element helium. Uranus has 4 satellites, known as Ariel, Umbriel, Titania, and Oberon. Of these, the 2 last named were discovered by Sir William Herschel in 1787. Ariel was glimpsed by the astronomer Lassell on 14th September 1847, and Umbriel by Otto Struve a few weeks later. their existence being finally confirmed by Lassel's observations a few years later. The satellites are very faint. Ariel, the nearest satellite, revolves around Uranus in 2 days, 12 hours, at a mean distance of 124,000 miles. Umbriel revolves in 4 days, 3 hours, at a mean distance of 173,000 miles. Titania, at a mean distance of 285,000 miles, revolves in 8 days, 16 hours, while Oberon, at a mean distance of 381,000 miles, requires 13 days, 11 hours to circle round its primary. Nothing is known of the physical condition of these satellites. A remarkable fact connected with them is that they revolve almost at right angles to the plane of the ecliptic, in which most of the planets and satellites move. It is quite possible that there may be other satellites of Uranus yet to be discovered. If little is known of Uranus, less is known of Neptune. The two worlds are about the same size and seem to have many points in common. The spectrum of Neptune has been investigated by various observers who have found it to resemble closely that of Uranus. In 1883, Mr. Maxwell Hall, an astronomer in Jamaica, noticed certain variations of brightness, which he believed indicated that the planet rotated on its axis in about 8 hours. But this observation has not been confirmed. Neptune has one satellite, so far as is known. It was discovered by Lassell on 10th October 1846, only a fortnight after the planet itself was detected. It is situated at a distance of 223,000 miles from its primary, round which it moves in 5 days, 21 hours, 8 minutes. Like the Uranian moons, its motion is retrograde. It must be very large to be visible at all at a distance so vast. Some astronomers consider that it is the largest satellite in the solar system. Probably it is over 3,000 miles in diameter. We have now described the outermost planet of the solar system, revolving in solitary loneliness. But is the orbit of Neptune really the frontier of the Sun's domain? Are there planets beyond Neptune? Astronomical science has not yet answered these questions. The existence of one planet at least has been strongly suspected, and at the present time, 1910, Professor W. H. Pickering is undertaking a search for a world beyond Neptune, the existence of which he believes to be indicated by its influence on the motion of certain comets. It may, however, be many years before such a planet, if it exists, is detected. We have now come to the end of a description of the solar system, proceeding outwards from the Sun. But the planets and their satellites are not the only bodies in the solar system. There exists another class of celestial objects, the cometary and meteoric bodies. To the consideration of these, the next few chapters will be devoted. End of Chapter 12.
Chapter 13 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Andrea Weinman. The Romance of Modern Astronomy by Hector Macpherson. Chapter 13. The Sun's Family of Comets. Of all the celestial bodies, perhaps comets are the most remarkable and the most mysterious. They are totally unlike the planets. Instead of being round, solid globes, they seem to be diffused masses. Instead of revolving round the sun in orbits nearly circular, those comets which have been proved to belong to the solar system move in enormously long ellipses, and are only seen for a brief period when in the vicinity of the sun and the earth. Among the ancients, and indeed in the Middle Ages, comets were a source of terror to mankind, and were regarded as terrible portents of wars, famines, deaths of kings, and other national calamities. A bright comet which appeared in 1066 was supposed to be a portent of the Norman conquest of England. Another, which was seen in 1456, was believed to be connected with the taking of Constantinople by the Turks. In the Middle Ages, it has been remarked every comet was believed to be a ball of fire flung from the right hand of an angry god, and this view was by no means confined to the ignorant. We find Martin Luther and John Knox firmly believing in the direful effects of comets on the Earth and its inhabitants. In the 17th century, an illness among cats in Germany was actually ascribed to the appearance of a comet. In our time, thanks to the advance of science, we know that comets have no effect whatever on the Earth, either baneful or beneficial. Consequently, terror at brilliant comets has given way to wonder and admiration. A bright comet may be said to consist of 3 parts: coma, nucleus, and tail, while faint comets only seen in telescopes generally lack the tail. To the ordinary stargazer, a comet is an object with a tail. But, as a matter of fact, comets with tails are far outnumbered by comets without tails. Little comets which are only seen with the aid of the telescope, and which are consequently unknown to the ancient astronomers. Some comets not only lack a tail, but are also wanting in coma, and appear like round, diffused planetary disks. As was seen in previous chapters, the planet Uranus was at first believed by Herschel to be a telescopic comet, and Ceres, the first discovered of the asteroids, was also taken for a comet. When a comet is first seen in a powerful telescope, or first imprints its image on a photographic plate, it is merely a round, faint nebulosity. As it approaches the Sun, if it is going to be a prominent comet, it develops the well-known tail or tails, for comets have been known with 2, 3, and as many as 6 tails. Comets are of 2 kinds, those which belong to the solar system and those which do not, and in this chapter attention is given to the former class. The scientific study of comets only began about the year 1680, when Sir Isaac Newton, in his investigation of them, demonstrated that they were, like the planetary bodies, subject to the action of the law of gravitation. Newton himself did not prove that any particular comet revolved around the Sun. This was reserved for his friend Halley, who in 1705 stated his conclusions on the subject. Of all the comets which have been seen by the Earth's inhabitants, the most famous is that which bears Halley's name. It was not the brightest seen, nor the most remarkable, but it was the first which was definitely proved to revolve around the Sun. There have been brighter comets, such as Donati's and the Great Comet of 1811, but the chief interest in Halley's comet lies in its regular returns at intervals of 73 or 74 years. In the year 1682, while Newton was busily engaged in testing his law of gravitation, a bright comet made its appearance and was attentively studied by the foremost astronomers of the day. Among these was Edmund Halley, the well-known Englishman, who became the second Astronomer Royal of England. It occurred to Halley that comets possibly revolved round the Sun in orbits similar to those of the planets, and that it would be useful to investigate as to whether a comet had been seen more than once. As Sir Robert Ball says, at the expense of much labor he laid down the paths pursued by 24 of these bodies, which had appeared between 1337 and 1698. Amongst them, he noticed 3 which followed tracks so closely resembling each other that he was led to conclude that the so-called 3 comets could only have been 3 different appearances of the same body. The first of these 3 comets had been seen in 1531, while the second was observed by Kepler in 1607, and the third was the bright comet studied by Halley himself in 1682. The astronomer also noticed that bright comets had been seen in 1456, 75 years before 1531, in 1380, and also in 1305, at intervals of about 76 years. After a careful study of the comet's orbit, and of the effect which Jupiter would have in retarding the return, Halley predicted that the comet would reappear in the end of 1758 or the beginning of 1759. He knew that he himself would be dead long before its return, and he wrote thus: "If it should return according to our predictions about the year 1758, impartial posterity will not refuse to acknowledge that this was first discovered by an Englishman. Posterity has not refused to admit this fact, and the name of Halley has ever since been associated with the comet. The verification of his prophecy reflects a glory on his name which will cause it to live forever among the greatest of astronomers. As the year 1758 drew near, great excitement prevailed among men of science to see whether Halley's prediction would be fulfilled. The astronomer had been dead for 16 years, but nevertheless interest in his prophecy was unabated. The French mathematician Clairaut and 2 other mathematicians undertook the task of calculating the exact date of the comet's return. The outcome of these researches was to show that the attraction of Saturn would delay the return of the comet by 100 days and that of Jupiter by 518 days. Men of science all over the world watched anxiously, and at last on Christmas Day, 1758, the comet was sighted by an amateur, a farmer in Saxony. The comet reached its perihelion, or point nearest to the sun, on March 12, 1759, and then disappeared on its long journey. In 1835, the comet again reappeared, and on November 15, 1835, passed the point of its path closest to the sun. 3 able mathematical astronomers undertook to calculate the exact date of the planet's perihelion passage. Damoiseau, a Frenchman, fixed on November 4, 1835. Pontéculot, another Frenchman, fixed on November 12th. Rosenberger, a German calculator, taking account of the attractions of all the principal planets, fixed on November 11th. The perihelion passage actually took place on November 15th, a proof of the remarkable accuracy of the 3 calculators. In 1835, the comet was first detected at Rome and was particularly studied by Sir John Herschel, who, on May 5, 1836, caught the last glimpse of the comet with his giant telescope. From 1836 to 1873, the comet was on its journey outward, to the most remote point of its orbit beyond the pathway of Neptune. In 1873, it reached its aphelion, as this farthest point is called, and then commenced returning with increasing velocity to the regions of light and heat. In November 1908, plates were exposed in the region of the heavens where it was calculated that the comet would appear, but it was not until September 1909 that it was actually discovered photographically by Dr. Max Wolf of Heidelberg. The comet, in May 1910, was disappointing as a spectacular object to observers in Britain, but the public interest was unprecedented. Halley's was thus the first comet which was proved to revolve round the sun in an elliptic orbit and to be subject to the law of gravitation just as the planets are. Also, of all the known periodic comets, it is the one which has the longest period of revolution. The next comet, ascertained to be also periodic and to be a member of the Sun's family, was an insignificant little object known as Encke's comet. On November 26, 1818, Pons, a French astronomer who devoted much of his attention to the discovery of these objects, detected a small telescopic comet. The German astronomer Encke undertook to calculate the orbit of the comet and found it to be probably identical with comets discovered by the French astronomer Michele in 1786, by Caroline Herschel in 1795, and by Thales in 1805. Encke accordingly found that the time required for the comet to revolve round the sun was 3 years and a half, and he calculated that the comet would pass its perihelion point on May 24, 1822. True to Encke's prediction, the comet returned, and the perihelion passage took place within 3 hours of the time which he predicted. As the late Miss Clerke has remarked, the importance of this event will be better understood when it is remembered that it was only the second instance of the recognized return of the comet, and that it, moreover, establishes the existence of a new class of bodies distinguished as comets of short period. The comet returned again in 1825 and has returned ever since at regular intervals. At its return in 1828, it was actually visible to the unaided eye as a star of the 5th magnitude. In 1838, Encke made a remarkable discovery in connection with his comet. He found that it returned to its perihelion point 2.5 hours before the predicted time. He accordingly put forward the theory that this acceleration of the motion of the comet was due to the existence of what he called a resisting medium in the vicinity of the Sun, too rarefied to retard the motions of the planets, but quite dense enough to make the path of the comet smaller, and eventually to precipitate it on the Sun. This theory was held for a considerable time, but in 1868 the acceleration began to decrease, and accordingly the theory was abandoned. At its return in 1904, the comet was well observed, being comparatively bright. In 1908, however, it was very faint, and the only record of its return in that year was its image on a photographic plate. Mr. G.F. Chambers, in his book The Story of the Comets, gives the number of known short-period comets as 13. The periods of revolution vary from over 3 years in the case of Encke's comet to over 13 in the case of Brorson's. It would require considerable space to describe each of these objects individually. Only some of the more prominent can be mentioned here. In 1843, Faye at the Paris Observatory discovered a comet which was ascertained to revolve round the Sun in an elliptic orbit in over 7 years. Its orbit is the least elliptic of all the short-period comets. It was last seen at its return in 1895, being missed when it reached its perihelion in 1903. In 1884, Dr. Max Wolf discovered at Heidelberg a telescopic comet which was proved to revolve round the Sun in 6 years and 3/4. Before 1875, it is doubtful if the comet was a permanent member of our system, as in that year its orbit was completely changed by the great attractive power of Jupiter. Another remarkable comet was detected in 1892 by Mr. Holmes, an English amateur. Of this comet, Professor Barnard, who carefully studied it with the great telescope of the Lick Observatory, wrote as follows. From several points of view, it was one of the most remarkable comets ever observed. At the time of discovery, it was distinctly visible to the naked eye as a slightly ill-defined star of the 6th magnitude. The remarkable fact that the comet had attained naked eye visibility when discovered, coupled with the further fact that this region must have been repeatedly swept over by comet seekers to within a few days of its discovery, shows that the comet must have rather suddenly attained its conspicuous visibility. The orbit of Holmes' comet is almost circular. Another well-known comet is that known as Brooks' second periodic comet. It was detected in 1889 and returned again to perihelion in 1896. In 1903, it was again observed much fainter than before. Mr. Chambers remarks in connection with this comet, "The steady diminution in the brightness is so marked that it is hazardous to predict its future. At its last return it was only visible in some of our largest telescopes. It is due to return in 1910 and again in 1917. Shall we see it? Perhaps we shall. Perhaps we shall not. But if we do see it on either of these 2 occasions, it will still be leading a threatened life. For in 1921 it will again approach very close to Jupiter, and very likely that may end its career. Or, if not, it will certainly lead to a serious transformation of its orbit." Besides these comets of short period, there are 6 comets of long period. Westphal's revolving round the Sun in 67 years, and which is again due in 1913, Pond's comet, revolving in 70 years, which returned in 1883 and is again due in 1955, De Vico's, revolving in 73 years, which is due in 1919, Olbers, revolving in 74 years, which, first seen in 1815, returned in 1887 and is again due in 1960, Brorson's, with a period of almost 75 years, which is due in 1922, and finally Halley's, already referred to. Thus, it is known that the solar system contains certainly 13 comets of short period and 6 of long period. Besides, it is believed that 14 other comets are also periodic. Their periods range from 5 to 9 years, but they have not been proved beyond a doubt to belong to the solar system. Besides these periodic comets, there are 3, Lexell's Comet, de Vico's Comet, and Biela's Comet, which were once periodic and have now either ceased to exist or have been deflected into new paths. The first named was discovered by Messier, a famous discoverer of comets, on June 14, 1770. An orbit was calculated for it by a Russian mathematician named Lexell, who assigned to it a period of 5.5 years. It was, however, never seen again. Lexell found that in 1707 the comet had passed very close to Jupiter, which had completely altered its path, and accordingly he made another calculation to the effect that the comet should be seen in 1781, but again he was doomed to disappointment. He finally concluded that in 1779 Jupiter had again altered the comet's path by its enormous attraction when the flimsy cometary body again passed near to the giant planet. Lexell's comet has never since been seen. In 1844, a comet was detected at Rome by de Vico, and an orbit was assigned of 1,993 days. The comet, however, was never seen again. The most remarkable case of all was that of Biela's comet, which, after being known for years as a member of the Sun's comet family, disappeared in 1852 and was not again seen. In a future chapter, this comet, which is the key to our knowledge of the nature of these bodies, will be fully discussed. The comets above mentioned are those which belong to the Sun's system. The great majority of comets with which the next chapter deals have not been proved to belong to our system, and many of them seem to be only visitors from the depths of space. End of chapter 13.
Chapter 14 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Wayne Cooke. The Romance of Modern Astronomy by Hector Macpherson. Chapter 14. The Messengers of Space. The previous chapter dealt with those comets which are known to belong to the solar system, and which are thus always subject to the influence of the sun. In the present chapter, attention is directed to the large comets, which are either visitors to the solar system from the depths of space, or which, if they do revolve around the sun, move out to distances so enormous that we cannot with certainty pronounce them to be members of the sun's family. Many of the most famous comets which have ever appeared belong to these two classes. Some of the comets contained in the second class probably belong to the solar system, but their periods are so long that astronomers do not know whether or not they will ever return. For instance, the second comet of 1824 has been calculated to have a period of millions of years. The first comet of 1863 has been said to revolve in nearly 2 million years, the comet of 1680 in over 15,000 years, and so on. But no one can implicitly trust these estimates, as much uncertainty surrounds them. Such comets might, in their long journeys in space, be attracted from their paths by dark stars or meteor streams, and would thus be lost forever to the solar system. They cannot be regarded as permanent members of the solar system. Most of the really grand comets which have been seen, with the exception of Halley's Comet at its appearances, have belonged to either of these two classes. The comet of 1264, a magnificent object which was supposed to have been identical with the comet of 1556, was expected on this supposition to return about 1858. But it was not seen again, and consequently it is doubtful if the two comets were really identical. In 1264, popular superstition fixed on the comet as a presage of the death of Pope Urban IV. A remarkable comet, known as Deschezos' comet, appeared in 1744. It had no fewer than 6 tails. Deschezos, the discoverer, has left a very detailed description of the object. He wrote as follows: "The sky was quite overcast from the 1st to the 7th of March, but on the last named day the clouds became broken and gave us some hope of seeing the comet's tail. I was preparing myself for seeing over again just about what I had seen during the closing days of February. At 4 o'clock on the morning of March 8th, I went downstairs with a friend into the garden with the east facing us. This friend, walking in front of me, startled me by saying that instead of 2 tails there were 5. I hardly believed him, but after having paused from behind several buildings which had partly concealed the eastern horizon from me, I did indeed see 5 tails. Besides these 5 tails, there was a 6th. This was probably one of the most remarkable comets ever witnessed. The great comet of 1811 was in many ways unique. Discovered on 26th of March, 1811, it was last seen on August 17th, 1812, nearly 17 months later. The tail, when seen at its best in the middle of October, stretched into space for the distance of 100 million miles, while its breadth was 15 millions. Measurements made by Herschel indicated that the diameter of the nucleus of the comet was 428 miles. A famous German astronomer calculated its orbit and estimated that its greatest distance is 14 times that of Neptune, and its period over 3,000 years. Another magnificent comet appeared in 1843. This was described as a grand and wonderful sight for the extraordinary distance of 1/3 of the heavens, the nucleus being perhaps about the size of the planet Venus. This remarkable comet, one of the brightest which has ever been seen, was detected in the end of February 1843 in the southern hemisphere. After the middle of March, the comet became visible in the northern hemisphere. The remarkable feature about the comet of 1843 was its near approach to the sun. Its central portion was within 78,000 miles of the orb of the day, so that only a little over 30,000 miles separated the surface of the sun and the comet. The result of this near approach was that the comet whirled past its perihelion point at the amazing rate of 366 miles per second. In 2 hours and 11 minutes, it described half of the curvature of its oval-shaped orbit, while, as one astronomical writer has pointed out, in traveling over the remaining half, many hundreds of sluggish years will doubtless be consumed. In many ways, the comet of 1843 was a remarkable object. Its tail streamed into space for 200 millions of miles. The next brilliant comet was detected by Donati at Florence on June 2, 1858, as a little round nebulous mass, very faint, in the constellation Leo, and is considered by most astronomers to have been the grandest comet of the 19th century. At first, no one suspected that the faint little telescopic object would develop into so magnificent a stellar spectacle as the comet of Donati. In the middle of July, a nucleus developed. In the middle of August, a tail began to make its appearance, and by the beginning of September, it was visible to the unaided eye. By the 12th of that month, the nucleus of the comet shone with a brilliance equal to that of the pole star. From this date, a magnificent celestial spectacle was assured. Occupying a favorable position in the northern heavens, it was in a most famous position for observation. This comet, as Mr. G. F. Chambers has pointed out, has not often been equaled in the intense brilliance of its nucleus, and the unusual and, so to speak, artistic configuration of its tail, which features the absence of the moon in the early part of October, enabled spectators to view to the very best advantage. The passage of the comet in front of Arcturus on October 5th will ever remain treasured in the memory of those who saw it. The late Miss Clark confirms this estimate. She says, "The most striking view was presented on August 5th, when the brilliant star Arcturus became involved in the brightest part of the tail, and during many hours contributed, its luster undiminished by the interposed nebulous screen, to heighten the grandeur of the most majestic celestial spectacle of which living memories retain the impress. The comet was followed by astronomers until March 4, 1859, when it disappeared from view of the largest telescopes then in existence. Various estimates have been made of the period, such as 1,879 years, 2,040 years, and 2,138 years. One calculation suggested that Donati's comet was identical with a famous comet which appeared in 146 BC and is mentioned in the Chinese annals. But the periods calculated are very uncertain. Estimates, probably correct, have been made of the dimensions of the nucleus and the tail of the comet. The tail was 14 million miles long on 30th August, and seems to have reached its maximum length on 10th October, when it streamed outwards into space for 51 million miles. On the same day, the nucleus was estimated at 630 miles in diameter. The comet was carefully studied by astronomers on both sides of the Atlantic. Good weather prevailed during its nearest approach to the Earth, and consequently it was thoroughly and exhaustively studied. 3 years later, another brilliant object, perhaps even more remarkable than Donati's comet, became visible to the Earth's inhabitants. It was discovered on May 13, 1861, in New South Wales, and on 11th June passed its perihelion point. On 29th June it became visible in the northern hemisphere. The following description were given by Sir John Herschel, who observed it from Hawkhurst in Kent. The comet, which was first observed here on Saturday night, June 29th, by a resident of the village of Hawkhurst, became conspicuously visible on the 30th, when I first observed it. It then far exceeded in brightness any comet I have before observed, those of 1811 and the recent splendid one not excepted. Its total light certainly far surpassed that of any fixed star or planet, except perhaps Venus at its maximum. The remarkable fact about the great comet was that on the night of 30th June, the Earth and the Moon passed through its tail. The comet was at the time between the Earth and the Sun, 14 million miles from our planet, while its tail stretched outward for 15 millions of miles. The passage of the Earth through its tail was almost imperceptible. The vast majority of persons never knew that such an event had taken place, and even the astronomers noted only a singular phosphorescence in the sky. Lowe, a meteorologist of the day, remarked that the sky had a yellow aural aspect, and that the sun gave but feeble light, although the sky was cloudless, and at 7 o'clock in the evening, although it was the midsummer season, artificial lights had to be used. The fact that our world passed through its tail, and that the inhabitants were unaware of the fact, is the strongest proof of the harmlessness of this large comet. The comet of 1874, discovered by a French astronomer named Kotzer at Marseille on 17 April 1874, and since known by his name, was much less brilliant than its predecessor in 1861, but nevertheless was a fine celestial spectacle. In July it became visible to the unaided eye. On the 21st of that month it was at its nearest point to the Earth, a distance of 9 millions of miles. Various estimates have been made of the period in which the comet revolves. One calculation assigned the period of 5,711 years, another a period of 10,455 years. The comet of 1880, seen in the southern hemisphere only, was one of the most remarkable cometary bodies. In appearance, it was very similar to the great comet of 1843, and when its orbit was calculated, it was found to revolve in a path almost identical to that famous body. 3 of the most distinguished calculators investigated the comet's motions independently, and each found the path of the two bodies almost identical. 2 years later, another great comet was discovered by the director of the observatory at Rio de Janeiro. It soon became a magnificent object in the southern hemisphere. Sir David Gill, who observed it from the Cape Observatory, remarked that the comet showed an astounding brilliancy as it rose behind the mountains on the west of Table Bay, and it seemed in no way diminished in brightness when the sun rose a few minutes afterwards. It was only necessary to shade the eye from the direct sunlight with the hand at arm's length to see the comet with its brilliant white nucleus and dense white, sharply bordered tail of quite half a degree in length. The comet passed between the Earth and the Sun on the 17th September, and on the following day was visible in full sunlight close to the orb of day. In Spain it was seen through a passing cloud when very close to the Sun. The most remarkable feature of this great comet was the fact that its orbit showed a remarkable resemblance to the great comets of 1843 and 1880. Astronomers were amazed at this discovery. It was at least possible that the comet of 1880 was a return of that of 1843, but for an enormous comet to return in only 2 years was unthinkable. As the late Miss Clark remarked, "A comet with a single passage through the Sun's atmosphere encountered sufficient resistance to shorten its period from 37 to 2 years and 8 months must in the immediate future be brought to rest on its surface." The great comet was kept under observation for about 6 months, but before it disappeared, the opinion was widespread that it was not a return of the comets of 1843 and 1880. In 1887, another comet was discovered with an orbit also similar. Now, the only explanation of the identity of these orbits is that each of these comets were fragments of a larger cometary body which, revolving in the same orbit, had been gradually disrupted into a number of different comets. The comets of 1668, 1843, 1880, 1882, 1887, and probably also another comet seen in 1882. This is proof that comets, unlike the planets, are not lasting, that they are liable to be dissipated into space. This much may be gathered from a study of the movements and orbits of comets. Much more remarkable, however, is the information gained by a study of their physical conditions. After 1882, no very brilliant comets was visible in the northern hemisphere, although in 1901 another bright southern comet was observed. In 1902, Perrine's comet was faintly visible to the unaided eye, but too faintly to attract popular attention. The appearance of the great daylight comet of 1910 came therefore as a pleasant surprise not only to astronomers but also to the general public. On January 15, 1910, the Johannesburg newspaper, The Leader, informed Mr. Innes, director of the Transvaal Observatory, that they had received the following telegram from the station master at the railway station at Kopjes in the Orange Colony. "Halley's comet was seen by Fireman Burke, driver Tucker, and guard Moraes at 4:45 rising in front of the sun. It was visible for about 20 minutes. The railway employees had seen the brilliant object in the sunrise before the astronomers saw it, and they thought it was Halley's comet, which was due to return at that time. As soon as the comet was observed, however, it was seen that it could not be Halley's. Warned by this message from the station master, we kept watch on the next morning, but it was cloudy. This morning, January 17th, was also cloudy, but there was a break just above the place of sunrise. At 5:29 Standard Time, the comet was seen." In a later statement, Mr. Innes said, "The earliest date on which this comet was seen in South Africa appears to be Thursday, January 12th at 14 hours 25 minutes Greenwich Mean Time by some workmen at the Transvaal Premier Diamond Mine. A letter from Cullinan, dated January 16th, informed me that on that date, and also on Friday morning, several workmen observed the comet." The comet soon passed the sun and became visible in the evening skies, a magnificent object which attracted much attention. And had it not been for the unfavorable weather in Great Britain at the time, a good deal more would have been seen of it. On the clear evenings, the comet was observed and admired by the average man and closely studied by the astronomer. The comet was observed by the present writer at Balerno, Midlothian, on January 22nd and 29th, observations on other dates being impossible owing to the unfavorable weather. Seen in a 2-inch refractor on January 29th, the nucleus was very bright and well defined, while the head presented a resemblance to drawings of Coggia's comet of 1874. Even at the large observatories, it was difficult to get good photographs, owing to its position in the western sky so close to the sunset twilight. The spectrum of the comet was observed by Professor Frost, director of the Yerkes Observatory, on January 24th, when the bright lines of sodium characteristic of many comets were noted. The element cyanogen was also detected. The spectroscopic observations indicated that on January 27th, the comet was receding from the Earth with a considerable velocity. This agrees with its very rapid diminution in brightness. On January 29th, it was well seen. A few days later, it was practically invisible. The lines addressed to the Stranger of Heaven, the great comet of 1811, by the Ettrick Shepherd, seemed specially appropriate to the comet of 1910. Stranger of heaven, I bid thee hail, shred from the pall of glory riven, that flashest in celestial gale, broad pennon of the King of heaven. Whate'er portends thy front of fire and streaming locks so lovely pale, or peace to man, or judgment dire, stranger of heaven, I bid thee hail. End of chapter 14.
Chapter 15 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Isaac Janney. The Romance of Modern Astronomy by Hector Macpherson. Chapter 15. The Nature of Comets. In the 2 previous chapters, mention was made of the 2 principal classes of comets. Comets which have been proved to belong to the solar system, and those comets which either belong to our system, revolving in uncertain periods, or only pay a fleeting visit to the planetary regions, dashing away again into space. Although these 2 classes differ in many respects, they only differ in regard to their orbits. That is to say, all comets, whether they belong to the solar system or not, are alike in their constitution and nature, and in this chapter, an attempt will be made to explain the complicated phenomena connected with them. The most striking feature about a bright comet is its tail. As remarked in a previous chapter, telescopic comets are often devoid of tails, but all bright comets are distinguished by these appendages, and consequently, to the average man and the casual stargazer, a comet is only of interest if it possesses a tail. One of the most notable things about the tails of comets is that they are always pointed away from the sun. If the comet is approaching the sun, the tail follows the head. If it is receding from the sun, the head follows the tail. This is a remarkable fact, which shows that comets lack the stability which characterizes the planets. For many years, this fact puzzled astronomers, and it was not until the beginning of last century that any progress was made towards an explanation. The astronomer Olbers of Bremen, well known for his discovery of the asteroids, explained the tails of comets very simply. The sun not only attracts comets and planets to itself, but its light exercises a repulsive power on minute particles, which are thus driven off in a direction opposite to the sun. This theory was very fully elaborated by a famous Russian astronomer, the late Professor Bredikhin. Bredikhin's researches led him to divide the tails of comets into 3 types. The first of these consists of long straight tails, pointed directly away from the sun, represented by the tails of the comets of 1811, 1843, and 1861. In the second of these types, represented by those comets bearing the names of Donati and Coggia, the tails, although on the whole pointed away from the sun, are considerably curved. The tails of the third type have been described as short, strongly bent, brush-like emanations, which, in bright comets, seem to be only found in combination with tails of the higher classes. He showed that, probably, tails of the first types are formed of hydrogen, those of the second of hydrocarbon, and those of the third of iron. with a mixture of sodium and some other elements. On the whole, this theory is considered satisfactory. The question, however, presents itself: what is this remarkable repulsive force? There seems to be a general agreement among the scientists that the force is electrical. It only affects the very smallest and most insignificant particles of matter. And this explains why the planets and the solid bodies are not affected by the force. It has also been suggested that the repelling force may be due to what is called light pressure, the action of rays of light on very minute particles of matter. So much has been learned of the nature of comets by theory. Most of our knowledge of these objects, however, is due to direct observation. The invention of the spectroscope, about the middle of the 19th century, referred to in a previous chapter, resulted in a considerable increase of our knowledge of comets and cometary phenomena. It was shown early in the history of this line of research, by Donati and others, that the light of comets is partly inherent and partly reflected. The late Sir William Huggins, the late Dr. Copeland, and others ascertained the existence in the heads of comets of hydrocarbon gas, and this has been since confirmed by other observers. These observations, of course, give support to Bredikind's theory of comets' tails. In 1882, this theory was still further confirmed by observations which the late Dr. Copeland and others made of Wells' comet of that year. On May 27th, Copeland ascertained the existence of sodium in the comet. This was the first occasion on which that element was recognized in one of these bodies. The same astronomer also recognized sodium in the Great Comet of 1882. A comet which contributed materially to our knowledge of cometary phenomena was that discovered on September 1, 1908, by Morehouse, an American astronomer. Observations on this object revealed the presence of the poisonous gas cyanogen, which was indeed the most prominent element in the comet, and which dominated its spectrum. Other remarkable disclosures were made by this comet. A large number of photographs were taken at the Goodsill Observatory, Minnesota. Professor H.C. Wilson of that institution remarks as follows on this comet. While the observer was guiding the telescope for these photographs, the portion of the comet's tail which was in the field of the guiding telescope grew visibly fainter, and appeared to detach itself from the head. The two photographs taken with the 6-inch camera show that this appearance was real, and that the bright part of the tail was actually detached from the head of the comet and was moving outward. On October 15, a bend became apparent in the main tail, which photographers showed to be traveling rapidly from the head. This outward motion, says one observer, was also traceable in the case of several knots of brightness in the tail. Morehouse's was not the only comet which was observed to break up. The Great Comet of 1882 was also seen to throw off portions of its mass. A German astronomer noted on 5th and 7th October of that year 2 centers of condensations in the comet, while on the 9th of the same month, Schmidt detected a little nebulous object close to the comet, which had been apparently thrown off. Professor Bernard, some days later, glimpsed 6 or 8 little cometary masses separate from the comet. Another instance of cometary disruption was afforded by Brooks' second periodic comet, discovered in 1889. About a month after its discovery, it was seen to have thrown off 4 fragments. In his interesting work on comets, Mr. Chambers writes as follows: 2 of these were faint and soon disappeared, but the other 2 brighter ones were miniatures of the main body, each having a nucleus and a tail. For a while, these moved away from their primary. In 3 weeks, the nearer companion ceased to recede. It then expanded and finally disappeared. The fainter companion continued to recede until it had become, a month from discovery, brighter than the parent comet. In another month, it began to approach its parent, its head swelling and becoming faint, the tail disappearing. It is probable that astronomers have learned more of the constitution and nature of comets from one small member of the Sun's family than from all the other comets, periodic and non-periodic, put together. On February 27, 1826, Wilhelm von Biela, an amateur astronomer at Josephstadt in Bohemia, detected a faint comet which was independently noticed 10 days later by a French observer, Gambart, at Marseille. When its orbit was calculated, it was found to be identical with those of comets which appeared in 1772 and 1805. The comet turned out to be a periodic one, revolving round the Sun in a period of between 6 and 7 years. Its return was predicted for 1832, and true to calculation, it reappeared in that year. Its reappearance was made the occasion of a comet scare. Certain calculations were made which seemed to show that portions of the comet would sweep over part of Earth's orbit. This statement gave rise to a dread lest the comet should strike the Earth and our world be destroyed. A panic ensued among the ignorant, especially in Paris, and the popular excitement was not cooled until the director of the Paris Observatory announced that the Earth and the comet would at no time approach within 50 million miles of each other. The comet was not seen in 1839, owing to its unfavorable position in the heavens, but on November 28, 1846, it was rediscovered. In less than a month, it was seen to be pear-shaped, and on December 29, and early in January, it was found that the comet had actually separated into two distinct portions. All over the world, astronomers observed the comet with amazement, for this was the first occasion within the memory of man on which a comet was seen to divide into two portions. The comet again returned in 1852. The companion comet was again seen, but at a much greater distance. It was now 1.25 million miles from its primary, 8 times its distance in 1846. In 1859, the comet was not observed, but this was not considered remarkable, as it was in that year unfavorably placed for observation. However, much interest was displayed at its return in 1866, at which date it was expected to be very favorably placed. An active search was instituted, but neither Biela's comet nor its little companion was seen. The comet was obviously lost, and astronomers gave up hope of ever seeing it again. But an extraordinary thing happened. The comet was again due to appear in 1872. It was not visible, but when the Earth crossed its path, on the night of November 27, there was a magnificent shower of shooting stars. Beginning shortly after sunset, the rain of fire, as one observer called the display, lasted until 11 o'clock. 400 meteors were counted in a minute and a half, and some magnificent fireballs equal in size to the apparent diameter of the moon were observed. The Earth had not collided with Biela's comet, but it was plowing its way through the wreckage and debris into which the comet had dissolved. A German astronomer, Klinkerfues, observing at Göttingen, was impressed with the idea that Biela's comet, or at least a portion of it, might still be visible, and concluded that if it were to be seen at all, it would be in the southern hemisphere, in the opposite region of the heavens from the point from which the meteors had radiated. Accordingly, convinced that the meteors represented the shattered debris of the comet, and believing that other portions of it might still be in existence, he telegraphed to Pogson, the astronomer at Madras, the following message: Biela touched Earth November 27. Search near Theta Centauri. Pogson promptly turned his telescope to that portion of the sky and glimpsed on December 2, and again on the following evening, a very faint object, which he at first took for Biela's comet or its companion. It was shown, however, that it could not have been either, but was probably another fragment which was detached at an earlier date. The orbit of Biela's comet was thus shown to be identical with the meteoric shower known as the Andromedids, and another fine shower was observed in 1885, when the Earth again crossed the path of the lost comet. Biela's comet therefore no longer exists. It has been dissolved into fragments. And with some of these fragments, our planet collided on November 27, 1872, with the result that a display of celestial fireworks took place, which has seldom been surpassed. Thus, we see that comets die, as Kepler said 3 centuries ago. Unlike the planets, they are not lasting, but break up into small particles of matter, which, when they enter our Earth's atmosphere, become ignited with the friction of the atmosphere and appear in the form of shooting stars. To sum up, we know that comets are bodies of extreme tenuity. Stars are usually to be seen shining through them undimmed. And although they are of enormous bulk, they have practically no weight. That is to say, they exercise no disturbing influences on the motions of the planets. In all these points, comets differ from planets, and as already mentioned, there is another important point of difference. Although nothing in the changing universe can be called eternal, the sun and the planets are certainly lasting bodies, but comets are not lasting. Even in the short period of man's life, comets have been seen to break up and disappear. An admirable summary of our knowledge of comets is given by Mr. E. W. Maunder as follows. Though the bulk of comets is huge, they contain extraordinary little substance. Their heads must contain some solid matter, but it is probably in the form of a loose aggregation of stones enveloped in vaporous material. There is some reason to suppose that comets are apt to shed some of these stones as they travel along their paths, for the orbits of the meteors that cause our greatest star showers are coincident with the paths of comets that have been observed. But it is not only by shedding its loose stones that a comet diminishes its bulk. It also loses through its tail. As the comet gets close to the sun, its head becomes heated and throws off concentric envelopes, much of which consists of matter in an extremely fine state of division. Mr. Maunder goes on to show that for a particle of matter less than 1/25,000th part of an inch in diameter, the repulsive force of the sun's light is greater than the attraction force of the central orb itself. Particles in the outer envelope of the comet below this size will be driven away in a continuous stream, and will form that thin, luminous fog which we see as the comet's tail. Thus, comets lose in bulk and mass through their heads and their tails. Of the subsequent history of the luminous fog, driven off by the repelling power, we know nothing. But of the loose stones shed by the head, we know a great deal. To a consideration of these loose stones, the next chapter will be devoted. End of chapter 15.
Chapter 16 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Kayla Solpizio. The Romance of Modern Astronomy by Hector Macpherson. Chapter 16. The Shooting Stars. Scarcely a night passes without the recurrence of a celestial phenomenon familiar to the most casual stargazer. As Flammarion puts it in his picturesque language, sometimes when night has silently spread the immensity of her wings above the weary earth, a shining speck is seen to detach itself in the shades of evening from the starry vault, shooting brightly through the constellations to lose itself in the infinitude of space. These shining specks are known variously as shooting stars, falling stars, and meteors. The latter term is the most scientifically accurate, because the shining specks are not stars, while the so-called fixed stars are huge globes, some exceeding the sun in size at enormous distances from the earth. The shooting stars are merely little stones and particles of matter a few miles above the surface of our planet. It must always be borne in mind, therefore, that the titles shooting stars and falling stars are incorrect, and that it is more accurate to refer to these objects as meteors. Scarcely a night passes without one or more of these meteors being seen. During the day, too, there are probably as many entering our atmosphere and flashing across the sky as at night, but owing to the sunlight, they are unobserved. It has been calculated that every 24 hours, the dust of 400 million meteors falls to the surface of the Earth. On most evenings, meteors are observed in twos or threes. On some evenings, more are to be seen than on others. On some occasions, however, these meteors are to be seen not in twos or threes, but in dense showers. In 1799, for instance, a bright shower of meteors was observed in South America by the famous Humboldt. On the night of November 12th through the 13th, 1833, there were observed perhaps the finest display of shooting stars ever witnessed by man. It was best seen in North America, and during the maximum it was quite impossible to count the number of meteors which flashed across the sky. It was estimated that their frequency was about half that of snowflakes in an ordinary snowstorm. It was calculated, in fact, that no fewer than 240,000 meteors were visible. Observations made on that memorable occasion showed that the paths of all the meteors traced backwards in the sky, intersected at a point in the constellation Leo. That is to say, the meteors radiated from a point in that star group. Hence, this point was called the radiant point, and the star shower was called the Leonid display. On the occasion of this great display, the meteors struck terror into the hearts of the ignorant, especially the Negroes on the plantations in the southern states, who believed the end of the world to be at hand. The fact that 34 years had elapsed since the magnificent star shower led astronomers to expect another display about 1866 or 1867. An American astronomer, the late Professor H.A. Newton, undertook a search through the ancient records to see if he could find traces of star showers at intervals of 33 or 34 years. His search was successful, and he predicted a star shower on the evening of November 13th and morning of November 14th, 1866. At the same time, it was noted that meteors were to be seen yearly in varying quantities, radiating from the same point in Leo. Professor Newton's prediction was fulfilled. On the evening of November 13th, there was a magnificent display of meteors, inferior, it is true, to that of 1833, but still magnificent. In his book, In Starry Realms, Sir Robert Ball has given an excellent account of this fall of meteors, which he observed from Lord Rosse's observatory, Birr Castle, Ireland, where he was at the time employed as astronomer to that nobleman. The memorable night, says Sir Robert Ball, was a very fine one. The moon was absent, a very important consideration in regard to the effectiveness of the display. The stars shone out clearly, and I was diligently examining some faint nebulae in the eyepiece of the great telescope, when a sudden exclamation from the attendant caused me to look up from the eyepiece, just in time to catch a glimpse of a fine shooting star, which, like a great skyrocket, but without its accompanying noise, shot across the sky over our heads. About this time I was joined at the telescope by Lord Oxmantown, afterwards Earl of Ross, and we resumed our observations of the nebulae, but a grander spectacle soon diverted our attention from these faint objects. The great shooting star, which had just appeared, was merely the herald announcing the advent of a mighty host. At first the meteors came singly, and then, as the hours went on, they arrived in twos and in threes, in dozens, in scores, and in hundreds. Our work at the telescope was forsaken. We went to the top of the castellated walls of the great telescope and abandoned ourselves to the enjoyment of the gorgeous spectacle. To number the meteors baffled all our arithmetic. While we strove to count on one side, many of them hurried by on the other. The vivid brilliance of the meteors was sharply contrasted with the silence of their flight. In 1867, another shower, much feebler than that of 1866, was seen, and as the years passed on, the display became fainter, until the number of meteors seen on the particular night in November was normal. A display was predicted for 1899, in accordance with the 33-year period, but, to the great surprise and disappointment of astronomers, nothing was seen. In 1900, there was no better success. In November 1901, there was a fairly good shower observed in America, but vastly inferior to those of 1833 and 1866. Finally, in 1904, there was a fairly good display visible in Scotland. The writer observed the display at Balerno, in mid-Lothian, and noted a considerable number of bright meteors. The shooting stars were not numerous, but they were brilliant, and, in short, the display was much above the normal. Since 1904, the November meteors have been few, about the usual number being observed. There is another well-known shower of meteors. This is the Perseids, so called from the fact that the meteors appear to radiate from the constellation Perseus. These are to be seen in varying numbers between the 9th and 11th of August every year. Unlike the Leonids, they have no well-defined period of greatest number and brilliance. Other two important showers are known, the Lyrids, seen in April, which appear to radiate from Lyra, and the Andromidids, which are to be seen towards the end of November. Many minor showers are known, but they are too faint and insignificant to attract general attention. When it was found that the Leonid meteors reached a maximum every 33 years, astronomers sought for an explanation of this remarkable fact. Professor Adams, one of the discoverers of Neptune, showed that these minute Leonid meteors revolved around the Sun in a well-defined orbit in a period of 33 years, and that the orbit intersected that of our planet. It thus became apparent that meteors were distributed all around the orbit, but that there was a main swarm where the meteors were closely crowded together, and which, when crossing the Earth's orbit, was plowed through by our planet on its journey around the Sun. The failure of the main swarm to encounter the Earth in 1899 was a source of much difficulty to astronomers. However, the general opinion seems to be either that the swarm has become greatly worn out and extended along its orbit, or else that it was slightly deflected from its path by the action of some of the planets. The most remarkable feature of the November meteors, however, was disclosed in 1866 by Professor Schiaparelli. Having calculated the orbit of the meteors, he was impressed by its identity with the orbit of a comet, known as Tempel's Comet, which revolves around the Sun in 33 years and which was seen in 1866. Then, investigating the orbit of the August meteors, he found it to coincide with that of a bright comet which appeared in 1862. Finally, there came the discovery that the lost comet of Biela traveled in the same orbit as the Andromedids. Thus it was shown that the shooting stars so familiar to the Earth's inhabitants, and so long a mystery, were nothing less than the appendages of comets. Professor Schiaparelli says, "The meteoric currents are the products of the dissolution of comets, and consist of minute particles, which certain comets have abandoned along their orbits by reason of the disintegrating force which the Sun and planets exert on the rare materials of which they are composed." There must be thousands of these meteoric currents in the solar system, and large numbers must cross the orbits of the other planets and encounter the various orbs. The result of this is that the Earth and the other planets are gradually increasing in size, owing to the constant fall of meteoric matter. None of the ordinary shooting stars, of course, reach the ground whole. They are reduced to dust, which falls imperceptibly to the surface of the Earth. There is another class of much larger meteoric bodies, and numbers of them fall to the ground without being reduced utterly to vapor. These are known variously as uraanoliths, bolides, and aerolites. From ancient times, there were traditions of the fall of stones from the sky, but it was not until 1803 that men of science came to believe in such phenomena. In that year, an aerolite fell at L'Aigle, in the department of the Orne in France. A great aerolite, moving from southwest to northeast, perceived at Alencon, Caen, and Falaise, suddenly exploded with a frightful noise, and a number of meteoric stones, of which the largest weighed 20 pounds, were thrown to the ground and were picked up still smoking. On July 23, 1872, on a beautiful summer's day, an aerolite fell in France after a tremendous explosion which was heard for 50 miles round. It weighed no less than 126 pounds, and, by the force of its fall, dug a hole over 5 feet in depth. In April 1873, another great bolide fell near Rome. It had a velocity of 37 miles, a second on arrival in the Earth's atmosphere, and it was shattered to fragments. At Raiynn in Shropshire, on April 20th, 1876, a piece of iron fell and buried itself in a field. When dug out, it was still hot. This, which is known as the Raiynn siderite, is now preserved in the British Museum. In 1881, a stone weighing 3 pounds fell in Yorkshire on the railway line and made a hole 11 inches deep. On November 23, 1877, a meteorite exploded with a loud report over the town of Chester. A famous meteorite, which did not fall to the ground as a solid mass, was seen in December 21, 1876, in Kansas. It is thus described by Professor Howe, an American astronomer: "A superb fireball appeared over the state of Kansas, and moved thence eastward south of Chicago, across Indiana, over Lake Erie, to Lake Ontario, where it disappeared. When nearly 200 miles from Bloomington, Indiana, the meteor burst, and the inhabitants of that city saw a magnificent array of fireballs sweeping through the evening sky. After the excitement aroused by the marvelous spectacle was over, there came a tremendous crack, like the reverberations of thunder. The concussion which accompanied it led some to think that a light earthquake had shaken the town. How terrific must a detonation have been, which was so startling 200 miles away, after the sound waves had been on their journey a quarter of an hour. There has been much controversy among the astronomers as to the exact nature of these aerolites and fireballs. Laplace suggested about 100 years ago that they might have been ejected from the volcanoes on the moon. But this theory was soon abandoned, as was also a suggestion that they were ejected from the sun. Sir Robert Ball and a number of other astronomers believed that these aerolites were ejected many ages ago by the volcanoes on the Earth's surface, then much more powerful and active than at present, and that they, having once been thrown out from our planet, would intersect the terrestrial orbit at each revolution. The alternative theory, supported by Professor Schiaparelli, Sir Norman Lockyer, and others, regards aerolites as simply larger members of meteor swarms, fragments of comets. This is confirmed by the fact that chemists have made analysis of the elements in these bodies raised to incandescence, and the presence has been detected by hydrocarbons, present also in comets. On the other hand, it is remarkable that, with one exception, an aerolite was never seen to fall to the ground during a meteoric shower. The exception took place on November 27, 1885, when during a shower of Andromedan meteors, a large bolide weighing more than 8 pounds fell at Mazapil in Mexico. Whether it was connected with the showers is not known. The study of meteors has made great progress within the last 30 years, thanks mainly to the work of a single observer, Mr. W. F. Denning of Bristol, the well-known English amateur astronomer. From 1872 to 1903, Mr. Denning determined the radiant points of 1,172 meteor showers. In addition, he published in 1899 a catalogue of the radiant points of meteors numbering 4,367. Thanks to Mr. Denning's work, the observation of meteors is a recognized branch of astronomy, and may be studied by anyone who is interested in the subject and can make good observations. A word may be said here of a phenomenon closely allied to the subject of meteors, the zodiacal light. This is a phenomenon which is much better seen in tropical than in temperate regions, but it is occasionally observed in Europe. A pearly glow is observed in the spring to spread over a portion of the sky just where the sun has disappeared. In autumn, the same thing is also to be seen before sunrise. It is in tropical regions, however, that it is seen in its full glory. Instead of being seen like a cone, as in temperate regions, it appears as a band of light. The portions nearest to the sun are equal to the Milky Way in brilliance, while the more distant parts are much fainter, and are only visible owing to the clearness and purity of the atmosphere in the tropics. The exact nature of the zodiacal light has long been more or less a mystery, but it seems to be generally believed among astronomers that the light is due to diffused dust, probably meteoric matter forming an outer appendage to the sun. Opposite in the heavens is a much fainter phenomenon, generally known by its German name of the Gegenschein, or counterglow, probably also of meteoric composition. Our survey of the solar system commenced with the infinitely great, the mighty orb of the sun itself, and it is fittingly closed with the description of the infinitely little, the minute particles of cosmical dust which move round the central orb in obedience to the law of gravitation. End of Chapter 16.
Chapter 17 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. The Romance of Modern Astronomy by Hector Macpherson. Chapter 17. Eclipses and Transits. In previous chapters, a brief survey has been made of the solar system, the Sun and its family of planets, and the comets and meteoric swarms. But before passing to a consideration of the vast universe outside of the solar system, it is well to consider the phenomena which arise from the movements of the various planets and the inclination of their orbits round the Sun. These facts give rise to the two classes of kindred phenomena known as eclipses and transits. We cannot properly understand the cause of the periodic occurrences known as eclipses until we fully realize the fact that every body shining by reflected light casts a shadow into space in a direction opposite to the source of the illumination. Thus, the Earth casts a shadow, and the Moon casts a shadow. Similarly, Mars, Jupiter, Saturn, Venus, and the other planets cast shadows. But it is the shadows of the Earth and the Moon which cause the phenomena known to Earth's inhabitants as eclipses of the Moon and eclipses of the Sun. The Earth casts a shadow into space, and when the Moon, the Earth, and the Sun are in a line, with the Earth in the center, the shadow of the Earth, which extends to and beyond the orbit of the Moon, is thrown in the direction of our satellite. If the Moon's orbit were exactly in the same plane or level as that of the Earth, our satellite would pass at every revolution through the shadow. In other words, the moon would be totally eclipsed and would become altogether invisible every time it reached the full phase. As a matter of fact, however, the moon's orbit is not exactly in the same plane as that of the Earth, and it is only occasionally that an eclipse does take place. Sometimes an eclipse of the moon is total, that is to say, the moon is completely immersed in the Earth's shadow, and sometimes only partial, a portion of the moon's disk remaining outside the true shadow. A total eclipse of the moon is a very striking and beautiful phenomenon. As the moon becomes more and more immersed in the shadow, the illuminated portion becomes smaller and smaller until it completely disappears. The moon is not, however, usually totally invisible. It generally assumes a dark copper-colored hue, caused by the refraction of sunlight through the atmosphere of the Earth. This is believed to be due to the fact that the blue rays of the sun are absorbed in passing through the atmosphere of the Earth, just as the sunset and sunrise skies are seen to assume a ruddy color. The moon, however, does not always assume this tint during eclipses. Sometimes there is a phenomenon known as the black eclipse, when the moon's surface is seen with a grayish-blue tint. Indeed, sometimes the moon disappears altogether during eclipse. These variations are explained by a well-known astronomer in the following remarks. It has been suggested that if the portion of the Earth's atmosphere through which the sun's rays have to pass is tolerably free from aqueous vapor, the red rays will be absorbed, but not the blue rays, and the resulting illumination will either only render the moon's surface visible with a grayish-blue tinge, or not visible at all. This will yield the black eclipse. Eclipses of the moon have long been a source of terror to the unlearned, and especially to savage tribes. Many instances might be given of the fear which the darkening of the moon's light struck into the hearts of the ignorant, but one instance will suffice. An eclipse of the moon took place when Columbus was in the island of Jamaica in 1504. The eclipse was total and occurred very soon after sunset, and the event occurred at a most convenient time so far as the great explorer was concerned. In the Life of Columbus, by Sir A. Helps, the narrative is told as follows. The Indians refused to minister to their wants any longer. The famine was imminent. But just as this last extremity, the admiral, ever fertile in devices, bethought him of an expedient for re-establishing his influence over the Indians. His astronomical knowledge told him that on a certain night an eclipse of the moon would take place. One would think that people living in the open air must be accustomed to see such eclipses sufficiently often not to be particularly astonished at them. But Columbus judged, and, as the event proved, judged rightly, that by predicting the eclipse he would gain a reputation as a prophet, and command the respect and the obedience due to a person invested with supernatural powers. He assembled caciques of the neighboring tribes. Then, by means of an interpreter, he reproached them with refusing to continue to supply provisions to the Spaniards. "The God who protects me," he said, "will punish you. You know what has happened to those of my followers who have rebelled against me, and the dangers which they encountered in their attempt to cross Haiti, while those who went at my command made that passage without difficulty. Soon, too, shall the divine vengeance fall on you. This very night shall the moon change her color and lose her light, in testimony of the evils which shall be sent upon you from the skies." The night was fine. The moon shone down in full brilliancy. But at the appointed time, the predicted phenomena took place, and the wild howls of the savages proclaimed their abject terror. They came in a body to Columbus and implored his intercession. They promised to let him want for nothing, if only he would avert this judgment. As an earnest of their sincerity, they collected hastily a quantity of food and offered it at his feet. At first, diplomatically hesitating, Columbus presently affected to be softened by their entreaties. He consented to intercede for them, and retiring to his cabin performed, as they supposed, some mystic rite which should deliver them from the threatened punishment. Soon the terrible shadow passed away from the face of the moon, and the gratitude of the savages was as deep as their previous terror, and henceforth there was no failure in the regular supply of provisions to the castaways. It is well to bear in mind the differences between the two kinds of eclipses. While a lunar eclipse may last for several hours, a solar eclipse is a matter of a few minutes. And while a lunar eclipse can only take place at full moon, a solar eclipse occurs at new moon. Professor Gregory gives an instance of a novelist who, in one of his books, describes an eclipse of the sun which took place at full moon and lasted half an hour. A little knowledge of the theory of eclipses would prevent such an error. As has been pointed out, an eclipse of the moon is caused by the immersion of our satellite in the shadow of the Earth. A solar eclipse, on the other hand, is caused by the moon's shadow falling on our planet. The moon is a much smaller body than the Earth, and consequently it has a much smaller shadow. The shadow is too small to completely cover the Earth. It merely falls on a portion of the globe, and at the parts immersed in the shadow the sun is totally eclipsed. Solar eclipses last only a few minutes, and they are confined to a narrow strip known as the shadow track. At any given place on the Earth's surface, total eclipses of the sun are rare. There has not been a total eclipse of the sun visible in the United Kingdom since 1724, and there will not be another until 1927. However, though rare at given points on the surface of our planet, they are fairly frequent when the Earth is considered as a whole. There are 3 kinds of solar eclipses: total, partial, and annular. A total eclipse takes place when the moon is at its nearest point to the Earth, and consequently appears just large enough to hide the sun, and when our satellite is exactly in a line with the Earth and sun. A partial eclipse occurs when the moon is not exactly in a line with the Earth and sun, and only covers a portion of the disk, while an annular eclipse takes place when the moon is at its farthest point from the Earth and does not appear to be large enough to cover the disk of the sun, and thus we see an annulus, or ring of light, around the moon's disk. Of these 3 classes, only total eclipses are useful to astronomers, and that only because of a peculiar combination of circumstances. Seen from the Earth, the sun and moon appear to be about the same size. Consequently, at a total eclipse the moon is large enough to cover the large and glowing disk of the sun, but not large enough, fortunately for the science of astronomy, to obscure the immediate surroundings of the orb of day. When a solar eclipse takes place, expeditions are sent to observe the phenomena from all parts of the globe. Those who are unacquainted with the problems of solar astronomy may think it strange that so many expeditions are dispatched to observe the obscuration of the sun by the moon, an event in itself of no particular importance. But owing to a combination of circumstances, these obscurations have proved to be full of interest to the astronomer. The interposition of the moon enables us to study the fainter and outlying portions of the sun. In the words of Professor Campbell, the director of the Lick Observatory, our sun is one of the ordinary stars. In size, perhaps it is only an average star, or it may be below the average. It is the only star near enough us to show a disk. All other stars are as mathematical points, even when our greatest telescopes magnify them 3,000-fold. The point image of a distant star includes all its details, and it must be studied as a whole, whereas the sun can be studied in geometrical detail. It is not too much to say that our physical knowledge of the stars would be practically a blank if we had been unable to approach it through the study of our sun. If we would understand the other stars, we must first make a complete study of our own star. Several of the most interesting portions of our sun are invisible, except at times of solar eclipse. Our knowledge of the sun will be incomplete until these portions are thoroughly understood, and this is the reason why eclipse expeditions are dispatched, at great expense of time and money, to occupy stations within the narrow shadow belts. The chief objects of study during total eclipses are the solar prominences and the reversing layer, or shallow solar atmosphere, and the corona. The red prominences were formerly observable only during total eclipse, but in 1868, M. Janssen, viewing the total eclipse in India, and Sir Norman Lockyer, reasoning the matter out in England, discovered the method by which prominences could be observed in full sunlight, by means of the spectroscope. Accordingly, less attention is devoted to them during total eclipses. It may, however, be remarked that a class of objects known as white prominences, discovered by the late Professor Ticini during the eclipse of 1883, are observable only on the occasion of a total eclipse. The corona is perhaps the chief object of interest in eclipse observations. The corona is a halo of light which makes its appearance as soon as the sun is totally eclipsed, and remains in view only during the few minutes of totality. It is not a solar atmosphere, using that word in its proper sense, and it is probably of a compound nature. The spectroscope has had little chance to teach us much regarding the corona, owing to the faintness of the spectrum and the short time of visibility. Professor Young considers that the coronal spectrum is composed of 4 superposed spectra, indicating, of course, that the corona is a compound phenomena. First, there is the continuous spectrum, due probably to incandescent dust, or solid and liquid particles near the Sun. Secondly, the gaseous spectrum, indicating the presence of gases of a permanent nature. This spectrum is distinguished by a green line, which has not been identified with any terrestrial element. Thirdly, there is the continuous spectrum of reflected sunlight with the dark Fraunhofer lines, due to sunlight reflected from meteoric dust. And fourthly, the light reflected in the Earth's atmosphere. Drawings and photographs of the corona show that its size and shape vary in a period of 11 years, corresponding with the changes of the solar spots, and even more nearly so with the period of the prominences. In fact, the late Professor Ticini showed that the distribution of the prominences and the shape of the corona vary in harmony. There is still much uncertainty as to the actual nature of the corona, and as to what part electricity and magnetism may play in the phenomena. In Professor Campbell's words, much has been written concerning a possible eruptive origin, or about magnetic influences in shaping the form of its streamers. It is a surprising fact that, with all the changes of form, we do not know whether the materials composing the streamers are moving in or out, or both, or neither. Photographs of the corona should be secured for this purpose at widely separated stations, preferably at 3 or more stations, with essentially identical instruments and with equivalent exposures, in order that results may be as nearly comparable as possible. The reversing layer of the Sun was discovered by Professor Young by means of the spectroscope during the total eclipse of 1870 visible in Spain. As the solar crescent grew thinner, says Professor Young, the dark lines of the spectrum itself gradually faded away, until all at once, as suddenly as a bursting rocket shoots out its stars, the whole field of view was filled with bright lines more numerous than one could count. The phenomena was so sudden, so unexpected, and so wonderfully beautiful as to force an involuntary exclamation. Professor Young concluded that every line in the spectrum had become bright, and hence the newly disclosed layer of the Sun was called the reversing layer. In 1896, its spectrum was photographed by an English observer. The eclipse problem which appeals most to the popular mind is perhaps that of the possible existence of intermercurial planets, already discussed in an earlier chapter. With the exception of some doubtful observations in 1878, eclipse observations have tended to negative the idea of even a small planet within the orbit of Mercury. Photographs were secured by Mr. W. H. Pickering in 1900 and by Professor Perrine in 1901, and on these no trace of an intramercurial planet was seen. Professor Campbell made an exhaustive search during the total eclipse of August 30th, 1905, visible in Spain, and no trace of an intramercurial planet could be found. For those who have never seen a total eclipse, the following description by an American writer, Mrs. Todd, is worth reading as illustrating the magnificence of the spectacle. With frightening velocity, the actual shadow of the moon is often seen approaching, a tangible darkness advancing almost like a wall, swift as imagination, silent as doom. The immensity of nature never comes quite so near as then, and strong must be the nerve not to quiver as this blue-black shadow rushes upon the spectator with incredible speed. Sometimes the shadow engulfs the observer smoothly, sometimes apparently with jerks, but all the world might well be dead and cold and turn to ashes. Often the very air seems to hold its breath for sympathy. At other times a lull suddenly awakens into a strange wind blowing with unnatural effect. Then out upon the darkness, gruesome but sublime, flashes the glory of the incomparable corona, a silvery, soft, unearthly light with radiant streamers, stretching at times millions of uncomprehended miles into space, while the rosy, flaming protuberances skirt the black rim of the moon in ethereal splendor. It becomes curiously cold, dew frequently falls, and the chill is frequently mental as well as physical. Suddenly, instantaneous as a lightning flash, an arrow of actual sunlight strikes the landscape, and Earth comes to life again, while corona and protuberance melt into the returning brilliance. For many years, eclipses both of the sun and the moon were a source of terror to mankind, before proper knowledge had been gained of their true cause. And even today, in uncivilized nations, eclipses cause much consternation. In China, drums are beat and trumpets blown to frighten the dragon, which is supposed to be devouring the sun. The Hindus think that an eclipse causes food to be unclean, and consequently that it is unfit for use. The following cutting from an American newspaper in 1878 indicates the excitement caused among the Red Indians by the total solar eclipse of 29th July 1878. Some of them threw themselves upon their knees, others flung themselves flat on the ground face downwards, others cried and yelled in frantic excitement and terror. At last an old Indian stepped from the door of his lodge, pistol in hand, and, fixing his eyes on the darkened sun, mumbled a few unintelligible words, and raising his arm, took direct aim at the luminary, fired off his pistol, and after throwing his arms about his head, retreated to his own quarters. As it happened, that very instant was the conclusion of totality. The Indians beheld the glorious orb of day once more peep forth, and it was unanimously voted that the timely discharge of the pistol was the only thing that drove away the shadow, and saved them from the public inconvenience that would certainly have resulted from the entire extinction of the sun. Closely allied to eclipses are transits. Only 2 planets can be seen in transit across the sun, Mercury and Venus. These transits occur like eclipses of the sun, when the sun, the earth, and Mercury, or the sun, the earth, and Venus are in a straight line. But, owing to the very small apparent size of Mercury and Venus as seen from the earth, there is no eclipse. We merely see the black disks of the planet as spots on the glowing face of the sun. The first observed transit of Venus was predicted by Kepler for 1631. These transits take place in pairs, separated by intervals of 8 years, and the pairs are separated by intervals of 105.5 and 121.5 years. Kepler, although he had predicted the transit of 1631, was unaware of the fact that transits occur in pairs, and he did not expect another until 1761. A transit, however, took place in 1639, and was only witnessed by 2 persons. The story of its observation is an interesting one, and has long been a favorite among lovers of astronomy. A young Englishman, Jeremiah Horrocks, a curate in the English church, became at a very early age proficient in mathematical astronomy, and ascertained the fact that a transit of Venus, which Kepler had overlooked, would take place in 1639. The day he predicted for the transit happened to be a Sunday, and Horrocks could not observe continuously owing to his duties as a clergyman. At 9 o'clock he was obliged to suspend observations. But at 10 he was again watching. He saw nothing on the sun's disk. At noon he was again at church, but by 1 o'clock he was enabled to resume observations. To his sorrow the sky clouded, and he almost abandoned hope of seeing the event he had predicted. But in the afternoon the clouds dispersed, the orb of day shone out once more, and the young astronomer beheld, to his intense delight, Venus in transit across the sun. He had informed only one man, his young friend William Crabtree, of the occurrence of the event, and Crabtree also succeeded in observing the transit. But these 2 young men were the only observers of this occurrence, unexpected by the astronomers of the day. Horrocks, who gave promise of becoming one of the greatest astronomers of his time, did not long survive his triumph. He died shortly after, at the early age of 22. The next pair of transits occurred in 1761 and 1769. Before they took place, however, Halley had pointed out that observations on Venus while in transit would lead to a correct measurement of the distance of the sun, and consequently several expeditions were sent to observe these transits at different ends of the earth. As an erroneous estimate of the sun's distance was deduced from these measurements, astronomers looked eagerly forward to the next 2 transits in 1874 and 1882. As before, expeditions were dispatched to all regions of the globe, but the results were disappointing, and astronomers have since devised better and more accurate methods of measuring the sun's distance. The next pair of transits of Venus will take place in 2004 and 2012, and there will be another pair in 2117 and 2125. The reason of the rarity of these occurrences is the fact that the orbit of Venus is not exactly in the same plane as that of our Earth. Transits of Mercury are not of so much interest as those of Venus, and they are much more frequent. The last took place in 1907, and there will be another in 1917. Closely allied both to eclipses and transits are occultations. The difference, however, between transits and occultations is that, while a transit is the passage of an apparently small body over an apparently large body, An occultation is the obscuration of a body apparently small by a body apparently large. Thus, when the moon passes over Jupiter or Mars, or a star, it is said to occult these objects. In the system of Jupiter, which we only observe from a considerable distance, we can observe eclipses, transits, and occultations. We see the satellites immersed in the shadow, and we can also observe them in transit across the disk of their primary. In addition, we can observe Jupiter passing over and occulting these small bodies. Thus, observation of the system of Jupiter gives us a practical illustration of the fact that eclipses, transits, and occultations are all kindred phenomena, arising from the fact that every body shining by reflected light casts a shadow into space. End of chapter 17.
Chapter 18 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 18. The Sons of Space. When we lift our eyes to the heavens on any clear, moonless night, apparently innumerable luminous points of all degrees of brightness attract our attention. They are fixed in position relatively to one another, and they rise and set like the sun. These are the stars proper, as distinguished from the planets or wandering stars. These stars are the same orbs which shone down on Job and Homer and the ancient writers of thousands of years ago. And it is a solemn thought when we look upward to the star-spangled heavens that the same constellations and star groups met the gaze of generations upon generations which have long since passed away. Homer and Hesiod both refer to the constellations. Job mentions Orion and the Pleiades, and also, it is believed, the Great Bear. This fact proves that long ago, before astronomy was founded on a scientific basis, the early stargazers had already divided the sky into constellations and had given to them names. These star groups are recognized by astronomers today, and one of the first steps for the beginner in astronomy is to learn the constellations. Just as in botany and geology respectively, it is necessary to know the various flowers and the different classes of rocks by name. So in astronomy, it is essential to know the constellations and to be able to follow them throughout the changing seasons. Most people are familiar with the Great Bear or Ursa Major, or at least with its most prominent part, the Plough. The Plough is not the most conspicuous constellation, but it is visible all the year round, and its shape is very easily remembered. But its position varies from month to month. It is essential to remember that the aspect of the heavens changes with the seasons. Not only do the stars appear to go round the Earth once in 24 hours, but, owing to the apparent motion of the sun, the stars appear to rise and set 4 minutes earlier every night. The result is a constant change, gradual but steady, in the position of the stars at any given time. And at the end of the year, the revolution is completed, and the stars return to the places which they occupied a year before. One star in the heavens, however, scarcely changes its position at all. This is a fairly bright object in the northern sky known as the pole star, so called because the axis of the Earth points almost exactly to it. That is to say, were we standing exactly at the North Pole, we should see the pole star almost exactly overhead. The pole star therefore remains practically fixed in position, while all the stars in the sky appear to revolve round it. The farther the star from the pole, the wider the circle which it appears to describe. Thus, the stars of Ursa Minor, the constellation in which the pole star is situated, describe smaller circles than the stars in the Plough. But even the stars in the Plough describe a relatively small circle. They are never below the horizon, and their ceaseless revolution round the pole is an index of the changing seasons. For instance, in the spring evenings, the plow is almost directly overhead. In summer evenings, it is in the northwest. In autumn evenings, it is low down in the north. In winter evenings, in the northeast. On the opposite side of the pole from the plow is the constellation Cassiopeia. It is shaped like the letter W. Between Cassiopeia and the plow is Auriga, a star group dominated by a brilliant star known as Capella. And on the other side of the pole from Auriga is Lyra, another star group also dominated by a bright star known as Vega. These four constellations are almost always visible, though sometimes Auriga and Lyra are lost in the haze of the horizon. In England, these two stars disappear for a certain time in the haze of the horizon, but in Scotland and northern latitudes, they are nearly always to be seen. These four constellations, moving around the pole, constitute what has been well named the Great Star Clock of the North. As Mr. E.W. Maunder has said, to watch these northern constellations as they follow each other in ceaseless procession round the pole is one of the most impressive spectacles to a mind capable of realizing the significance of what is seen. We are spectators of the movement of one of nature's machines, the vastness of the scale of which, and the absolutely perfect smoothness and regularity of whose working, so utterly dwarf the mightiest work accomplished by man. Once a knowledge of the northern heavens has been gained, it is a comparatively easy matter to learn the names and outlines of the remaining constellations. Each season has its own particular groups. For instance, Orion, Taurus, and Canis Major are the great constellations of winter, even though they may be seen in spring and autumn. But it is in winter that they are seen to most advantage, and that they are visible at the most convenient hours of the night. Similarly with the other stars. In spring we have Leo, Virgo, and Boötes dominating our skies. In summer we have Lyra, Scorpio, Hercules, Corona Borealis. In autumn, Cygnus, Aquila, Aries, Perseus, and other groups. As the seasons advance, the reappearance of a familiar constellation lends a new charm and interest to the evening walk. Not only the constellations themselves, but the stars which compose them have their own designation. Some of the brighter stars, such as Sirius, Vega, Arcturus, and Capella, have proper names, but the vast majority are designated by letters of the Greek alphabet. Thus, the bright star Aldebaran is also known as Alpha Tauri, Tauri being the genitive of the Latin noun Taurus. Similarly, Sirius is Alpha Canis Majoris. When the Greek letters in each constellation are exhausted, numbers are used also with the genitive of the Latin noun. Thus, we talk of 61 Cygni, 42 Comi Berenices, etc. So much for the stars as they appear. But the science of astronomy enables us to understand what the stars really are. To us they appear little twinkling points of light suspended above the clouds, useful on a moonless night. Astronomy teaches us that, so far from being merely little points of light, the stars are suns. This great truth gradually dawned on mankind. Even Copernicus had very hazy notions as to the nature of the stars. But as astronomy developed, and as better instruments were invented, our information concerning the distant orbs increased, until today our knowledge of the stars is considerable. It was the great Sir William Herschel who first studied the stars systematically. And so many and important were his discoveries, and so great was the interest in the stars aroused by his investigations, that since the commencement of his work, stellar astronomy, as distinguished from planetary astronomy, has gone from triumph to triumph. The stars are suns. This is the first great truth which we must bear in mind. Very insignificant they seem, even the brighter objects among them being almost obliterated by the moonlight, utterly extinguished by the sunlight, and seeming very small and unimportant beside Jupiter, Venus, and Mars. As we saw in preceding chapters, distance is often very deceptive. The moon, for instance, shines many times more brightly than Jupiter, and yet it belongs to an altogether inferior order of bodies. It is only a satellite, the attendant of our world, while Jupiter is a planet many times larger than the Earth. Jupiter shines many times more brilliantly than Sirius, the brightest of the stars. Yet Jupiter is to the stars as the moon is to Jupiter. For the stars are suns, and Jupiter sinks to utter insignificance compared with even the faintest of the stars. It belongs to an altogether inferior order of bodies. It is the vast distance of the stars which explains their apparent insignificance, a distance so vast that for many years it was hopeless to attempt to measure it. In a previous chapter, explanation was made of the principle of measurement of the celestial distances and of the meaning of the term parallax. If the measurement of the distances of the sun and planets is difficult, it will easily be understood how much more difficult is the measurement of the distances of the faraway stars. The fact that the stars showed no measurable displacement greatly perplexed Copernicus. It was argued, and rightly, by the opponents of the Copernican system that if the Earth had an annual revolution round the sun, there ought to be a corresponding displacement of the stars owing to the observer's change of position. But the most careful measurements of the astronomers of that day failed to show any displacement. Copernicus had therefore to claim for the stars a much greater distance than he was willing to, for in those days men had a very inadequate idea of the universe. Tycho Brahe, the last of the great pre-telescopic astronomers, also attacked the question and attempted to find this displacement, but he failed. After the invention of the telescope, many attempts were made, but in vain. The greatest astronomers were baffled, among them such men as Bradley and Herschel. And it was not until the third decade of the 19th century that the first milestone of infinity, so to speak, was reached. 3 attempts were made independently to measure this displacement. In 1835, the German astronomer Struve commenced a series of measurements on the bright star Vega, but the distance which he deduced from his measurements proved so far from the truth that the result was practically useless. Other 2 attempts proved more successful. The German astronomer Bessel succeeded in measuring the distance of a faint little star of the 5th magnitude numbered 61 in the constellation Cygnus. At the same time, Thomas Henderson, the great Scottish astronomer, afterwards Astronomer Royal of Scotland, measured the distance of what has proved to be the nearest star. While employed as the Astronomer Royal at the Cape of Good Hope, he made a series of observations on the brilliant star known as Alpha Centauri, one of the brightest stars in the heavens, and he succeeded in measuring its distance. This distance is about 25 billions of miles. Such figures are unthinkable. The entire solar system is about 5,000 millions of miles in diameter. A great diameter, it is true, but inconsiderable when compared to the enormous distance of the nearest star. Our solar system is indeed a little island in space, a mere speck in the greater system of the stars. It is difficult to obtain a true idea of this vast distance. The late Dr. Dalmage, in his book Astronomy of Today, gives a unique illustration which should help the reader a little, as it were, in comprehending the incomprehensibleness of this distance. What is a million? It is 1,000 thousands. But what is a billion? It is 1,000,000 millions. Consider for a moment. 1,000,000 of millions. That means 1 million, each unit of which is itself 1 million. Here is a way of trying to realize this gigantic number. 1,000,000 seconds make only 11.5 days and nights, but 1 billion will make actually more than 30,000 years. An idea of the immense distance of the nearest star may be gained from consideration of the fact that if the distance from the Sun to Neptune were represented by 10 feet, Alpha Centauri would be 14 miles away. But the true method by which we can properly comprehend the distances of the stars is by considering the velocity of light. Light crosses the diameter of the entire solar system in 8 hours. Yet it takes about 4 years to span the gulf which separates our system from the nearest star. What, then, of the more distant stars? 61 Cygni is about 53 billions of miles away, and light requires about 7 years to reach us from that orb. Sirius, the most brilliant star in the sky, is distant 58 billions of miles, and light is 8 years on the journey. In the vast majority of cases, there is no visible displacement of the stars in the sky, and their distances cannot be measured. An idea of the great difficulty of measuring this parallax or displacement may be gathered from the remark of an American writer, Mr. G.P. Service, that the displacement is about equal to the apparent distance between the heads of 2 pins placed an inch apart and viewed from a distance of 180 miles. The wonder is not that astronomers have measured the distance of so few stars, but that they have succeeded in measuring the distances of any. Comparatively few distances have been measured with any approach to accuracy. A number have been measured roughly, and a number estimated. It might be supposed that the brightest stars, those of the first magnitude, are nearest to the Earth, but such is not the case. Sirius, it is true, is among the nearer stars, but it is at a greater distance than 61 Cygni, an insignificant little star of the 5th magnitude. Thus we see that, just as there are great diversities among the planets, so the stars are far from being all of the same size. A tolerably accurate measurement of the distance of the brilliant star Arcturus has been made. So vast is the distance that light takes over 200 years to travel to our system from its glowing surface. How enormous, therefore, must be the star which shines so brilliantly from so vast a distance. The diameter of Arcturus is believed to be about 62 millions of miles. Compared with Arcturus, our Sun, great and splendid orb as he seems to us, is a puny dwarf. Mr. Garrett P. Service says of this enormous Sun, "Imagine the Earth and other planets constituting the solar system removed to Arcturus and set revolving round it in orbits of the same forms and sizes as those in which they circle about the Sun. Poor Mercury! For that little planet it would indeed be a jump from the frying pan into the fire, because as it rushed to perihelion, the point of its orbit nearest the Sun, Mercury would plunge more than 2,500,000 miles beneath the surface of the giant star. Venus and the Earth would melt like snowflakes at the mouth of a furnace. Even faraway Neptune would swelter in torrid heat." Another enormous sun is Rigel, one of the 2 brilliant orbs in Orion. So distant is this body that Sir David Gill utterly failed to measure its distance. Capella, in Auriga, is yet another gigantic orb. According to Mr. Gore, it is about 14 millions of miles in diameter and is equal in volume to 4,000 suns such as ours. A little reflection on these enormous sizes shows us that everything in the universe is relative. To us on Earth, a range of mountains is gigantic. The Earth itself is so vast that we cannot conceive of it as a globe at all, and we can only regard a portion of it at a time. And what of the Sun? To us its size is overwhelming. We cannot realize a diameter 100 times that of our Earth. And as to the stars, we may repeat the figures which denote their diameters, but we cannot grasp what these figures mean. The stars themselves are of all sizes and at all distances. All are enormously distant, but some are much nearer than others. All are enormously large, but some much larger than others. Of the 2,000 visible at a time to the unaided eye, we have measured the distances of very few, and have calculated the sizes of the merest handful. And yet at the very beginning of our investigations among the suns of space, we learn that indeed, one star differeth from another star in glory. End of chapter 18. Read by Andrea Kotzer.
Chapter 19 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 19. The Revelations of Starlight. When we cast an upward glance to the heavens and look at the stars, we little realize what may be called the revelations of starlight. We little imagine that in the rays of the stars are born to us most of the secrets of the universe, and that the light rays from immensity tell us a story which for wonder, mystery, and majesty is unrivaled in the realms of the imagination. In the chapter on the Sun, reference was made to the spectroscopic method of observing that luminary, and to the knowledge which has been gained from a study of the band of colored light known as the solar spectrum. It is much more difficult to observe the spectra of the various stars than the spectrum of the Sun, owing to the relative feebleness of starlight. However, since 1863, astronomers have made rapid progress in this branch of knowledge. In that year, the late Sir William Huggins commenced his work in this department by a particular study of two stars of the first magnitude, Betelgeuse and Aldebaran. In the former star he ascertained the existence of the elements sodium, iron, calcium, magnesium, and bismuth, and in the latter the same elements with the addition of tellurium, antimony, and mercury. Thus, for the first time, the rays of starlight had revealed to humanity the constitution of the suns of space. Secchi, a well-known Italian astronomer, made classification of the stars in the heavens about the same time that Sir William Huggins started his observations. It was known many years before that just as the sun had a different spectrum from any of the stars, so the stars differed among themselves. It was shown, however, by Secchi that the stars could be divided into four well-defined groups: white stars, yellow stars, red stars, and dark red stars, according to the variations in their spectra. Although other more scientific classifications have since been proposed and adopted, the first classification gives us a general idea of the different types of stars. When we turn our eyes to the heavens, we see that the stars are not all of the same color. We at once know the bluish-white of Sirius, the red color of Betelgeuse, the orange-red hue of Aldebaran. When we consider the bright stars according to their spectra, we find that Sirius, Vega, Rigel, Altair, Regulus are included in the class known as the white stars, or Sirian stars, from their brightest example. In the second type are included Capella, Arcturus, Aldebaran, Procyon, Pollux, and the Pole Star. The spectrum of our Sun, in fact, is of this type, and hence this class of orbs is known as the group of solar, or yellow stars. The stars of the third type are much less numerous. Betelgeuse and Antares are the most notable representatives of this type. The fourth type includes stars of a deeper red, none of which are bright enough to command the attention of the casual observer. The first type has been subdivided by the late Dr. Vogel into two subclasses, the Orion type and the Sirian type. The stars of the Orion type are so called because most of the stars in the constellation Orion are of that class. They are distinguished by the presence in their atmospheres of the element helium. Rigel, in Orion, is one of the typical stars of this group, and a massive and gigantic orb it appears to be. Its mass is no less than 34,000 times that of the Sun, the enormous orb whose size overwhelms the minds of mortals. Rigel, however, as the late Miss Clerk pointed out, quote, is not massive in the proportion of its luminosity, end quote. It gives about 8,000 times more light than our Sun. Quote, but the Sun is dimmed to about 1/3 of its native luster by the effects of absorption, which are virtually absent from the star. Hence, a total light emission 8,000 times greater would represent a radiating surface only 2,667 times more expansive than the solar photosphere. Stars of the helium variety are composed of highly rarefied materials. End quote. Sirius and Vega may be taken as typical stars of the second subdivision of stars of the first type. Stars of the solar type are of various sizes. Alpha Centauri, one of our nearest neighbors in space, seems to be a sun in many respects similar to our own. Another star of the solar type which deserves mention is Arcturus, or Alpha, of the constellation Bootes. Its spectrum is of the solar type, but so far as size is concerned, as mentioned in the last chapter, it dwarfs the Sun to utter insignificance, and apparently belongs to a higher order of suns than the ruler of our own planetary system. In a work like the present, it is obviously impossible to present the technical details of the researches of astronomers on the spectra of the stars. One interesting discovery may be mentioned. It might be supposed that stars of the different types are scattered over the sky at random, but such is not the case. The white stars congregate on the whole in a definite region of the heavens, that marked by the Milky Way, or galaxy, while the solar stars are on the whole distributed with some approach to uniformity. The meaning of this difference in distribution of the two types will be unfolded in a later chapter. Although most of our knowledge of starlight is due to the marvelous revelations of the spectroscope, a considerable amount of knowledge has been gained from a study of starlight by the telescope, and indeed by the unaided eye. Perhaps the most remarkable objects in the heavens are the new or temporary stars, orbs which blaze out in the sky where no previous stars have been seen, and which then sink into invisibility. Many instances of temporary stars have been recorded. A temporary star is believed to have appeared in the year 134 BC, and to have suggested to Hipparchus, the famous Greek astronomer, the idea of forming a catalogue of stars. The first temporary star, however, of which we have any authentic record, was observed by Tycho Brahe, and is always known as Tycho's star. The famous Danish astronomer was not, however, the discoverer of the star. It was detected by a German at Wittenberg on August 6, 1572, whereas Tycho did not notice it until November 11th. Looking up to the sky one evening, Tycho was astounded to see the appearance of the well-known constellation Cassiopeia entirely changed by the appearance of a new and brilliant star, far outshining the other stars of the group. When first seen by Tycho Brahe, the new star was brighter than Jupiter, and when it reached its greatest visibility, it was fully equal to Venus. So bright, indeed, was the new star, that in a clear sky it was visible in full daylight. In March 1574, it ceased to be visible to the unaided eye. Another bright star, usually associated with the name of Kepler, appeared in 1604. On 10th October of that year, one of Kepler's pupils noticed that a new and brilliant star had made its appearance in the constellation Ophiuchus. The planets Mars, Jupiter, and Saturn were close together in the same constellation, and it was easy to make comparisons between the new star and the planets. It was estimated as brighter than Mars and Jupiter, and indeed as equal to Venus. The star, which was also studied by Galileo, disappeared in March 1606, having been visible for about 17 months. These two stars were the brightest temporary stars recorded in history. The next authentic instance of a similar object was the appearance of a much less imposing stellar phenomenon. By the middle of the 19th century, the discovery of temporary stars was a much easier matter than at the time of Galileo, owing to the increased power of telescopes as well as the increased number of astronomers. The star detected by the English observer Hind on April 28, 1848, never exceeded the 5th magnitude in brilliancy. More striking was the star of 1866, popularly known as Blaze Star. John Birmingham, an amateur astronomer at Tuam in Ireland, observing the heavens with the unaided eye on the evening of May 12, 1866, detected a brilliant star in the constellation Corona Borealis. It was then of the 2nd magnitude and equal in brilliance to the brightest star of the constellation. It must have increased very rapidly, for Schmidt of Athens, one of the most competent observers of the day, affirmed that when he scanned the same part of the sky 4 hours earlier, it was not then visible, although he was sure that no strange star brighter than 5th magnitude could have escaped his notice. This star was notable from the fact that for the first time the newly invented spectroscope was applied to the study of temporary stars. The star was particularly studied by Sir William Huggins, who discerns 4 brilliant lines in the spectrum. The principal line represented hydrogen. It was thus obvious that the cause of the outburst was the eruption of vast masses of hydrogen gas. The new star declined very rapidly in brilliance, although not so rapidly as it increased. 9 days after its appearance, it was invisible to the unaided eye. The remarkable thing about this star was that it was not actually a temporary star in the true sense of the word, as it had been observed 10 years earlier as an ordinary telescopic star invisible to the unaided eye. The appearance of this star caused much interest among astronomers. The marvelous feature of the outburst was that in a few hours the star increased its brilliance by about 900 times. Mr. Peck, astronomer of the city of Edinburgh, has the following remarks in this connection. Quote, "What would likely be the result if a conflagration like that, which took place on this remote sun, were at any time to happen to our sun? Not only would all the various forms of life on Earth be utterly destroyed, but on all the members of our solar system there would be such a change effected that if any life existed even on the remote Neptune, it would at once be completely extinguished. Probably the life that existed on the whole system of worlds that circled round this distant star must have been annihilated, and as the heat and light of this star increased so very suddenly, there could have been given but short warning to the inhabitants of these worlds." End quote. Another new star made its appearance 10 years later. On November 24, 1876, Schmidt noticed a strange star of the 3rd magnitude in Cygnus. It was closely similar to the new star of 1866, hydrogen being present in abundance. A new star which appeared in Andromeda in 1885 is interesting from the fact that an attempt was made to measure its distance from the solar system. So vast, however, was this distance that the attempt was a failure. The next temporary star was detected in January 1892 in the constellation Auriga by Dr. Anderson of Edinburgh, a famous observer of variable stars. At the time of discovery, it was of the 5th magnitude. Remarkably enough, this new star had been visible to the unaided eye for some time before Dr. Anderson's discovery, but had never been noticed. It had imprinted its image on photographs taken in America by Professor Pickering. These photographs showed that on November 20th it was a little over the 4th magnitude. It then began to decline, and when discovered visually, it was of the 5th magnitude. Then, after its discovery, it brightened up again, and on February 14th was between the 4th and 5th magnitudes. After this, it steadily declined until April, when it was of the 15th magnitude, but in August, astronomers were astounded to find that it had again increased, this time to the 9th. Since then, it has steadily diminished. A number of insignificant temporary stars made their appearance between 1892 and 1901, being mostly detected by photography. These are of little interest except to the professional astronomer, and may be passed over here. But on February 21st, 1901, a magnificent temporary star, the most brilliant since Kepler's in 1604, shone out in the constellation Perseus. It was so brilliant as to be detected by a number of independent observers, including Dr. Anderson, the discoverer of the previous new star, and Mr. J. E. Gore. When first seen by Dr. Anderson, it was of the second magnitude, and a photograph taken of the previous evening showed that it must have been then below the 12th magnitude, as it was invisible on the photograph. On the evening of February 23rd, the star was equal to Capella and of the first magnitude. But it did not long retain its preeminence. By March 1st it was of the second magnitude, and by March 6th of the third. In September it faded to the 6th magnitude, while in March 1902 it was of the 8th magnitude, and in July of the 12th. Since that date, 2 other new stars have been discovered, both faint, in 1903 and 1905 respectively. Many theories have been advanced to account for temporary stars. The most probable of these various theories is that put forward by Professor Seliger, who regards these outbursts as due to the passage of dark extinct stars through masses of nebulous matter. The dark stars are raised to incandescence through friction, just as the meteors are ignited by passing through the Earth's atmosphere. Temporary stars differ in many respects from variable stars. But one body in the heavens, which seems to belong partly to both classes, deserves mention. This star is known as Eta Argus, and is invisible in Europe. At present, it is of the 7th magnitude, and cannot be seen without the aid of a telescope. In the 17th century, it was of the 4th magnitude, and 100 years later of the 2nd, while in 1837 it was equal to the 1st magnitude star Alpha Centauri. Then it began to decrease. In 1843, however, it again blazed up, and became the 2nd star in the heavens, surpassed only by Sirius. Since then it has steadily declined, and is still inconspicuous. There are many known variable stars in the heavens, the catalogues containing thousands of them. The first variable was first seen in 1596 by Fabricius, a Dutch observer. It is known as Mira Ceti, or the wonderful star of Cetus. It has been thus under observation for over 3 centuries. Its period is about 331 days, but it is not very regular, and sometimes at its maximum it is much more brilliant than at other times. For instance, in 1906 it was brighter than the 2nd magnitude. Its variations appear to result from great internal disturbances. There are many stars which appear to vary in much the same manner, designated as variable stars of long periods. Other 2 classes of variables are known as, quote, algol stars, end quote, and short-period variables. The algol variables are so called from the brightest star of their type, Algol, or Beta Persei. The fluctuations in the light of Algol, which occupy 2 days, 20 hours, 48 minutes, 51 seconds, are believed to have been discovered by the ancient Arabian astronomers, and were rediscovered by Goodricke, an English astronomer in 1782. Goodricke suggested that the variations in the light of Algol were caused by the partial eclipse of the star's light by the interposition of a dark satellite star, just as the sun's light is cut off by the moon. In modern times, the late Professor Vogel of Potsdam confirmed this theory in a remarkable, indeed marvelous, way by means of the spectroscope. The explanation of this method is rather abstruse, and it is somewhat difficult to comprehend without a knowledge of physics. One of the most remarkable uses of the spectroscope is due to the fact that, by its means, motions may be measured. In 1842, Doppler, a German physicist, expressed the view that the color of a luminous body would be changed by its motion of approach or recession, and that a larger number of light waves would be entering the eye of the observer if the body were approaching than if it were retreating. The late Miss Clerke thus illustrates Doppler's principle, Quote, suppose shots to be fired at a target at fixed intervals of time. If the marksman advances, say, 20 paces between each discharge of his rifle, it is evident that the shots will fall faster on the target than if he stood still. If, on the contrary, he retires by the same amount, they will strike at correspondingly longer intervals. End quote. In an approaching body, the lines of the spectrum will be displaced towards one end of it, on a receding body towards the other. By this method, several astronomers succeeded in measuring the motions of the stars, and it was obvious to Vogel that, as Algol and its satellite are revolving around a common center of gravity, Algol would, before each eclipse, be retreating from our system, and after each eclipse, approaching. Vogel found that such was the case, thus proving the theory conclusively. Not only did he confirm the theory, but he has arrived to the conclusion that Algol is a star 1 million miles in diameter, the dark companion being 800,000 miles, about the size of the Sun. The distance between the two is about 3 million miles. From irregularities in the movements of Algol, an American astronomer is of the opinion that Algol and its dark companion revolve around another dark globe in 180 years, at a distance of about 1,800,000,000 miles. Thus, though we have never seen the satellite of Algol, we know that it exists, and though we cannot tell its distance from us, we can tell its probable size. The variable stars of short periods, such as the famous Beta Lyrae, are also explained by the mutual revolution of one or more bodies, and many a thorny question concerning variable stars has been solved by this method. Thus, the study of variable stars indicates the existence of systems of stars, stars in revolution around their center of gravity. This brings us to the subject of the next chapter, systems of stars. End of chapter 19. Chapter 20 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 20, Systems of Stars. In the well-known constellation of the Plough, there is a bright star known as Miser, or Zeta Ursae Majoris. Close by is an orb much fainter, which is only seen to advantage in a binocular or small telescope. These two stars, Miser and Alcor, form the finest examples in the heavens, to the unaided eye, of what is known as a double star. Other examples are to be found in Beta Cygni, a magnificent pair of colored suns, which is revealed in a small telescope, and in Alpha Capricorni, which a field glass will show as a double. A considerable number of double stars are known. The first to be discovered telescopically was found in 1664, when an English astronomer, while observing a comet in the constellation Aries, incidentally noticed that the star Gamma of that constellation consisted of two stars close together. For many years it was believed that these double stars were not really double, and that their apparent connection was merely the result of perspective. It was supposed that one star might be millions or billions of miles in space behind the other, and that the two appeared connected only because they happened to lie in the same line of vision. This view was generally held until, in 1802, it was shown by Sir William Herschel that many double stars were real stellar systems. In that year he announced that in the case of many of these doubles, the two stars were in mutual revolution. In other words, that the law of gravitation extended to the stars. Thus, he showed that the law of gravitation which Newton found applicable to the solar system was not merely a local law, but existed throughout the length and breadth of the universe. To distinguish between mere optical doubles, of which there are a considerable number in the heavens, and revolving stars, he gave the latter the name of binary stars, and this name is retained by them to the present day. Many of the brightest stars in the heavens are binaries. Among them must be mentioned Alpha Centauri, our nearest neighbor in space, Castor, one of the two well-known twins in the constellation Gemini, Sirius, the brightest star in the sky, and Procyon, another first-magnitude orb. The detection of the satellites of these two stars reminds us of the discovery of Neptune. In 1844, Bessel, the great German astronomer, discovered that Sirius was being attracted off its path by the action of some unseen body. Orbits were calculated by astronomers, and one calculator assigned a period of revolution of about 50 years to the satellite star. In 1861, the star was discovered close to the indicated spot, and its period of revolution turned out to be about 50 years. In the case of Procyon, the existence of a satellite star was also predicted before it was seen, and the actual period of revolution agrees with that which was deduced by the calculators, a fact which illustrates the remarkable accuracy of astronomical calculation. The number of double stars in the heavens is to be counted by thousands, and the orbits of many of these have been calculated successfully. The greatest names in this department of astronomy have been the Herschels, father and son, the Struves, father and son, and Professor S.W. Burnham of Chicago, the greatest living observer of double stars, who has himself discovered over 1,200 of these objects. Thanks to the spectroscopic method of determining motion in the line of vision, mentioned in connection with Algol, many double stars have been discovered, the components of which are too close together ever to be separately seen. Mizar in Ursa Major, which with Alcor forms a wide double and connected system, was found by Professor E.C. Pickering, by means of the spectroscopic method, to be itself double, and Spica, the brightest star of Virgo, was found to be also double. In the case of the last named star, the companion is almost completely dark. Since these discoveries were made in 1889 and 1890, quote, the astronomy of the invisible, end quote, as this line of research is called, has come to be regarded as a recognized branch of astronomy, and many of these close double stars are now known. Double stars, that is, telescopic doubles, often exhibit great varieties of color. Perhaps the most beautiful example within the range of small telescopes is Beta Cygni. A view of this beautiful star is a never-to-be-forgotten spectacle. The larger star is reddish-yellow, and the smaller one blue. Antares, a fiery red star in Scorpio, of the first magnitude, is attended by a small green companion star, and there are many other instances. For long it was thought that star colors were merely the effect of contrast. This, however, was disproved by the spectroscopic observations of Sir William Huggins. The colors of the stars are real. A vivid description of the scene observed by a dweller on any one of the planets revolving around these stars is given by the late Mr. Proctor in The Expanse of Heaven. He supposes one of the suns to be blue and the other orange, the planet being placed in the same position as the Earth is in our system. There would be an endless variety of sights in the heavens. The blue sun and orange sun might rise together and produce double day, or the blue sun might rise as the orange sun was setting, and there would be no night. In Proctor's own words, quote, the skies must be exceedingly beautiful. Our clouds have their silver lining because it is the light of the sun which illuminates them. Our summer sky presents glowing white clouds to our view, and at other times we see the various shades between whiteness and an almost black hue. But imagine how beautiful the scene must be when those parts of a cloud which would otherwise appear simply darker shine with a fuller blue light or with a fuller orange light. How gorgeous again must be the coloring of the clouds which fleck the sky when one or the other sun is setting. There are infinite varieties of arrangement depending on the relative dimensions of the suns of a double star system, and in their colors there are immense varieties. Yellow and purple suns, red and green suns, suns of golden yellow, cream white, rose color, and so on. Companion suns of lilac, russet, citron, fawn, buff, and olive hue in endless numbers. I conceive that few thoughts can be more striking and instructive than are those suggested by this infinite wealth of beauty and variety. End quote. It must be clearly borne in mind that these systems are completely different from ours. In the solar system, we have one bright star and a number of planets revolving around it. There may or may not be planets in these systems. But if such worlds do exist, they will, as Proctor points out, certainly experience very varied sights in their skies. Double stars of all classes are so numerous in the heavens that it may well be that these systems, long considered an exception, may be as prevalent as the systems of one star and a number of secondary worlds. Flammarion, in his Popular Astronomy, has the following reflection on double stars, which is worthy of reproduction, so high are the thoughts which it suggests to the mind. Quote, "The double stars are so many stellar dials suspended in the heavens, marking without stop in their majestic silence the inexorable march of time, which glides away on high as here, and showing to the earth from the depth of their unfathomable distance the years and centuries of other universes, the eternity of the veritable Empyrean. Eternal clocks of space, your motion does not stop. Your finger, like that of destiny, shows to beings and things the everlasting wheel which rises to the summits of life and plunges into the abysses of death. And from our lower abode we may read in your perpetual motion the decree of our terrestrial fate, which bears along our poor history and sweeps away our generation like a whirlwind of dust lying on the roads of the sky, while you continue to revolve in silence in the mysterious depths of infinitude." End quote. Double stars are not the only type of stellar systems. There are triple, quadruple, and multiple stars. One famous system is Zeta Canceri. This system has been particularly studied by Professor Seeliger of Munich, who has shown that in all probability 3 bright stars in this system revolve round a dark body, apparently the most massive of the 4. From multiple stars to groups and clusters of suns is but a step, and in such groups as the Hyades and Pleiades, we have the next step in the scale of stellar systems. The group of the Pleiades is the most famous star group, or indeed cluster, in the heavens. It has been known from the earliest ages, and is referred to in the book of Job and by Greek authors. The Pleiades, which in the winter months is one of the most noticeable objects in the sky, consists of 6 or 7 stars visible to the unaided eye. Of these stars, the largest is known as Alcyone. With a telescope, a great number of stars are to be seen in the Pleiades, and photography has disclosed the fact that many of the principal stars in the cluster are enveloped in nebulous matter. The Hyades, surrounding the bright star Aldebaran, forms a more scattered group of stars. Another interesting group, or rather cluster, is Praesepe, or the Beehive, in the constellation Cancer. The grandest clusters in the heavens are only to be seen with the aid of telescopes. Perhaps the 2 finest in the whole sky are those in Hercules and Centaurus. The cluster in Hercules may be seen with the aid of a small telescope, but it is only to be seen with advantage when a large instrument is applied to it. The Scottish astronomer Nichol of Glasgow remarked that, quote, "Probably no one who has beheld this cluster for the first time in a telescope of great power can refrain from a shout of wonder." End quote. Let us consider the conditions on a planet situated in the middle of such a cluster as that in Hercules. Such a world would know no night. Day would be everlasting. If such a world turned on its axis, sun after sun, blazing with light and heat, would pass across its sky in solemn procession. Indeed, the perpetual state of affairs on such a planet is equal to the spectacle which we on earth should behold if all the stars seen on the darkest and clearest night were to increase in brightness until even the faintest of them shone with a significant radiance to banish night. Herschel considered that this cluster contained 14,000 stars. Omega Centauri, only to be seen in the southern hemisphere, is a closely compressed cluster of thousands of stars. It may be seen with the unaided eye as a hazy star, but a good telescope is required to show it in all its beauty and grandeur. In the southern hemisphere are also situated two remarkable objects, the Magellanic Clouds, individually known as Nubecula Major and Nubecula Minor. Both of these are roughly of a circular form. Mr. Gore says of these two clusters, quote, "The larger cloud covers over 42 square degrees, and when examined with a telescope is found to consist of upward of 600 stars of the 6th to the 10th magnitude, with numerous fainter ones, and nearly 300 clusters and nebulae. The smaller Magellanic Cloud, Nubecula Minor, is fainter to the eye, and not so rich in the telescope." End quote. These clusters are in many ways the most remarkable objects in the heavens, mighty collections of suns, and probably worlds at an enormous distance from our world. Here we observe what Tennyson with scientific accuracy describes as, quote, "clusters and beds of worlds, and bee-like swarms, of suns and starry streams." End quote. End of chapter 20.
Chapter 21 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 21. The Motions of the Stars. The stars are generally designated as fixed stars to distinguish them from the planets or wandering stars. On a first consideration of the subject, the name fixed stars seems to describe very accurately the chief characteristics of these groups. While the planets move about through the zodiacal constellations, the stars preserve relatively to one another the same positions. The constellation Orion preserves throughout the ages its well-known form. Similarly, the plough shines down on us today as it did on the kingdom of Israel and on the plains of Troy, so that for all practical purposes we are correct in speaking of the fixed stars, and yet, scientifically speaking, we are wrong. The stars are no more fixed than are the planets. Indeed, many of the stars are moving through space with a velocity far greater than the swiftest of the planets. But so distant are the stars, so deep are they sunk in the depths of space, that in the course of hundreds, even thousands of years, the casual stargazer can detect no difference in their positions. But casual stargazing, or even intelligent observation of the stars with the unaided eye, is a very different thing from careful and patient measurement. The ancient astronomers, even when they measured carefully the positions of the stars, detected no change in their positions, and hence they believed the stars to be literally fixed to the inside of a huge sphere which rotated once in 24 hours. And even after it had been shown that the earth rotated on its axis and that there was no literal sphere, the idea was still maintained that the stars were motionless. At length it was found in 1715 that the star Arcturus was in motion. Halley compared its position as noted by his own observations with its position in the old catalogues, and he found that unmistakably the star had moved. Here was an extraordinary discovery. The fixed stars were not fixed. Since the time of Halley, the proper motions, as they are called, of many other stars have been measured and estimated, until at the present moment, in the estimate of Professor Dyson, Astronomer Royal of Scotland, the proper motions of 10,000 stars have been measured. The stars whose motions have been measured travel with various velocities. The swiftest star of all is an 8th magnitude star in the southern hemisphere. This little object is not designated by a name or a letter, or even an ordinary number. Its designation is Gould's Cordova zones, 5 hour 2:43. This is the swiftest known star in the heavens, and an idea of its vast distance may be obtained from the statement that the star would require 200 years to move over a space equal to the moon's apparent diameter. The next swiftest star is an insignificant star in Ursa Major, which is known as 1830 Groombridge, that being its number in the catalogue of the astronomer Groombridge, who lived early in the last century. This star would in 265 years move over a space in the heavens equal to the sun's apparent diameter, and in 185,000 years would complete a revolution of the whole sky. Next to 1830 Groombridge come two small stars in the southern hemisphere, and next our nearer neighbors in space 61 Cygni and Alpha Centauri, the distances of both of which have been measured. The real velocity of Groombridge 1830 is 128 miles a second. 61 Cygni moves at the rate of 30 miles per second, while the bright star Arcturus has been calculated to have a velocity of no less than 376 miles per second. The Sun is a star. It possesses points in common with many of the suns of space, and as the stars are moving, is it not possible that the Sun is also moving? At first sight, it looks almost impossible to determine the motion of our Sun if it does move, for it is obvious that if the Sun is moving through space, the Earth and other planets will be carried along with it, just as the Moon is carried along with the Earth. It is quite plain, therefore, that if the Sun does move, there will be a corresponding displacement of the stars, just as there is in our solar system a displacement of the Sun resulting from the motion of the Earth. But here a complication enters into the problem. If the stars were stationary, it would be quite an easy matter to detect from their displacements the motion of the Sun. But they're not stationary. Each star is moving through space in its own particular direction, and with its own particular velocity. Thus the problem becomes almost insuperable. Nevertheless, it was tackled and solved over 100 years ago, and its solution is one of those brilliant strokes of genius which astronomy owes to Herschel. It was obvious to Herschel that if the Sun is moving in a certain direction, the stars in front will appear to open out, and those behind to close up. Of course, as already mentioned, this is complicated by the motions of the stars themselves. Nevertheless, Herschel, by an ingenious method of separating the real from the apparent motions of 7 stars, was able to show that the Sun was moving towards a point in the constellation Hercules, near to the apparent position of the star Lambda Herculis. Herschel believed the rate of the solar motion to be, quote, certainly not less than the Earth has in her annual orbit, end quote. However, the general opinion of astronomers is that the velocity of the Sun is about 11 miles per second, somewhat less than the rate of our planet's motion in its orbit. It has now been ascertained that the point towards which the Sun is moving is not in Hercules, but in the neighboring constellation Lyra, near to the star known as Delta Lyrae. If we give this great discovery a moment's consideration, we cannot but be impressed with it. Not only does the Earth revolve round the Sun, but it follows the Sun in its endless journey through space. And not only is the Earth moving round the Sun at the rate of 18 miles a second, but it is being carried along with it at the rate of 11 miles a second. Yet so vast is the space surrounding the solar system, and so completely isolated from the rest of the universe, that although the Sun has been moving at the rapid rate of 11 miles per second throughout the time in which the human race has been in existence, yet the resulting displacements of the stars are utterly imperceptible to the unaided eye. Sir Robert Ball explains very clearly the enormity of the stellar distances and the isolation of the solar system in the following words, quote, "The Sun, and with it the whole solar system, is bound on a voyage to that part of the sky which is marked by the star Delta Lyrae. It also appears that the speed with which the motion is urged is such as to bring us every day about 700,000 miles nearer to this part of the sky. As you look at Delta Lyrae tonight, you may reflect that within the last 24 hours you have traveled toward it through a distance of nearly 750,000 of miles. So great are the stellar distances that a period of not less than 180,000 years would be required before our system, even moving at this impetuous speed, could traverse a distance equal to that by which we are separated from the nearest of the stars." End quote. Mention has been made of the marvelous method of finding by means of the spectroscope the motions of bodies in the line of vision. In this way, the motions of many stars have been measured. When we measure the proper motion of a star over the face of the sky, we are in reality only measuring that part of the motion which is across the line of vision. The star may be moving towards or away from the Earth, but that part of the motion could never be detected by the purely telescopic method. It is here that Doppler's method comes in conveniently. The first results were obtained by the late Sir William Huggins as long ago as 1868. Very satisfactory results were reached by the late Dr. Vogel, who applied photography to this branch of research. Vogel found that 10 miles a second was the average velocity of stars in the direct line of sight. Some stars, however, proved swifter and some slower than the average. Thus the brilliant star, Aldebaran, is moving away from the solar system at the rate of 30 miles a second. Perhaps the most remarkable fact about the motions of the stars is that some stars share their proper motions with others. Flammarion mentions the case of Regulus, the brightest star in Leo, which travels at the same rate as a faint star of the 8th magnitude. When more than two stars have a common proper motion, the phenomenon is known as star drift. The best known instance is afforded by 5 of the 7 stars of the Plough. Each of these stars moves with the same velocity in the same direction. Not only do these stars have the same velocity across the line of sight, the spectroscope proves that they have the same motion in the line of vision also, so that they certainly form a connected system, although they are separated from one another by billions of miles. Does any law regulate the motions of the stars? This problem has exercised the minds of astronomers for many years and has not been solved, but this is not to be wondered at. Even after the motions of the planets were known and could be predicted, the law of the planetary motions was unknown, and many years, indeed centuries, elapsed before it was shown that the planets were in revolution around the sun. It is therefore not remarkable that no law has been detected. Several speculations have been made as to the revolution of the stars round some central body. A well-known German astronomer, Argelander, suggested that the central body of the stellar system was situated in the constellation Perseus. Mädler, another famous German astronomer, after an elaborate investigation, believed himself to have obtained satisfactory evidence that the Sun and all the other stars were in revolution around Alcyone, the chief star of the Pleiades. But neither of these theories has been accepted, and at the present time astronomers do not believe that there is a central sun, large and powerful enough to control the motions of the other stars. Flammarion, in one of his picturesque illustrations, compares our solar system to an absolute monarchy with the sun as despot, and the system of the stars to a federated republic without a dominating authority. End of chapter 21. Read by Sandra, Montreal, 2022.
Chapter 22 of The Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Taylor Nuffer. The Romance of Modern Astronomy by Hector Macpherson. Chapter 22, The Fire Mist. Perhaps the most remarkable objects in the heavens are the hazy celestial clouds known as nebulae, or, as they have been picturesquely called, the fire mist. Even with the unaided eye, 2 of the most famous nebulae in the heavens are partly visible. On a clear winter's night, the middle star of the Sword of Orion is seen to be somewhat hazy, and even a small-hand telescope will show it as a cloud on the dark background of the sky. This is the famous object known as the Great Nebula in Orion, considered by all astronomers to be one of the finest sights in the heavens. Similarly, a keen eye will detect a hazy spot of light in the constellation Andromeda, which the smallest optical power resolves into a nebula. These are the 2 most famous nebulae in the heavens. The Andromeda Nebula is the more easily seen without telescopic aid, yet the other is considered by far the grander object of the 2. Even in a small telescope, the Orion Nebula is certainly the more interesting and awe-inspiring. It was first observed by a Swiss named Sist in 1618, and it is somewhat remarkable that it was not discovered by Galileo. The first observation on it was made by Huygens, who described the Great Nebula as follows. In the Sword of Orion are 3 stars quite close together. In 1656, as I chanced to be viewing the middle one of these with a telescope, instead of a single star, 12 showed themselves. Increase of telescopic power has shown the Orion Nebula to be more and more complex, until today it is known to be part of a mighty nebulous system, enveloping the entire constellation of Orion. Another of the diffused nebulae not visible to the unaided eye is that known as the North America Nebulae in Cygnus. This nebula was discovered by Dr. Wolf, who was so impressed by its resemblance to the map of North America that he gave it the name which it has retained ever since. The Great Nebula in Andromeda is a much less diffused mass than that in Orion. Its distance from the solar system seems to be very great. One of the ablest of modern astronomers has calculated its possible diameter, and he finds it to be so great that light would require many years to pass from one side of the nebula to the other. It has been calculated that if, on a map of this object, we were to lay down a map of the entire solar system drawn to scale, it would be a mere speck compared to the nebula. What are the nebulae? In the end of the 18th century, the general idea was that the nebulae were all star clusters, too far away for the stars composing them to be visible separately. Herschel, after sharing this view for some time, came to the conclusion that the nebulous light was not of a starry nature, but was composed of huge masses of glowing gas. There was nothing, however, to prove beyond doubt the correctness of his view, and even Sir David Brewster in 1854, in More Worlds Than One, declared that increase of telescopic power would resolve all the nebulae, which, in his view, were all star clusters at enormous distances. Herschel's son, Sir John Herschel, also shared this view. Telescope after telescope was turned on the nebulae with the hope of resolving them into stars, but the attempts proved futile. The gigantic reflector erected by the Earl of Rothesay at his estate in Ireland in 1845 was turned to the nebulae in the hope that at last they would be resolved into stars. Lord Rothesay himself considered that he had partially resolved the Orion nebulae, and that a little increase of telescopic power would prove beyond all doubt that it was a star cluster. The refractor of Cambridge, Massachusetts, USA, was said to have also accomplished the resolution of the nebulae. Only 5 years after Kirchhoff's discovery of the principles of spectrum analysis, Sir William Huggins, on August 29, 1864, turned the spectroscope on the nebulae in Draco. The spectrum showed that the nebulae were a mass of incandescent gas. In Sir William Huggins' own words, these nebulae are shown by the prism to be enormous gaseous systems. He then observed the Orion Nebula and showed it to be also gaseous. After all, Herschel had been right, and other astronomers wrong. Huggins also proved that the Ring Nebula in Lyra and the Dumbbell Nebula are gaseous. The spectra of the Great Nebula in Andromeda and the Great Spiral Nebula are more complicated, and they are considered to be in a further stage of their existence than the Great Nebulae in Orion. There are various shapes of nebulae. Some, like the Andromeda Nebula, are elliptical. Others, like the Ring Nebula in Lyra, annular. Others round like planets, and known as planetary nebula. Others widely diffused, like the nebula in Orion and the nebula surrounding Eta Argus. Others spiral, like the nebula in Cain's Venation, and many other varieties. Some years ago, the late Professor Keeler, director of the Lick Observatory, devoted himself to nebular astronomy. The results which he gained were striking. On one occasion, he was photographing a certain nebula in the constellation Pegasus, and was amazed, on developing the plate, to find that not only the nebula, but 20 others had been photographed. In the constellation Andromeda, he actually found 32 nebulae reproduced on a small photographic plate. This shows the immense number of nebulae. He considered with the Crossley reflector, the instrument with which he made his observations, 120,000 new nebulae would be visible. Half of these probably spiral. More recently, Professor Turenne of the same observatory announces that probably 300,000 nebulae are within reach of the same instrument. The gaseous nebulae in the heavens are to be counted by thousands. We cannot measure the distance from us to any of them, and therefore we are unable even to estimate their size. Sir Robert Ball, writing on the Great Nebula in Orion, says, "As the eye follows the ramifications of the great nebula, ever fading away in brightness until it dissolves in the background of the sky, as we look at the multitudes of stars which sparkle out from the depths of the great glowing gas, As we ponder on the marvelous outlines of a portion of the nebula, we are tempted to ask what the true magnitude of this object must really be. The only means of learning the true length and breadth of a celestial object depends upon our having first discovered the distance from us at which this object is situated. Unhappily, we are entirely ignorant of what this distance may be in the case of the great nebula in Orion. We shall, however, certainly not err on the side of exaggeration if we assert that the great nebula must be many millions of times larger than that group of bodies which we call the solar system. We can form no idea of the appearance of the nebula at close quarters. We can say that planets are globes like the Earth, with days, nights, seasons, and years. We can assert that the stars are suns like our sun, probably with planets revolving around them. We can even form some idea of what the scene must be at the center of a star cluster. But in the case of a nebula, our imagination fails. Their immense size, their enormous distance from our system, and the mighty changes which are believed to be progress in their midst, show us in a new light the insignificance of the Earth, and increase our astonishment when we remember that only 300 years ago our little planet was believed to be the center of the universe. Many telescopic observations have been made on nebula in the hope of determining whether, like the stars, they have a proper motion, but all these attempts have been futile. Professor Keeler, however, was successful in measuring the velocities of 10 nebulae in the line of sight by means of the spectroscopic method. He found a well-known nebula in Draco to be moving towards the solar system at the rate of 40 miles a second, and the Orion Nebula to be receding at a rate of 11 miles a second. Thus, the mighty fire mists are sailing through space on an endless journey, just as the stars and the comets are. We cannot fully comprehend the meaning of our own thoughts when we reflect that an enormous diffused mass of gas, many times larger than the solar system, is in rapid motion through the depths of space, covering 40 miles in 1 second of time. Truly, the universe is more wonderful than we can comprehend. End of chapter 22.
Chapter 23 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. The Romance of Modern Astronomy by Hector Macpherson. Chapter 23. The Galaxy. When we turn our eyes to the heavens on any clear moonless night, we cannot but be impressed with the majestic stream of milky light which spans the heavens like a mighty arch. This is the Milky Way, or galaxy, the ground plan of the stars. The galaxy traverses the constellations Scorpio, Sagittarius, Aquila, Cygnus, Cepheus, Cassiopeia, Perseus, Auriga, Gemini, Canis Major, Monoceros, Argo, Crua, Era, and Centaurus. It has been known from the earliest ages, and many speculations as to its true nature were made by the ancient Greeks. In the opinion of Aristotle, the galaxy was due to atmospheric vapors, while Anaxagoras held the absurd opinion that it was the shadow of the earth. Several acute thinkers among the Greeks, however, were of the opinion that the galaxy was nothing more than a collection of very faint stars, too faint to be separately seen. When Galileo turned his newly invented telescope to the heavens, this theory was at once found to be the true one. For centuries the galaxy has arrested the attention not only of men of science, but of all thoughtful observers of the heavens, and it is referred to by many of the poets. Wordsworth calls it heaven's broad causeway paved with stars, and Milton's beautiful description of it is not only poetic but scientific. A broad and ample road whose dust is gold, the pavement stars as stars to thee appear, seen in the galaxy that Milky Way, which nightly as a circling zone thou seest, powdered with stars. This broad and ample road was specially studied by Galileo, but of course his telescope was far too small to resolve the galaxy into stars. There were parts of the galaxy, writes Mr. Peck, that Galileo's telescope utterly failed to penetrate, and there still remained in the background the same misty light which had for so many centuries engaged the attention of astronomers. With every increase of telescopic power, more stars were seen, and greater depths were reached, but only to find, as Galileo had found, that some parts would require a more powerful instrument to reveal the individual stars that by being crowded so closely together caused this cloudy light. And even when Sir William Herschel applied his powerful reflectors to this part of the heavens, and reached still farther depths, there was yet to be seen that same milky light which speaks of the myriads of stars to be revealed. Nay, even Lord Rosse, with his gigantic telescope, could not resolve some of the luminous patches scattered throughout the Milky Way. Since the time of Lord Rosse, photography has been applied to the galaxy with striking success by three distinguished photographers of the sky: Professor Max Wolf, Professor Barnard, and the late Dr. Isaac Roberts. These astronomers have shown the constitution of the Milky Way to be exceedingly complex. The stars are, in many cases, intermixed with nebulous matter. Another remarkable feature of the galaxy is the presence in it of rifts and chasms. There is, for instance, a typical chasm in the southern Milky Way known as the coal sack, and there are many others. Dr. Wolf's remarkable series of photographs, too, revealed many smaller rifts which were previously unknown. Through these rifts we evidently get a view into the depths of space beyond the galaxy, into the region which has been designated the darkness behind the stars. Another remarkable feature of the galaxy is the existence of streams of stars. In Cygnus, close to the star Deneb or Alpha Cygni, there is a typical instance of a star stream, which may be observed with a binocular. Many others of these are to be seen in the galaxy, stars obviously connected, which may yet be separated by enormous distances. Let us consider what streams of suns are. They are aggregations of vast orbs, some larger and some smaller than the mighty sun. Each of them possibly the center of a system of planets, abodes probably of human life. It is difficult to conceive of the utter insignificance of our planet, indeed of our sun and solar system, compared with these mighty star streams. Seen from these orbs, the sun itself, if visible at all, will be seen as a faint little star, and the earth and planets, of course, will be totally invisible. If the sun were to be suddenly extinguished, the consequences would be very serious so far as our world and the other planets were concerned. All life would disappear from the surface of the earth, which would move through space as a dead world. But the extinction of the sun, with the consequent destruction of the human race, would be absolutely unimportant, if not unknown, to the universe at large. As Sir Robert Ball has expressed it, all the stars of heaven would continue to shine as before. Not a point in one of the constellations would be altered, not a variation in the brightness, not a change in the hue of any star could be noticed. The thousands of nebulae and clusters would be absolutely unaltered. In fact, the total extinction of the sun would hardly be remarked in the newspapers published in the Pleiades or in Orion. There might possibly be a little line somewhere in an odd corner to the effect, Mr. So-and-so, our well-known astronomer, has noticed that a tiny star, inconspicuous to the eye, and absolutely of no importance whatever, has now become invisible. The galaxy is no mere isolated phenomena in the heavens. It is the ground plan of the universe. It was shown by Herschel 100 years ago that there are more stars in the regions of the heavens near to the Milky Way than in the opposite regions. In other words, the stars increase up to the galaxy, which seems to be a region of stellar clustering. It has been shown by Professor Schiaparelli and the late Mr. Proctor that the stars visible to the unaided eye are more numerous on and near the galaxy, as well as the telescopic stars. What light does this throw on the great question of the construction of the universe, of the relation of the entire number of stars which are to be seen with the most powerful telescope to one another, and to the galaxy itself? The prevailing idea seems to be that the entire agglomeration of stars visible to the most powerful telescopes, known as the stellar universe, forms a globe of stars, and that the galaxy forms an equatorial zone of that globe, that there is greater clustering, that is to say, that the stars are closer together, in the galaxy than elsewhere in the universe. At the same time, there may be a greater extension of stars in the line of our vision in the direction of the galaxy. Although the above seems a fairly good outline of the entire universe of stars, there are a number of local peculiarities among the stars. For instance, as already mentioned, stars of the first or white type are the most prevalent on or near the galaxy. The investigations of Dr. Keptin, a distinguished Dutch astronomer, have disclosed the fact that near the vicinity of our Sun contains almost exclusively stars of the solar or yellow type, the same class as our own Sun. Another remarkable fact is that the stars in the constellation Orion have, with the exception of Betelgeuse, similar spectra, and that these stars are closely intermixed with the great nebulae. Professor Keptin's studies have also told us of the possible existence of two great streams of stars moving in opposite directions. These facts are all very disconnected, but the reason of their disconnection is that astronomers have not yet learned enough of the stellar universe and of its dominant feature, the galaxy, to form a complete theory of its constitution. As Mr. Gore has well remarked, the Copernicus of the sidereal system has not yet arrived, and it may be many years or even centuries before this great problem is satisfactorily solved. One point in connection with the system of the stars, however, is tolerably certain. The collection of orbs, which we call the universe of stars, is limited in extent. Probably space is infinite, but the number of stars in the stellar system is not infinite. There may be 500 million or more, but they cannot be infinite in number. There is a well-known law of optics which shows that if the stars were infinite in number, the whole sky would shine with the brightness of the sun, as a result of the blazing of an infinite number of suns extending to an infinite distance. In some parts of the heavens, too, the limits of the universe seem to have been reached. For instance, at a part of the sky diametrically opposite to the Milky Way, Sir William Herschel with his mighty telescope saw a certain number of stars. An Italian observer, Professor Caloria, using quite a small instrument, saw exactly the same number of stars. This showed that Herschel's telescope was unable to show any more stars in that direction than the little instrument of Caloria, because the stars in that part of the universe have a definite limit. At the same time, its diameter is almost unthinkable. Even on the most moderate estimate, the universe extends undoubtedly to an enormous distance, a distance which we can only estimate and which we are unable to conceive. Yet it is limited in extent. But what, after all, is the stellar universe? It is not the universe. It is merely one of a number of similar systems scattered throughout space. We have never seen such systems, nor can we expect to see them. When astronomers are still unable completely to pierce through our own stellar systems, it would be futile to expect to catch a glimpse of another system. Reasoning, however, from first principles, astronomers are on the whole inclined to believe in the existence of other systems, external universes. Mr. Gore has made a calculation of the possible distance of one of these external universes. Assuming that the distance of the nearest of these systems is proportionate to that separating our system from Alpha Centauri, he reaches the astounding conclusion that the distance of the nearest of these external universes is no less than 520 sextillion 149 quintillion 600 quadrillion miles. This is, of course, pure speculation. The external universe, if it exists, as it probably does, may be at a great distance, but it is most unlikely to be any nearer. Our minds are overwhelmed with the thoughts suggested by this calculation. We cannot fully comprehend the extent of the system of stars. Still less can we conceive of an external system. Mr. Gore, overwhelmed with the marvels disclosed in this calculation, with the revelation of infinity which astronomy gives us, closes his investigations with the following beautiful thought. The numbers of stars and systems really existing, but invisible to us, may be practically infinite. Could we speed our flight through space on angel wings, beyond the confines of our limited universe, to a distance so great that the interval which separates us from the remotest fixed star might be considered as merely a step on our celestial journey, what further creations might not then be revealed to our wondering vision? Systems of a higher order might then be unfolded to our view, compared with which the whole of our visible heavens might appear like a grain of sand on the ocean shore. Systems perhaps stretching to infinity before us, and reaching at last the glorious mansions of the Almighty, the throne of the Eternal. End of chapter 23.
Chapter 24 of the Romance of Modern Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Astronomy by Hector Macpherson. Chapter 24. The Origin of the Universe. One of the most fascinating branches of astronomy is that in which astronomers have attempted to discover the method and the evolution and development of the universe. Most of us believe that, in the beginning, God created the heavens and the earth, and that the earth was without form and void. Both of these sublime truths are taught by science as well as by theology. Science cannot go beyond that. It can only, with all reverence, indicate the method by which the Creator has brought into existence this stupendous universe. The general opinion of astronomers is that the method of creation is disclosed to us in the remarkable law of evolution. Indeed, the law of evolution, as developed in the nebular theory, may now be regarded as an established scientific truth. The first hint of the nebular theory, the development of the solar system from masses of nebulous matter, was given by the Scottish astronomer James Ferguson. It was in a private letter that Ferguson first put forward his views of the nebular theory, an effort to explain the method of the creation as described in Genesis. He was followed by the German philosopher Kant, who in 1754 propounded his views on the development of the planetary system from a chaotic nebula or mass of incandescent gas. The complete nebular theory was, however, put forward independently about 100 years ago by Herschel and the French astronomer Laplace. These two astronomers reached the nebular theory by different methods, Laplace by mathematical reasoning, and Herschel by direct observation of the heavens with his great telescope. Laplace noticed that in the solar system the planets all revolved around the sun in the same direction, from west to east, and that each of the satellites known to him revolved round the planets in the same direction. There was no obvious reason why the planets should revolve in this direction more than in any other. Another fact noted by Laplace was that all the planets revolved round the sun and the satellites round their primaries in almost the same plane or level as the earth moved round the sun. There was no obvious reason why the planets should all move in this plane, yet, as a well-known astronomer has remarked, there are 1,000,000 chances to 1 in favor of the supposition that the disposition of the movements of the planets has not been the result of chance. Laplace accordingly put forward his explanation. This was that the solar system had originally existed in the form of a mass of incandescent gas or nebula. In contracting, he pointed out, this nebula had shed rings which condensed to form the planets, and having condensed almost to its utmost, now forms the sun, the central body of the solar system, which is still contracting. Laplace had never seen a nebula, for the simple reason that he did not possess a telescope. Such an object probably existed in his imagination only. His great contemporary Herschel had seen hundreds of nebulae, had classified them, studied them, theorized concerning them. Quite independently of Laplace, Herschel was led to the view that these nebulae he was observing would in course of time develop into systems of suns and planets, and that conversely the solar system must have once existed in the form of a great diffused nebula. Since the days of these astronomers, a further addition to our knowledge has been made by Professor Darwin of Cambridge. According to his researches, millions of years ago the earth and moon were not separate bodies. At that time our planet was a gaseous mass, spinning on its axis in a very short period between 3 and 5 hours. In consequence of this rapid rotation, and in consequence of the tide raised by the sun, the earth split in two, and the smaller of these two parts now forms the moon. This hypothesis, rigorously developed by mathematics, is distinctly supplementary to the nebular theory, and explains in greater detail the particular development of that part of the solar domain known as the Earth-Moon system. Since the days of Herschel and Laplace, astronomical science has progressed remarkably. The nebular theory has been modified with the advance of knowledge, but the central idea, the development of the universe as we know it from the masses of incandescent gas, is thoroughly established. Thanks to the spectroscope, that marvelous instrument by which we are enabled to ascertain the elements of which sun, stars, and nebulae are composed, we now know that the nebulae are really gaseous, a point on which Herschel could merely theorize. And what is even more important, we are enabled to trace the order of development. We see nebulae and stars in all the stages through which our solar system has passed and will pass, and in the other planets of the solar system we behold the stages through which our Earth has passed and will pass. By a careful study of the heavens as they are today, we are enabled to read the past of our world and approximately to trace its future. In the heavens we behold stars and nebulae in every stage of evolution. First of all, we have widely different nebulae, of which the Orion nebula is a type. Next, we have a more condensed nebula, such as that in Andromeda, and then the stage of the spiral nebula. These spiral nebulae, of which there are many known, in the heavens are not gaseous. They are partially solidified and are already breaking up into subordinate centers of condensation, which will in course of time become planets or small suns. These larger nebulae, like the Orion nebula and the Great Spiral, will in all probability develop into clusters of stars. The smaller nebulae develop into stars similar to our own sun, attended by systems of planets. By means of the spectroscope we are enabled to trace the development of these stars after they pass out of the nebulous stage. We have first the helium stars of a bluish-white tint, in which the element helium is predominant, which are largely gaseous in their constitution. Next we have the white stars proper, in which the gases are not so widely diffused. Next we have the yellow stars, similar to our own sun, orbs in their prime, slowly but surely condensing. The next stage is that of the red stars, past the zenith of their careers, and slowly dying out. In this class are indeed many of the interesting objects known as visible stars, which are already becoming unstable in their light, just as a lamp flickers when it is going out. Lastly, we have the dark stars, which are only known to exist by their influence on the bright ones. These orbs are extinct and dead suns, and they roll through space, a solemn example of the goal to which our sun, among others, is steadily moving. The earth, our own world as we have seen, has developed from the conditions of a little local condensation in the primitive nebula. From the same condensation has developed our satellite, the moon. It may be interesting to trace the various stages through which our earth has passed, as exemplified in the objects in the heavens around us. In the early stages of its history, the earth was without form and void, as the book of Genesis so simply and graphically tells us. In scientific language, the earth existed in the shape of an unshaped gaseous condensation in a chaotic nebula. This was the first stage of the earth's existence. In the first day of creation, the Bible tells us, God said, "Let there be light," and there was light. Independently, science tells us the same. In passing, we may note that we must not interpret the word day as meaning our terrestrial period of 24 hours. Such a period did not exist when the earth was without form and void, and darkness was upon the face of the deep. In those early times the earth was self-luminous. Light came into existence as the nebulous mass slowly contracted. This light was in existence so far as the earth was concerned, long before the light of the sun. Next we have the period when the earth had solidified, so as to admit of the existence of dry land, air, and water. Before this was an intermediate period when the transformation was being effected. Professor Lowell, in his recent work on the evolution of the worlds, traces very completely the evolution of the earth from the gaseous state to its present condition. Not until the temperature of the earth had fallen to 100 degrees centigrade in the outer regions of the atmosphere could clouds form, and not until the surface had reached the same temperature was it possible for the clouds to settle on the surface as oceans. As Professor Lowell writes, "Reasoning thus presents us with a picture of our earth as a vast seething cauldron from which steam condensing into cloud was precipitated upon a heated layer of rock, to rise in clouds of steam again. The solid surface had by this time formed, thickening slowly and more or less irregularly, and into its larger dimples the waters settled as it grew, deepening them into the great ocean basins of today. Later on the crust hardened, while the oceans were still boiling seas. These oceans, according to Lowell, must have produced a small universe of cloud, all over the earth's surface. After this the earth began to sustain the lower forms of life. Vegetation, the flora of paleologic times, flourished, sustained by the heat of the earth itself below the cloud masses. So, again to quote Professor Lowell, the flora of paleologic times, as we see both at their advent in the Devonian and from their superb development in the Carboniferous era, consisted wholly of forms whose descendants now seek the shade. These plants, grown to the dimensions of trees, inhabited equally the tropic, the temperate, and the frigid zones as we know them now. They grew right on, day in, day out. The climate then was as continuous as it was widespread. The reason of the equality of climate all over the globe was the fact that the light and the heat of the sun were shut off by the great cloud masses, and the heat was wholly supplied by the earth itself. This produced the half-light which suits the growth and development of the tree ferns. Hence the luxuriant vegetation of ancient days. By and by the clouds dispersed. It was only then, in reality, that the year began, and that the seasons made their appearance. As the sun was invisible, and its rays played little part in the climate of the earth, the annual revolution had no visible effects. But with the clearing of the sky, the outer universe came into existence, so far as the earth was concerned. An interesting point may be mentioned here, which Professor Lowell does not touch on in his book, and which is indeed seldom dealt with. It has been the fashion among many scientists to treat the record of creation in the first chapter of Genesis either as a story or as an allegorical history. But it is somewhat remarkable how close is the correspondence between the biblical account and the latest scientific theory as developed by Professor Lowell. After detailing the bringing forth of vegetation consequent on the appearance of dry land, which followed the division of the waters which were under the firmament from the waters which were above the firmament, the biblical record says, "And God said, Let there be lights in the firmament of the heavens, to divide the day from the night, and let them be for sign, and for seasons, and for days and years. And let them be for lights in the firmament of the heaven, to give light upon the earth. And it was so." Professor Lowell, who traces the earth's history from a purely scientific standpoint, says quite explicitly, "Only with the clearing of the sky did the seasons come in, to register time by stamping its record on the trees. Before that, summer and winter, spring and autumn, were unknown." He also shows that before the clearing of the sky there was no climate. The downpours of rain from the upper waters must have been stupendous. There was imperfect recognition of day and night. Dull, somber days alternated with nights black as pitch. The moment the sun was let in, all this changed, though not in a twinkling. The change came on most gradually. We can see in our mind's eye the first opening in the great welkin, permitting the earth its initial peeps of the world beyond. Eventually the clouds parted afresh and farther, and the earth began to open its eye to the universe without. The correspondence is complete between the account of modern science and the account of the ancient biblical writer. So there need be no discrepancy between a belief in the evolution of the earth as described by modern science and a belief in the accuracy and trustworthiness of the biblical record. Professor Lowell proceeds to trace the further development of our planet in what he calls the sun-sustained stage. The temperature of the oceans fell, and a totally different variety of animals and plants came into being. The oceans were inhabited by fishes in the earlier days. But after the clearing of the skies, the land became peopled with different varieties of animals and reptiles. Then came the development of vegetation, depending on the change of the seasons. Next followed the colored flowers. The earth became beautiful, clothed with all the verdure of the flowers. And this sudden development of beauty was due to the fact that the sun had become the dominant factor in the earth's organic life. The sun, so far as the earth was concerned, did not come into existence until after the original appearance of life on earth, and the celestial bodies in general were invisible until the fourth day or period of creation. Jupiter is a much larger planet than ours, and at a much earlier stage of its evolution. Therefore, a careful study of it throws light on the history of the earth. As already mentioned, after the invention of the telescope, it was found that the visible surface of Jupiter was diversified by numerous markings known as belts. As astronomical observation progressed, it was found that these were belts of dense clouds, so dense that it is impossible to see through them the real surface of Jupiter. It was originally supposed by astronomers that these clouds were of the same nature as our terrestrial clouds raised up by the heat of the sun. But it has been conclusively shown that this is impossible. The atmosphere of Jupiter is much more cloudy than our own, and yet the planet is many times farther from the sun than the earth. The clouds are certainly raised by heat, but not by sun heat. They are raised by the intense heat of the planet itself, which does not permit the vapors to settle down as oceans, but raises them into the atmosphere, in which they float in the form of cloud belts. Here, then, we have a world in a condition similar to that of our earth before the accomplishment of the work of the third day of creation, and consequently before the work of the fourth day, when the sun, moon, and stars appeared. Jupiter will not read its fourth day until the clouds roll away and the glories of the other universe are visible from the surface of the giant planet. Jupiter is the best example of a planet in an earlier state of development than our earth. Other examples may be cited in Saturn, Uranus, and Neptune. Each of these is much larger than the earth, and each of these appears to be in a condition of great heat and at present quite unfitted to be the abode of living creatures. In Venus we have a planet in the same stage of planetary life as Earth, because it is the same size. In Mars we have a stage further. This planet is smaller than the Earth, and has consequently run more swiftly through the stages of its evolution. On Mars, planetary old age has set in. The oceans are all practically dried up, and their place has been taken by marshy tracts of vegetation, and the atmosphere is very rare. In the Moon, our own satellite, we have the final stage of planetary life. The Moon is a dead world. It has practically no atmosphere, and the oceans which once must have existed on its surface have completely disappeared. The surface of the Moon is a succession of very mountainous regions, succeeded by flat, gray, barren plains, which are supposed, owing to their low level, to represent the old ocean beds of the Moon, which in earlier days were filled with water. The Moon rolls through open space, a dead world, an indication of the future which awaits our own planet. Just as in a garden, where we behold flowers in different stages of development, and may by the study of these indicate the life history of a given flower, and read its past and future, just as in the forest by noticing the various objects, from the tender shoot to the magnificent full-grown tree, we are able to tell the past and future of any member of the group. So in the heavens, by noting all the different stages of star and planet life, from the diffuse nebula to the dead world and the dark star, we are enabled with remarkable accuracy to read the past and future of our own dwelling place, the earth. To quote the reverent remark of Kepler, we are permitted to think the thoughts of God after him. We are enabled to trace in a partial manner the marvelously beautiful method by which the Creator has called into being this magnificent universe in which we live. And we realize in a new light the meaning of the words, "For my thoughts are not your thoughts, neither are your ways my ways, saith the Lord. For as the heavens are higher than the earth, so are my ways higher than your ways, and my thoughts than your thoughts." End of chapter 24.